Oh, hopefully the audio's right now. Okay, okay, perfect. So you can hear me on your video streaming. Okay, so today's goal is to complete learning segment trees and Fenwick trees. Huh. So yeah, today's the last day I'll be learning this Fenwick tree slash segment trees. Okay, I will be sharing my screen now. Let's go first.
What happens in a segment tree? Each of the individual elements present at each index, here 1 is present on the 0th index, 6 is present on the first index, 3 is present on the second index, and 5 is present on the third index, right? So initially what happens is these individual elements are present at the base level, right?
Hmm.
So these individual elements will be present at the base level. So this 0, 0 represents a range and its corresponding value in this node. Similarly, this is also a range and this is also a range. So for the base level, the value of the node will be equal to the value of the element present on that index in the initial array, right? Now let's see what happens. So if you remember, then what the question has asked us to do, it has asked us to initially calculate the bitwise OR of the individual elements, right? And after we calculate the bitwise OR of the individual elements, if the total number of elements are still greater than 1, then we again have to do a bitwise XOR operation. And we have to continue doing this in alternate fashion until there is only single element remaining at the bottom level, right? So here also we will do the same thing in the segment tree. So since every initial element is present at the base level initially, so it means that we will start from the base level only, right? So now what we have to do, we have to take the bitwise OR of the first two adjacent elements, that is these, and these next two adjacent elements, that is these, right?
Hmm.
So what will be the bitwise OR value of 1 and 6? So the bitwise OR of 1 and 6 will be equal to 7, right? And at the same time, let us also calculate the bitwise OR of 3 and 5. So 6 is 7 because this is what we have to do in the initial stage, right? That is on the first iteration of the original array. Similarly, we just calculated the bitwise OR of this 3 and 5. It is also equal to 7. So in this way, the bottom level is filled completely and also this level is filled here completely. And now we have to fill this level, that is this node. So now since we have done the first iteration on the original array, that is performing the bitwise OR operation on the adjacent elements and got these two elements, right? And since the total number of nodes, or you can say the total number of elements, so these two represent these two nodes, right? So since they are still greater than 1, it means that we again have to continue doing the bitwise operation in alternate fashion. So since at this level, let me write down here. So at this level, we perform bitwise OR operation. So it means that at this level now, we have to perform bitwise XOR operation. So in this level, these two are the only adjacent elements, right? So on performing the bitwise XOR operation, what will be the value? So since these two are same, it means that it will be equal to 0, right? So it will be equal to 0. So in this way, we fill the segment tree starting from the bottom level and going till the up level. And this is how the bit function works actually. It starts, it goes recursively in the left part first and the right part, and then continuously combine the left and right results into the parent node. So here we combine the results of these two nodes into this node. Similarly, we combine the results of these two nodes into these two nodes, and then finally combine the result of these two nodes into these two nodes. So I hope you have understood now how the segment tree actually builds and how the segment tree in this question will be built. So the parent node in this case is a single element, and this is our required v, right? This is what we have to calculate each and every time after performing the query. Since this was our given array, we called the build function that is initialize the segment tree, and in this way, our segment tree is made up from bottom to top. First, we calculated the bitwise OR of the adjacent elements, and in the next level, we calculated the bitwise OR of the adjacent elements, and thus we got the respective results each time, right? So now let us start performing the query. So what is the first query? So the first query is like this, that we have to assign. So the first query is like this, that we have to assign a value of 4 on the 0th index, right? That is 1 minus 1. If I try to do this here, that is in the 0th index, I have to assign a value of 4. So I have assigned now a value of 4 in this array. With that said, it means that I also have to update the status of the array in this segment tree. So I will call the function as, let us say the name of the segment tree is t. So I will say t.update 0th index equal to 4. So what this function will do, this will update my 0th index equal to 4. And if you see in the segment tree, then where is my 0th index located? So my 0th index is located at this range, right? That is the leftmost bottom node is my 0th index, right? So what does this update function will do? It will update this one value equal to 4 by recursively calling this update function. We will see later in the code how that will be implemented, and most of you must be knowing this already. So suppose now, after reaching this 0th index through recursion of this update function, we have reached this, right? So now what it will do? It will change this one equal to 4 because this is what the query has asked us to do. And by doing this, what has happened? By doing this, if you see, bitwise OR of these two adjacent elements will remain same. That is, will remain 7 or not. So it might or might not get changed, right? So let us see and try to do the new bitwise equal to 6 only. So it means that after I change this 1 equal to 4, the bitwise OR of these two adjacent elements also changed. It means that I also have to update this 7 equal to 6 now. I think there should be no doubt in this. So what does our update function will do now? It will update this 7 equal to this 6 here, right? So this is equal to 6. The only change that was needed was here. Why? Because the bitwise OR from which this is made is changed, right? Earlier it was 1, so the result was something different. But since now it has been changed to 4 as per the query, so the bitwise OR will also change now. So that's why it is equal to 6 now, right? And again, the update function will see that these two are my new elements, and it will try to evaluate the XOR value of the 6 and 7. Since earlier there was 7 here instead of 6, and the XOR of 7 was getting equal to 0, but since now this 7 has been replaced by this, so it will be like this way. We can move on to the. So this array corresponds to this segment tree with the required values in each and every node. So what was the second query? The second query was this 3 and 4. That is, we have to update the sequence of second index equal to 4. So I will say that this 3 has now become equal to 4. And once I change this 3 equal to 4, it means that I have modified this array. It means that I also have to modify the set. So I will again call this update function, but instead of calling it for 0, 4, I will now call it for 2, 4. That is, we have to update on the second index and update it with a value of 4 now. So this update function will recursively call itself until it reaches the previous query that since I have changed this element now, it means that whatever internal nodes are present by going in the upward direction till the top, each one of them will be changed, right? So since I have changed this node now, it means that the bitwise OR of these two will also change. That is, the value of this will also change now. And if the value of this node changes, it means that the bitwise OR of these two will also change, due to which this will also change. So let us erase this and let us recalculate the actual values. 0, 1. So this 6 and 5, that is two elements is 3 now. So I will write 3 here. So this is our new value of v, and if you remember, then this is our required output for the second query as well, right? So in this way, we performed the second query and got the correct value of v. I hope you are getting the concept what I'm doing every time, right? So let us now perform the third query. So according to the third query, let's see, it asks us to change the 0th index equal to 2, right? That is, the 0th index equal to 2. So this 4 will now become equal to 2, and since now I have changed 0th index equal to 2, that is this equal to 2. So I will call again this update function, and it will be something like 0th index equal to 2. So I have to update this 0th index equal to this 2 value, right? By calling this update function, it will recursively reach this node, and after it reaches this node, it will set this 4 equal to the new value that is just provided internally, that is this 6 and 3 will be changed, right? Or will be modified, and others will remain as it is. So let us now erase these old values and recalculate the actual values now. So the bitwise OR of 2 and 6, that is 0, 0, 1. I have to calculate the bitwise OR of the 6 and 5, that is 6 and 5. So 0, 1, 1, 0 and 0, 1, 0, 1. So what will be the bitwise OR? It will be 0, 0, 1, 1, which is equal to also the same thing since it is already reached. So again, segmentary whatever 2 log n already stored at the function. Update function is taking complexity is nothing but log n down. In order is what? It is nothing but log n. And right, and we make sure that our segmentary whatever we build and initialize, it is always a balanced segmentary, and the height of a balanced segmentary is what? It is nothing but log n. And hence we just need to travel a total of 2 log n times, right? First in going from up to down in order to reach 6, and after we update 6, again going back to the top in order to update the new values, which is nothing but log n only. And thus we say that the update operation is a log n operation. So what is the new time complexity for this approach? The new time complexity is nothing but m for the number of queries, and what I am doing for each query, I am just calling the update function, and this update function is taking a total of log n times, right? So that's why I can say that my new time complexity is m log n, and this is far better than what we got previously, and this will get accepted into the platform. Also, some of you might say that what about the query operation? What will be the time complexity of that query operation? Why I am not taking that into account? Because whenever I will call that query operation, that is t.query, since my result is already stored at the parent level, that is this level, it means that I don't have to travel through any of the nodes in this direction or any direction, right? Because my result, that is v, is already stored at the top. And since this segmentary is nothing but an array which we generally name as tree, right, or seg tree, so I will just return tree of 0. So what does this tree of 0 will represent? It will always represent the parent level value, that is this value. So I will just call this, and it will give me the topmost value. So in that case, so that's why by calling this query function, it will not take me any time complexity. Now let me tell you one last thing. Some of you might be wondering that, okay, we got this, but how we will make sure that at each of the level we have to perform either OR operation or XOR operation? How we will determine this? Let me erase this stuff so that I can make you this thing understand much better. So what I'm now saying is, how we will make sure that at this level we have to perform OR operation, or at some other level we have to perform XOR operation. How we will determine this? So in order to determine this, what I'm saying is, let us maintain another array, and let's say the name of the array is level. So by name it is obvious that it will represent the level of that node, right? This level array will hold the level of each and every node present in the segmentary. So since there are a total of 4n nodes that we considered as the segmentary size, so this level array will also have a size of 4n only, right? So we know that this is our 0th node, and this is our first node, this is our second node, this is our third, this is our fourth, this is our fifth, and this is our sixth. So in order to calculate the value of the node for the left and right child, we do nothing but, if my parent node has a value, let's say node, its left child is calculated as 2 into node plus 1, and the value of the node for the right child is calculated as 2 into node
2 into node plus 2.
2, right? That's why since the parent level has a value of 0 here, so 2 into 0 plus 1, which will be equal to 1 only, and it will be equal to 2. So that's why I named it here 0, 1, 2, 3, 4, 5, 6. You can calculate for each and every one, and the result will be same every time only, and it will be equal to 2. So that's why I named it here 0, 1, 2, 3, 4, 5, 6. You can calculate for each and every one, and the result will be same every time. So now what I'm saying is, let me write this level array here for a few of the elements. So actually this is of the size 4n, so it will go from 0 to 4n minus 1, right? So it will go till this point, but since here I have considered only 7 nodes, so I will write them here. So now what I will say is, so after I initialize the segment tree for the given original array in the question, that is calling the build function internally in the class, so each one of these nodes will be calculated, right? So at the same time, I will also fill this level array. So I will say that initially each one of these nodes in the base level has a value 1. The value of 3, 4, 5 and 6 nodes, that is these 4, will become equal to 1. And once these values will have been calculated, it's time to look upon these two now, right? So we will say now that, okay, we filled the values in this array, no problem. And now we want to fill the level array for this two node values, that is this 1 and 2. So what I will
Hmm?
say now is, since this has a level of 1, I will say now
Something
that
unknown to
the level of these two nodes will be the level of nothing but any one of its children node. Take any children, let's say the left one. So the level of the left child plus 1, level of the left child plus 1. So here it will become equal to 2, right? And after doing so, at the level of these two nodes will be the level of nothing but any one of this has no problem. And now we want to fill the level array for this two node values, that is this 1 and 2. So what I will say now is, since this has a level of 1, I will say now that the level of these two nodes will be the level of nothing but any one of its children node. Take any children, let's say the left one. So the level of the left child plus 1, level of the left child plus 1. So here it will become equal to 2, right? And after doing that, what will happen? I will fill the level value for the 0th node, that is this, and it will become equal to the level of this first node plus 1. So what is the level of the first node? It is equal to 2, right? So 2 plus 1, that is 3. So this will become equal to 3 now. So in this way, our level array will be calculated for each and every node present in this segment tree. But how this level array will help us in determining whether to perform OR operation or XOR operation at that particular level? So it's quite easy, because what is the similarity between these three and these all ones? These all are odd, right? And but these two are even.
Yeah.
And this parity check will help us in determining whether to perform OR operation or XOR operation on a particular level by seeing the parity of that level. So suppose I'm standing at this node, and we know that the level of this node now, that is 1, is 2, and this 2 is even, right? This is even. So if it is even, then what we will do? We will perform the bitwise OR operation. So let me write down here. So whenever if the level of a particular node is even, then what I have to do? I have to take the bitwise OR of left and right child, right? So since the level of this one was even here, I took the bitwise OR. Same for this, I took the bitwise OR because the level of 2 was 2, that was even, that is even. And now once the results are calculated for this level, I am present at this level. And now I will see the level of the 0th node in this level array. So what is the level of the 0th node? It is equal to 3. That is odd. So if it is odd, then what I will say is, if the level of an internal node is odd, then it means that I have to take what? I have to take the bitwise exclusive OR of the left and its right child. So here I will take the bitwise XOR of this left and right child. That is this. And hence this tree will have been calculated. So in this way, this level array is the bitwise XOR of this left and right child. That is this. And hence this tree will have been calculated. So in this way, this level array is helping us in determining whether to perform OR operation for a particular level or bitwise XOR for a particular level, right? So I hope you got the complete concept of this problem, how we use the segment tree and the level array in order to efficiently compute and update the base level node and compute the bitwise OR and XOR for each of the steps in log time. So this might have got a little messy, but I tried my very best in order to explain you with the visuals. So I think now it would be very good for us if you go to the code editor and actually code this up and understand how this code is working and finally submit it on the platform, right? Let us now go to the code editor and code this up quickly and see if we are right or not. So this was our brute force approach, right? So let me erase all of this. Let me quickly paste my standard segment tree template here. So as you can see, this is my standard segment tree template supporting only three operations, that is build, query and update. So this segment tree template needs to be modified, right? Because currently it supports range, sum and point update, and we have to modify a few things in all these three functions. And also we have to declare another level array just as we discussed in the approach. But first let us code the approach in the void function and do the initial things. So what we have to do? We have to first take the input of this NNM, right? After taking the inputs of NNM, we have to take the input of our 2 to the power n integers. Let's name it as sequence only, and the size of it will be 2 to the power n, initializing every value equal to 0. So just do this for taking the input. So just take the input like this. Once we take the input for the initial array, what we have to do next? I have to initialize the segment tree, right? So I will initialize the segment tree, and let's name this segment tree as small t, and I have to pass this sequence, right? And just by calling this, what it will do? It will build the segment tree in the initial state. We also discussed this in the explanation in the starting point, right? And now I have to take the input for the m queries, so it will go from 0 till m minus 1. I have to take the input for two integers, that is p and b. So I will say p and b, just take the input, and since this p is given in one based indexing, so I will say p minus equal to 1, right? Thereby converting it to 0 based. And now what we have to do? We have to do update the segment tree, right? But before that, I will first update it in the original sequence. So I will say sequence of this p equal to this b, that is the new value, and then I will call my update function, that is t.update, update the this array at the pth index and set it equal to b. And once I do this, what is my last task? My last task is to just compute the query, right? That is, I will say t.query. I will just call this. I will not pass any parameter. Why I am not calling any parameter here? Because I know that my result will always be stored at the top level, right? So that's why I am not calling any parameter. And then at last I will just do a return. So once we have written this code, let us now start modifying our segmented template. So as I told you that in the query we don't have to pass anything, right? We just have to return what? We have to return tree of 0. So what does this tree of 0 represent? It represents the value whatever is stored at the parent node. That is this value. So just by calling the query function and returning this tree of 0, as I told you that in the query we don't have to pass anything, right? We just have to return what? We have to return tree of 0. So what does this tree of 0 represent? It represents the value whatever is stored at the parent node. That is this value. So just by calling the query function and returning this tree of 0, it will give me the desired value of v. So what is this? This is the value of v that Xenia wants, right? And once I do this, now I also have to modify this build, query and update function to some extent. So I told you in the explanation that whenever the build function will be initialized or be called in the internal class, then along with setting the value at the base level, I will also need to update, I will also need to assign the level array, right? So for that, I will declare a level array here. So I will say vector of int level, and it will also be of the size of 4n only, just like the tree, right? So I will say level dot resize 4 into n with each and every element initially equal to 0, right? So once I do this, I can start assigning this level array here. So I will say level of this node will be equal to initially 1. That is, what I'm doing by this statement is initially I'm setting each and every element present at the leaf level, that is the base level, equal to 1. And this is an odd number, right? This is odd value. And then I told you, in order to decide for the internal node what will be its level, you can take the level of any of its child plus 1 value. So I can say here that the level of this node will be equal to level of any of its children. So let's say level of 2 into n plus 1. So this represents my left child, right?
Mm.
So it's level plus 1. You can write 2 into n plus 2, that is the right level, right child also, that will not matter because the level of both
Going to node plus one.
the children will be same. So suppose for this particular level, I want to determine the value of this tree of node. So what does this tree of node will represent?
Into n plus one. It should be 2 into node plus one.
It will represent either the bitwise OR operation or the bitwise OR operation of the left and
Mm.
right child, right? So I will say now that if this level of the node is odd, so if the level of this node is odd, then what does it mean? It means that I have to take the exclusive OR operation, right? Otherwise, I have to take the bitwise OR operation only. So let me paste this here. So if this is odd, then what will happen? We have to take the exclusive OR of the left and right child. That is this, right?
Mm.
Otherwise, we have to take just the bitwise OR operation. So in this
Mm.
way, I completed the build function, and let me copy this here because I have to do the same thing in the update function. Because once we update the base level of the segment tree, the internal nodes values will also have to be recalculated, right? So that's why I will say here instead of this statement, this. And now let's look upon this query function. So as I just explained you in the explanation very well, that our required final value of v will always be stored in tree of 0, right? That is this. So it means that we don't have to perform the query because the result is already stored at the top, right? So we can erase this simply. This is not needed here at all. And once I write this, I think I have written the code completely. That is the that is initializing it with the build function, updating the levels like this, and determining whether we have to perform the XOR operation or OR operation. So this is doing the XOR operation, and this is doing our OR operation, right? And once we do this, I just did the same thing in the update function here, right? Because the update function works in the same way as the build function most of the times, and I also erased the query function because this is not needed in this question because the result is already stored at the top, right? And I think I've written the code completely. So let's now run the code and see if this is working fine or not. I think I did a silly mistake here. I wrote it here level of node equal to level of 2 into n plus 1. So this will not be n, this will be node, right? So sorry for this mistake. So this will be node. So now if I run the code, let's see. So as you can see that the results are correct here for this test case. So now if I try to submit it on the platform, let's see if this is completely correct or not.
Mm. 197. Oh, this was a long time ago. How to get this? How to get this problem? How to search a problem? Navigate to filter by tags, keywords. Okay. General equals general bit operations. This is nice. Hmm. Just a minute, I'll be back. Go to black. Okay, I'm back. So we have the problem here. Let me open code forces folder first. Okay, let's first write the code for segment 3. Okay, so 3, 3, 3. Should I just like I cannot class public class segment 3 public segment 3 equal to int n. This is just to initialize my segment 3. 3 equal to new n 4 times n. Do I have to add this here? No, right? Yeah. Hmm. Okay. Now public static void no int build is free. What do we have here? To build a segment tree, what are the things we need? Also initializing 10 this process and we need thing node. Where do they have the tree? We know the start, we know the end. What are the other things we need? That's it, right? Yeah, but we still need to send the start, the end. Yeah, that's it. If start equal to end, then finish it off. initialize this with, okay, this is, hmm, let inside, is this a starting, oh yeah, array of start, you also need the array, yeah, of node equal to array of start. Okay, hmm. Do I even need this? I don't need, okay. And maybe equal to plus image divided by 2. Build S3, we have node, we have start point, we have the end point, and this will be 2 into node plus 1 plus 2 meg plus 1 and then return free of node equal to free of 2 times node plus 1 plus free of 2 times node plus between um we have very we need to update we need int index and int value, right? But here we need to replace it with that value, replace it with that value. So call the return of update util. Now what is this public util? Public int update util. This will have int node, int uh, start, int left, int right, node will be 0, start is 0, int is n minus 1, L, oh, we don't have L, we have int index, int index and value as this. Okay, hmm. If start is greater than index or end is less than index, return 0. right functions. Oh no. Oh, this is for query. Oh, to update the perform of binary research. If start equal to end, then update that node with array and with value array of this. Now, if this is not the case, we find the med by start plus end divide by 2, and then if if index is less than equal to med, index is less than equal to med, call the update detail. This is 2 times node plus 1. Start for med. This is going to say else. Call the update util to 2 times node plus 2, med plus 1, and this. Update. This should be what to update. Hmm. Right. Uh-huh. Yeah. After that, also, oh, this is inside the else. Also, update tree of node with tree of 2 times node plus 1 plus 3 of times node plus 2. And then setting is yes. Okay, this is the update now for public int variable. We need the start point and the end point. Then click on very util. We have the node. We have starting index. We have ending index. We have left and then right. Public int very util int node int start int end int left int right. Okay. If if right is less than start, or left is, or end is less than left, return 0. Otherwise, perform these three queries. Else, else, if if left is less than equal to start, and right, and end is less than equal to right, then return tree of node. Else, find the mid, which is start plus end divided by 2. Then call the query util 2 times node plus 1 with mid. This is end. And then at the end, we will do, yeah, int L equal to this, int R equal to this, return L plus R. Okay, yep. Now, let's read the problem once. Mm, value V for A. The first line contains two integers and an m, contains 2 power n integers. Okay, so we have the scanner system dot in int n equal to c dot next int m equal to c dot next int int size equal to n, then initialize an array of that size. Now for int I equal to 0, I less than n, I plus plus. Hmm, okay. Wait, before that, take the input rfi equal to c dot next string. Now for int I equal to 0 and the setting is plus. We perform the queries. Should I also send or basically update my segment tree here itself by taking the input of like segment tree table the sequence. What just send this and it will first build itself on its own. Okay, can we do that? Hmm. Just send this. Okay. Segment tree t equal to just in this array int array var dot length then call the build segment tree function 0. This is 0. End is in -1 and then the array. Hmm. T equal to new segment tree array. Huh? This is chart. No including instance of type. What does this mean? What is the error in my code? Array. Yeah, this. I want to fill up this error first. Inside the static main, which is illegal in Java unless you instantiate the outer class, but surprisingly a file controls because it's actually not static. Instantiating will be static for correct usage. Okay, so this is static basically. It's just literally Okay, this is this article. So you told me which topic. Look on this. Why did you use this? Okay, so it was unnecessary, literally unnecessary. This is not required at all. Like, does it now? What is this? Why do you write it like this? Just like if the ones that oh, Nice. Also, I think um this should work. Yeah. Look, that's okay. Now what is the error here? Fix the error. I cannot initialize this. Oh, it should be just class. Hmm. So it doesn't have more than one public class or files or both. Okay, okay. Yeah, and this error is no longer there. Uh-huh. Okay. So now we have int p equal to c dot next int b equal to c dot next int p and b. Yeah, wait, wait. P equal to change this, then take out update p and the value is p. Okay. After updating, int b equal to t dot query. Yeah, and we don't send anything. And just print v. Now, for query, we don't need this. Just return tree of 0. For update, yeah, first of all, we need to keep a track of level equal to new int 4 times n. While building, if start equal to end level of that node will be equal to 1. Okay, then level of that node will be equal to level of 2 times node plus 1 plus 1. Oops. Okay. Huh. This makes sense. Now, now, this is while building. Now, while updating, check if level of that node equal to um, node modulo 2 equal to or if it's odd, then perform the XOR operation. If it's even, perform the OR operation. And in query, we don't need any parameters. This is this, and I think we should be good. Hmm. Okay.
Every element initially equal to 0, right? So once I do this, I can start assigning this level each and every element present at the leaf level,
Yes.
that is the base level, equal to 1. And this is of any of its child plus 1 value. So I can say here that the level of this node will be equal to level of any of its children. So let's say level of 2 into n plus 1. So this represents my left child, right? So it's level plus 1. You can write 2 into n plus 2, that is the right level, right child also. That will not matter because the level of both.
That's what I did here. And also this can be bold. Internal plus one. Plus one. Yeah.
So the children will be same. So suppose for this particular level, I want to determine the value of this tree of node. So what does this tree of node will represent? It will represent either the bitwise OR operation or the bitwise OR operation of the left and right child, right? So I will say now that if this level of the node is odd, so
Oh,
if the level of this node is odd, then what does it mean? It means that I have to take the exclusive
while building also we need to check this. Yeah. Mm-hmm. Well, mm, oh, okay. So, this is this is then That's not the file name. Loaded. Hmm. File name does not include the house name. If they differ even by one character, it is same. Yeah, no, do one. Okay, cool. Oops. Submit. Okay, source for the text area. Let's choose the file. Hmm. Hmm. How many test cases or tests does this have? So it went from 25 to 24. Okay, 26. Come on. I don't know what. I'm just going to move on to the next problem.
We are looking for you can do.
Hi everyone. So welcome back to yet another video on this segment 3 series. So today in this video we will be discussing about this interesting problem on code forces that goes by the name Sarija and brackets, and this has been asked in Div 1 round 223, and this problem is rated 2000,
Oh,
right? So let us start.
Sarija and brackets. Okay. Sarija and brackets. Code forces. 2000 rated problem. Dude, this is still running. Sarija has a bracket sequence this, or in other words, a string S of length n, consisting of characters this and this. Sarija needs to answer m queries. Each of them is described by two integers, li, rl. The answer to the ith query is the length of the maximum correct bracket subsequence. Oh, nice. You got it. Okay. Okay, okay. Oh, nice. Mm, okay. Mm, what is this? Unbreakable, unbindable. Sequence. Mm, okay, anyways. Sarija needs to, so this is this. The answer of the ith query is the length of the maximum correct bracket subsequence of sequence. This is helps Sarija answer all queries. Your ith query is the length of the maximum correct bracket subsequence. You can find the definition of subsegments and correct bracket in the notes. A correct bracket, a correct bracket sequence is a bracket sequence that can be transformed into a correct arithmetic expression by inserting characters 1 and plus between the characters of the substring. For example, bracket sequence is this, comma, this are correct. The resulting expression is this, and are not. Okay. For the third query, the word sequence will be this. Fourth query will be okay. Put in the answer to each question on a single line, print the answers in the order they go in the input. Okay, so we have a sequence of brackets. We have ranges from Li to Ri, and what we want to do is need to find the correct bracket sequences. The answer of the query is the length of the maximum correct bracket subsequence of sequence from this to this. Okay. For 1 comma 1, this is one base index. One comma one, 1 comma 1. So it is 0. Obviously, we don't find any sequences. 2 comma 3, so which is 1 comma 2. No, it is 0. 1 comma 2, 1, which is 0. This here we find 2. The answer is 2. The answer to the okay, okay, it is 2. Then 1 comma 2, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is 1, 2, 3, 4, 5. So 5 into 2 is 10. We have 10 here. Then 8, 12, 11, 10, 9, 8, 7. We have 2, which is 4 then. Yes. Okay, I understand the problem, but how can I implement it using segmentary? So basically, what the query will return is um the query should return the number of correct brackets, right? Hmm. So while returning the query, it should return the min value of this bracket and this bracket. And then while outputting, we can multiply it by 2. But let's see, how can we do that? Okay. And while updating, this is an interesting problem. While updating, yeah, oh, however, however, uh-huh. Wait. However, yeah, oh, however, yeah, oh, okay, yeah, oh, okay, yeah, oh, however, however, okay, public class, place, okay. So first we have a string. The first thing that contains the string. So string is equals to say dot next. Oops. Then should I just immediately convert? Oh wait, fade to black. Okay. Add this equals to s dot to cat array. Now, what's the next input? We have m and time equal to see dot next thing. Initialize our segment tree. Segment tree with this. start with class, segment tree, public, void, segment tree. You have that, okay, okay. We have that array. What do we want? Mhm. We have char tree. We have int n. This this should be fine. Tree equals to new int. Oh, no, char 4 times n. Then call the build st. We send the array. We send the node starting index, ending index, and we should be good. Public void build st char error int node int start int end. Okay. If start equal to end, what should be to tree of node equal to array of st- and then return. Then just write this tree of 2 times node plus 1 plus tree of 2 times node plus 2. Can we not do this? We are basically concatenating, right? Cannot convert from int to char. Everything's char. So int made equals to start plus int divide by 2 build st 2 times node plus 1 node plus 1. Wait, why is this wrong? What is wrong in the build st function? Oh, okay, but then what's the problem here? You use n before assigning. Oh my god. Yeah. What is wrong now? Okay. I just need to figure out why this is wrong. Like I understand because this is a character and we are trying to add character and character, which is wrong. But how can I fix that? Is I heard um, the segment tree stores cat, but this complex store. A correct solution for store a single cat per node. Every segment tree node must store number of unmatched, number of unmatched, number of complete. Okay. Oh, matches this, obviously. Then full. Hmm. Open, close, and full. Let's see the
Start now with the
solution.
problem. So the problem reads like this: that Sarija is the name of some girl, and she has a bracket sequence from S1 to Sn. Each of them for an integer m. The output is a given is array of integer. But in this problem, we are given just a string consisting of the alphabetic characters, right? So you don't
Hmm.
have to worry about anything. I will tell you in very detail how this problem will be solved using the segment tree. So let us now come to the blackboard and understand each and everything in very detail. So this is the given example in the question. But before moving ahead, let us first understand the meaning of a subsequence and the meaning of a correct bracket sequence. So how do we define from the starting that if we select elements like we selected this, and this, right? That is, after we selected this 4, we did not select this 6. We directly selected this 8. This is an easy thing. Let us now understand the meaning of correct bracket sequence. So consider this example. So in this example, as you can see that this is a closing bracket and this is also a closing bracket. And for these two closing brackets, there is no opening brackets on the left hand side, right? So
Hmm.
they will remain as it is. But for this opening bracket, this is a closing bracket. And also for this opening bracket, this is a closing bracket. So we can say that this is a correct bracket sequence. And for this, there is no opening bracket. And we can also say that this is in itself a correct bracket sequence and this is also in itself a correct bracket
Hmm.
sequence. And if we combine these two, then we will get this, right? That is of length 4. And hence we can say that for this example, the longest correct bracket sequence is what? It is of the length 4. And this is what the question has asked us to print. That is, for each of the opening brackets, you must have a closing bracket. And since for this opening bracket, this is a closing bracket, so this is a correct bracket sequence. And similarly, since this is an opening bracket and this is a closing bracket, so this is also a correct bracket sequence. So we can say that this four characters together also acts as a correct brackets. But there is one more thing to understand about this correct bracket sequence meaning. So now consider this example. So I have extended the given string a little bit, right? So now if I ask you what are the correct bracket sequences present in this example, so you can say me that okay, this is a correct bracket sequence, this is a correct bracket sequence, this is a correct bracket sequence, and this is a correct bracket sequence, right? So now if I ask you to give me or to answer me the length of the longest correct bracket subsequence in this example, then what will be your answer? So if you have read the problem correctly, then it has
8.
clearly mentioned here that we want to print the length of the maximum correct bracket subsequence. Focus on this word, subsequence. So
Hmm.
that's why if someone asks you to answer the length of the longest bracket subsequence for this example, then it would include this correct bracket sequence, this correct bracket sequence, this correct bracket sequence, as well as this correct
Hmm.
bracket sequence, right? So if I now mark them using the red color, then it would be something like this. So this bracket are the ones that would be the part of the longest correct bracket subsequence. Because if you draw them separately, then it would look something like this, right?
Hmm.
And all of these four individual correct bracket sequence are together forming the longest correct answer would be 8. That is a total of 8 brackets. These
Hmm.
closing brackets will remain as it is. Why? Because for them there is no opening brackets present on its left side. So this will remain as it is, this will remain as it is, this will remain as it is, and this will remain as it is. Only these much of bracket. For this example, the answer would be 8. Now you must have understood the meaning of subsequence and the meaning of correct bracket subsequence, right? So now if I try to explain you the original example, then let us start now. So this is the given sequence or the string, right? So let me mark the indexes of this brackets here. So now I have marked the indexes for this example, and now let us start performing our queries. So in the first query, we want to find the longest correct bracket subsequence for this range. That is starting from the first index and going till the first index only. And also keep in mind one thing, that this L and R are given in one base indexing only, right? So it means that
Mhm. So at the base level, it will be 0. P of node, this will be 0. And as you move ahead, you need to add some logic to calculate it.
this is asking us to answer the query from 1 to 1. So in 0 base terms, we can say that it is actually asking us to answer for 0, comma 0. So if we start from the 0th index and go till the 0th index, then it would include just the first bracket only, that is this bracket, right? If I draw this part of the string separately, then I can say that for the 0 to 0 range, the string would look like this only, right? For this string now, we want to print the longest correct bracket subsequence length.
Mm.
So as clearly visible that this is an opening bracket, and for this opening bracket, there is no closing bracket on its right side,
Okay,
right?
so it is
So I
0.
can say that the length of the longest correct bracket subsequence for this query would be just 0, because this will remain as it is, because there is no
Yep.
closing bracket on its right side. And since this will remain as it is, we do not got any kind of pair of brackets which match with themselves. That is the opening one with the closing one. So that's why it will be 0 for this. And that's why in the output also it is written 0 here. If I try to draw the second part of the query, that is from the first index to the second index, then it would look something like this only, right? And as also clearly visible here, that if we try to match up these brackets with their opposite ones, so for this closing bracket there is no opening bracket, and also for this closing bracket there is no opening bracket in this left part. So it means that they will remain as it is. And since
Mm.
they will remain as it is, we still did not got any kind of correct bracket sequence in this range, that is from 1 to 2. So we can again say that for this query the answer should be 0. And that's why it is again 0, as you can see. So in this way we have performed these two queries, and now we want to move to the third query, that is from
I think you only need the sequences, right? You only need the like correct sequences. You don't need to store the total number of packets, or do you? For the upper level, we need to know the correct sequences as well as the total number of sequences. That is open, close, and correct sequence. So, yeah, open, close, and correct sequence. You need these three parameters. Yeah.
1 to 2. So in 0 base it would be from 0 to 1, right?
Just open, right, open. Array element 3, open equal to 1, close equal to 1. This. Merge this and this. And what does merge do? Node int match when of left dot open, right dot close. Yeah, left dot open, right dot open. Minus the matches. Yeah, and those will be minus the matches. Yes. This makes sense. Why do we subtract the matches? Because in the future levels, the upper levels, we need to exclude the number of matches, and we only want the number of brackets that are unpaired. But now the problem is, what if the brackets are like this? What if the brackets are like this? Now what? How to keep a track of this? This is left close, right open. Left close, left close. Okay, left close. Oh, yeah. We have left open and right close only. And then here we have left close and right close only. Yeah. Hmm, nice. This makes sense. Yes.
right? So now the third query wants us to answer from 0 to 1, that is in this range. So if I try to draw this part here, brackets completely match up to. And if you see also, then 0 is our starting index and 11 is our the last index. So it means that now we have to answer the query for this whole range. So now the query wants us to answer the given string for the whole range, that is from the starting index till the last index. So now if we try to match up the brackets starting from the very start, then it would be something like, we would start from here, and since this is the opening bracket, we would look for the closing bracket on its right side. So for this opening bracket, this is the closing bracket. So this pair is forming a one correct bracket sequence. So let me mark this with green bracket. This is also opening bracket. Left separately here. Then the brackets
Albion on
4, 5, 6, 7, 8, 9, 10. And if we try to look the output, then with green color, 7th index. So now if we try to match the brackets, then closing bracket on its this string, 4th index to 10th index. So this is a closing bracket. Length of this bracket. So this will also bracket. This is my 4. And if this is not, I will actually start adding 2 to our result. String s like this. And if this is not the case, that is the current character is a closing bracket. That is the length of the longest correct bracket subsequence for each and every query's range. So let me erase these things now. So now let us quickly discuss our brute force approach here. We will not give much time to that. So what will be the brute force method? So in the first step, after converting our given values of L and R to 0 based, we would start our iteration from L and we'll go till R. And in the second step, since we have started our iteration from L to R, so on iterating on each index, we will check if the current character is equal to an opening bracket or a closing bracket. So if it is equal to an opening bracket, so what we will do? We will simply push this opening bracket character into the stack data structure, right? And if this is not the case, that is the current character is a closing bracket. So what we want for each closing bracket? We always want a opening bracket to be present or a opening bracket that we have encountered in the past. So we'll check if the stack is not empty. That is, there are still some opening brackets that are remaining. So it means that this opening bracket that is present here at the top of the stack will now make a pair with the closing bracket that we have just encountered now. And since this will form a pair, so it will contribute a 2 result to our top of the stack which is not empty. That is, there are still some opening brackets that are remaining. So
Solve using the stack thing. Yeah.
So it will contribute a 2. So since we have to take the input of a string as the bracket, so I will say string s like this. And once this is done, I have to take the input of the number of queries which is equal to m here like this. So one base index of L like this, and we'll go till exactly till R. But also make sure that before starting the iteration, we have to use a stack, right? So I will say stack of characters. Let's name it as ht. So I will say if my current character, that is s of I, is an opening bracket or a closing bracket. So if this is an opening bracket, so I will say just st.push this opening bracket. And if this is not the case, that is it is a closing bracket. So if this is a closing bracket, then what we want? We want an opening bracket
And
corresponding to this closing
result
bracket.
plus
So
equal
we'll just
to
check
2.
if the side of this stack is empty or not. So
Yeah,
if this
yeah,
is not
yeah.
empty, and what I will say that. So if this is not empty, it means that the opening bracket is already present at the top of the stack, which is not paired yet with any closing bracket. So it means that this closing bracket cannot pair. And after the iteration has been performed completely, I will simply print this result. That is this. Just do a return. And also make sure that after adding 2 to our result, since this opening bracket that is present at the top of the stack is now successfully paired with this closing bracket, so we have to do a pop operation, right? So I will say definitely get a TLE. So I'm not going to submit this, but I have submitted this earlier. So let me show you that. So as you can see, I have submitted this TLE solution here, and I got a TLE on the test 13, right? So this will definitely give a TLE. Why this is giving a TLE? Because if you see the time complexity of this, then as you can see that the total number of queries, that is m, can go up till 25. And for each query, the range that is from L to R can be present between 1 to n. So in the worst case, this m can go up to 25, right? And suppose for each one of those queries, that is all the 25 queries, the range that has been asked to answer is nothing but from the starting index, that is the first index to the last index. And since this range is quite big, because the n value can go up till 26, it means that we have to iterate 26 times for each and every query. So what will be the time complexity total for this? It will be 25 into 26. In the worst, it is equal to 111. So this is an O of n square solution. That is, this is what? This is nothing but O of total number of queries, that is m, into the range of the iteration, that is from L to R. That can be present at the worst case from first to the last index, that is n. So m into n, which is nothing but 111 in the worst case. So that's why it is giving TLE on the 13th test case in the platform. So I hope you have understood the brute force. Now go to the blackboard and understand the optimal approach for this problem. Let us now start discussing our segment tree approach here. Okay, so now let us first revise once how the general structure of the segment tree looks like. So it looks something like this. That is, suppose this is our given array, which consists of currently 8 elements. So we know that each element of this array is initially present at the base level of the segment tree, right? Actually, this segment tree will contain a total of 4 times of the total number of nodes that are present in this array. That is 4 times the total number of elements present in this array. That is 4 into 8 here, which is 32. But for the simplicity purpose, I just have drawn these much number of nodes so that you can understand better. And the remaining nodes will not play much crucial role because they will be 0. So ultimately, our answer will remain same as per the current example. So we know that for a general purpose segment tree, what operations can we do? So it mainly supports 3 operations. That is build, query, and update. So for this example, I have calculated the range sum. That is, if we are asked to query the range sum for any range, then this segment tree will help us in this case, right? So as you can see that first element, that is the 0th index element, is 0, and the first index element is 4. So we can say that the range sum from 0 to 1 is 2 plus 4, that is 6 here. Similarly, if this is 1 and this is 3, then it would be 1 plus 3, that is 4. So since this represents the 0 to 1 range and this represents from 2 to 3 range, it means that the combined node here, that is the parent node of these two nodes, will represent these extreme ranges. That is from 0 to 3, and the summation will be nothing but 6 plus 4. That is, the same thing is done for each and every node node till we reach the root node. So we know that this is the general purpose segment tree and how this is constructed, that is built initially, right? And how using the query we can compute the range sum for any range we want. And also if we want to update, then we know what actually happens on the ground. So suppose we want to update this one. Let's say we want to turn this one equal to index 8. And since it is equal to 7 problem, it will use the segment tree concept, but it will not use this regular segment tree concept, because what we are doing in this general purpose segment tree, we are just storing the summation of ranges in each and every node, right? So each and every node of this segment tree corresponds to a single value, and that value represents nothing but the sum of that range, right? But in the current problem that we are solving, that is region brackets, in this problem we will use the segment tree and we will construct or build the segment tree in the same way, but instead of using or storing a single value in each and every node, we will try to store actually 3 values, and I will tell you very soon what those 3 values will be, and using that we will be computing our answer for each and every query, just like we do it here, right? So let us now go and understand how the actual segment tree for this problem will be constructed. So if you remember, then this was our original sequence given, right? That is the brackets. So now if I want to construct a segment tree based on this, and since this is a string, and I think I'm more comfortable in constructing a segment tree using integer values rather than the characters of the string, right? So what I will say now is I will treat each forward bracket, that is the opening bracket, as 0 and the closing bracket as 1, right? So if I do this, then the new sequence will look something like this, right? That is
Okay. Okay.
I've represented each and every forward bracket as 0 and the backward bracket, that is the closing bracket, as 1. So there should be no problem in understanding this to any one of you, I guess. So this is our current array, right, that we just constructed from the given string of bracket, and now I want to construct a segment tree using this vector, that is this array num. So as I told you before, that in the general purpose segment tree we just store a single value in each and every node of the segment tree, but in this question we will require to store actually 3 values in each and every node. So now as I said that in each node of the segment tree I will store 3 values. So suppose this is a node, it can be any node of the segment tree, right? So let's say that this node represents the range from L to R, right? So for this node I will store 3 values. The first quantity is left unmatched, the second quantity will be right unmatched, and the third quantity will be result of the current range. So let's see what each one of these actually means. So consider that this is our given sequence of bracket, right? So what does this left unmatched mean? So left unmatched means what? That suppose I'm talking about a particular range. So as I said that each one of these 3 quantities will be calculated for a range, right? So for now let us consider some range. Let's say I'm considering this range, right? That is from the first index till the 6th index. So I'm considering this range. So now if anyone will ask you to tell or answer that what is the number of left unmatched for this range, then what will you answer? So this left unmatched means what? It represents the number of bracket, but which type of brackets? It represents the number of opening brackets. So this represents the number of opening brackets, that is these number of brackets which are still not matched with their closing bracket. And similarly, this right unmatched variable will represent the total number of this closing brackets that are still not matched with their corresponding opening bracket. And this result of the current range will, as the name suggests, this will show the maximum possible length of the matching bracket subsequence for a given range. Since here I have considered 1 to 6, so we have to answer for this range, right? So let me tell you once again for those who didn't get it at the first go. So we took 3 variables, and I told you that each node will store these 3 variables, and this will store nothing but the result that the question wanted us to calculate, that is the length of the maximum correct bracket subsequence, right? So there's no problem in this. But what does these 2 is representing? So these are representing nothing but
Okay. When we reach the base case here, yeah, open is 1, close is 1, but match, what about the match? It will be 0 because initially, like, where is this? I, no, okay. Like, understand how this works? Yeah, let's see. Wait a minute. Is it static? It should be a static plus node int. We have opening bracket, we have closing bracket, and we have matches. Or okay, full. Okay, so this is equal to node. We don't even, yeah. With node. Okay, so if this is equal to this, then tree of start, no, tree of node dot open equal to 1, else tree node dot close equal to 1, and then return. This is this. Okay. We call a merge function. Merge function. Public node merge. We have node left. We have node right. Now we calculate int node result equal to new none. Just node result and then return result. We want int matches equal to math dot min of left dot open and right dot lows. These are the number of matches. Result dot full equal to matches. Result dot open equal to left dot open plus right dot open minus matches lows equal this this what, yeah, equal to no. Hmm. Okay, after doing this, what do we want? We have built a segment tree. Now we need to perform our queries. For int I equal to 0, I is less than m, I plus plus. Each character, the second line contains m integers. This then each of the next m line contains a pair of integers. The ith line, okay, so int l equal to sc dot next int r equal to sc dot next int l minus equal to 1. Same goes for r, and then just t dot query is l comma r, and what will we don't even need an update function, right? We don't need a update function. This will return a value. Just simply print that value. Okay. Public void no int query int left int right. Now return query util public int query util. We have the node, we have This is the query, right? We have start, we have end, we have left, and then right. So node 0, 0, and minus 1, left, right. Okay. So if start is if start is greater than right or end is less than left, return 0. Else if left is less than equal to start and right is and end is less than equal to right, we return tree dot node of full, right? Else, what do we return? We calculate the mid, start plus end, divide by 2, perform the query util. This will be 2 into node plus 1, start mid, this plus 2, mid plus 1, end. Int L equal to this, int R equal to this, and return L plus R. All the full, uh, now what is this? Not all the correct, yeah, all the correct brackets from the left subtree, all the correct brackets from the right subtree, and add them up and return to our answer. This should work. Expected output is this, okay. Where what is this? What is this error null pointer exception? Why is there a null one? It's never initialized before use. Oh, no, wait. Didn't I call build st? Or I did call build st here. Why is this not initialized? It is literally called in the constructor. Oh, I need to create new nodes for each index. Oh, yeah, yeah, yeah. Left dot full plus right dot full plus matches. It's completely wrong for this. Why? Oh, yes, 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 yes. Yeah. What I was going to do is just do this, but okay, but I can do this as well. 002 10. This failed. Why can I not do this? Your recursive, your recursive query logic. This is not how packet segmentations. You must merge nodes at full pair counts. Return a node not an agent. Yes, fix it. Hmm, how is this wrong? Wait. No, why? Why should this be node? What is wrong with my logic? Now, why I am saying this is because they have just combined the node and at the end returned result.full into two. But what I am doing is directly calculating the result.full value. Where is this? Yeah, directly calculating the the full value, like accessing the full value and then multiplying it by 2 and then returning it. Why is this wrong? Why is this logic wrong? Yeah, I do want to return an int instead of instead of node. L here, sorry, L here means the number of full brackets or correct brackets. R means the number L means the number of correct brackets in the left subtree. R means number of correct brackets in the right subtree. And then we combine those both and return it into the query util. But I returned this and for partial overlaps, this logic is because bracket subsequences cannot be computed by just adding match pairs from child segments. Okay, just like during build, the essential query result equal to merge all the nodes in the query interval. Your original query did not perform merging. Okay. Okay. Okay, I understand why we merge now. Okay, I see why we merge. Because this subpart can have certain brackets, like certain opening brackets, which are unmatched. But in this subtree, in the right subtree, there can be some brackets, some closing brackets, which are unmatched. Now, we can match these two if we take the range from L to R. So we need to merge. Yeah. This, yeah. Okay. Return no, merge L comma R. Yeah, yeah, yeah. True. No, but yeah, just empty no. Hmm, done. Hmm, hmm,
but the number of left brackets and the right brackets that are currently not used or currently not matched with their opposite pair, right? So if I'm talking about this range that is from 1 to 6, that is this range, then what is the that we just built something like this will help us in computing the answer for each and every query. So as we said that it would be very similar to how we do in a general purpose, don't need to draw that. And whatever nodes are present internally, those are called as internal nodes. So you must be knowing this, right? Okay, so let us now start building our segment tree one by one. So bracket is not from 0 to 0. Why? Answer should be 8 only, right? This is correct. But when we sum this directly, we got 6. So that's why I told you that we cannot sum this directly. It will give us a wrong answer, right? So this 8 is our correct answer. I hope you got how we got 8 here. So one thing, if you have noticed here, that what we did in order to actually combine this result. So if I write here mathematically, then this result was nothing but actually right child's of already. This. So combine the result.
पौष्टिक
फक्त कोलगेट मॅक्स फ्रेश मध्ये
Okay, so hi everyone. So welcome back to yet another super interesting video on the segment tree series. In this video today, we will be discussing about this code forces problem, which was asked in round 271 div 2.
Ant colony. Clearly on test. Okay. Did this code give a really what? Process easily, but Java K. Oh, is on stop. So quickly achieve each node. Reuse nodes, modify mod so it does not allocate new nodes, remove this allocation, void merge, collect 10. Use this. Use buffer reload. Let's see if this avoids a KLE or not. Hmm. Let's just check. Hmm. Mhm. Let's just check if this gives a KLE or not. Wait, let's just check if this passes. Yes, it does. Submit.
And this problem is rated 2100, right? This problem will use the concept of segment tree, and that's why this is present in this series only. The problem goes by the name ant colony. So let us now start the problem. So the problem reads like this: that Mole is hungry again. He found one ant colony consisting of n ants ordered in a row. So we have a total of n number of ants, and each ant has some strength S of I. So in order to make the dinner more interesting, Mole organizes a version of Hunger Games for the ants, and he chooses two numbers L and R, and each pair of ants with indices between L and R inclusively will fight. So when the two ants INJ fight, ant I gets one battle point only if S of I divides S of J, and also J gets
when two ends I and j fight, and I gets one battle point, and if Si divides Sj, also I and j, what?
one battle point only if S of j divides S of I. So after all
Okay. I gets one battle point if Si divides Sj, and j gets one battle point if Sj divides Si.
fights have been finished,
Has been finished, mole
mole makes the
makes.
ranking, and ant I with vi battle points obtained is going to be freed, that is going to be freed from the ant colony if v of I is equal to r minus l. So what does this mean? It means that, in other words, if it took a point in every fight it participated. So
Okay, so let's implement this. The fast reader thing.
after that, mole eats the rest of the ants. And note that there can be many ants. And note that there can be many ants that can be freed. Or it is also possible that no one of them will be freed. So in order to choose
Nice. One 25 MB. Mm. Ant colony. Mole is hungry again. He found one ant colony consisting of n ants ordered in a row. Each ant I from 1 to n has strength Si. In order to make his dinner more interesting, Mole organizes a version of Hunger Games for the ants. He chooses two numbers, L and R. Uses and each pair of ants with indices between L and R inclusively. These will fight. When two ants I and J fight, ant I gets one battle point if Si divides J, and J gets one battle point only if Sj divides Si. After all fights have been finished, Mole makes the ranking. Ant I with VI battle points obtained is going to be freed only if Vi equal to R minus L. What is L? Oh, okay. And I with Vi battle points obtained is going to be freed only if Vi equal to R minus L, okay? Or in other words, only if it took a point In every fight it participated. And if it took a point, after that, mole eats the rest of the ants. Note that there can be many ants real or even none. In order to choose the best sequence, mole gives you T segments L to Li to Ri and asks for each of them how many ants is he going to eat if those ants fight. The first line contains n, which is the size of the ant colony. Okay, int n equal to a seed of experiment. Next second line contains the strength. Okay, int array equal to new int one, int p equal to string. Oops. While this is true, we want L and R int L equal to C dot next string, R equal to C dot next string, L minus equal to 1, R minus equal to 1. Now, what do we do? We first initialize our segment tree, equal to new segment tree T dot T dot query interval and SOut. I think we should be good enough. Static last segment public segment tree int array int tree and then this dot equals to array dot length tree equal to new int 4 times n and then value stay array int this and minus public void value stay int array int start node int start and if start equal to end, then initialize this node with array of start. Otherwise, just find the mid and call this 2 into node plus 1 is to be this. Med plus 1 and 3 of node equals to 3 of 2 times node plus 1 plus 3 of 2 times node plus 1. Okay, now we obviously return from here. More organizes a version of one. He chooses. Everything guesses between when two ants I and J fight, and I gets one battle point only if SI divides SJ. Okay, so this is the base case, right? SI will always divide SI. So what will be the battle point? It will be 1. This will be equal to 1, right? And then this will be, we don't know if SI divides SJ or not.
Choose the best sequence. Mole gives you the T segments. How many ants is ants that this mole will eat from this segment alike to I? Ants minus the number of ants that is freed. So this is the we want to fire as follows, like 1, 3, 2, 4, 2, and then we are given a total of 4 queries. This is the first query, this is the second, this is the third, and this is the fourth. And for each of these queries, we want to find that in this range, how many ants will be eaten by this person. That is total number of ants minus the number of ants that is freed. So this is the required output here, double 4 and double 1. And here the given example is explained completely. This is the complete problem statement, and
Let's understand this. In the first, there's battle points for each and are p equal to 1 to 5. So 0, 1, 2, 3, 4. Okay. V equal to 4, what? 40202. So and number 1 is freed. Mole eats the ants 2, 3, 4, 5. 2, 2, 3, 4. Okay, mole 1. So this. Okay, so this number SI divides SJ. SI divides SJ. So it obviously divides this, this, and this. So the answer is 4. And the query is like 5 minus 1 is equal to 4. So yeah, this guy is freed. Now let's see. For 3 cannot divide this, cannot divide this. So this is 0. This is 0. Then for 2, it cannot divide this, It can't divide this. It can't divide this. So this is equals to 2. Okay. So we can check if this number divides this, then increment the value of v for this with 1. Then if this, check if check if check if this can be divided by this, then check if this can be divided by this. Again, f- check if this can be divided by this, and this can be divided by this. This. So we don't need to, when we reach here, we don't need to check for this. We can simply check for the next element. Yeah. So we can check, basically calculate this in O of n in one pass. But how to do it efficiently? Because if all of these queries are from 1 to 5, then we are screwed. How can I update this efficiently? Oh.
And let us now go to the blackboard and understand how these each of the outputs are coming for each of these query, and then we learn that ants, and then we are given 4 queries and the output for right, that is the array that represents the strength of for each of the ants present in the ant colony. What the question wants us to print? It wants us to print the number of ants, that is the number of ants that mole will eat from the given segment. That is, we want to print the number of ants that will be eaten, right? So what will be the value of this quantity? So it will be equal to the total number of ants present in the given segment, that is from L to R. So total ants present in this segment, that is present from L to R, minus the number of ants that will be freed. As of now, our concern is not to how these ants will be freed, right? So since we want to print the number of ants that will be eaten by this person mole, so the number of ants eaten by this person will be equal to the total number of ants present in the given segment minus the number of ants that will
Hmm.
escape the ant colony, right? So this is a common sense thing. So if you want to print this, then we want to know these two quantities value, right? And since the total number of ants present in this range is nothing but r minus l plus 1, isn't it?
Hmm.
For example, if I want to know the total number of ants present between 0 elements from, if we want to calculate this term, then it will be equal to this. Our only task in this problem is to calculate this thing, that is the number of ants that will be freed, that is the number of ants that will escape the ant colony. So if you have read the question correctly, then here the definition of freed is written, like how the ant will be freed, right? So let us see now what is the procedure for an ant to get freed is. So as you can read here that an ant is going to be freed if and only if v of I is equal to r minus l, or in other
Hmm.
words, if strength is 2. So if you want this ant to get freed, then what does the definition in the question says? It says that if it is equal to a particular ant, that's condition, the condition,
Okay.
and then what
I'm skipping this because I understood the problem statement.
lost some 5
I need to understand like how to approach this solution.
for, let's say, the first ant. That is the ant that is having the strength of 1. So let us do the same thing here again. So now we want to make this ant free from the ant colony. So if this ant wants to get freed, then what is the condition? Its condition is that the total number of battle points should be equal to the total number of other ants, that is 4 here. So if it is able to gain a total of plus 4 battle points, then it will be freed from the ant colony, and thus it will not be eaten by the person. So let us start the fight for this ant with each and every ant present in the ant colony.
Wait. My um, sorry. Have a wait, what? There is a lag. Wait, crude. This efficiently.
And let us now go to the blackboard and understand how these each of the outputs are coming for each of these query, and then we'll learn that ants, and then we
Okay,
are
okay. Okay. Hmm.
So suppose the fight started between these two. So now we want this ant to win, right? So if this ant has to win, then what is the condition? The condition is that this s of 0 should be able to divide this s of 1. Say that
Hmm.
this will plus 1 battle point, able to dominate this 2 should be as we did previously, will not be able to redeem any battle not afraid, then the condition is that one warrior
Okay, so we just need to find a number like which is not divided by this number. If that is true, then that number will be eaten. That is for sure. Why? Because if this divides this, but but this number cannot divide this, so this will be eaten. This number will be eaten.
3 should be equal to 0. But we know that this is obviously not true. 3 cannot divide 1. So it means that this will never be able to gain a battle point.
Okay, so if it's eaten, set the value to 1. If it's not eaten, set the value to 0. So when we call the query update, when we call the query function, we just add the number of ones from that range. Okay, this. Mm, okay, but I understand what I have to do, but how do I implement this?
Point with this ant, right?
How do I implement
So
this?
this lost the fight, and since this ant lost the fight, that it will be ants in the array,
Hmm.
and whatever happened at the last, that is the state here. Only 4, that is we are talking about the whole range, and that means that we want to query the whole range only. That is from 0 to 4 in base 0 base terms, and the output for this query is 4 only, and this is what we just got. That is 5 minus 1. So total number of ants minus the number of ants that will be freed, which is 1 here only. So 4. So in this way we discussed the first query successfully and got our respective result 4. Let us now move to the second query for this example. So the second query is from 2 to 5. That is in this range, right? So if I draw it separately here, that is we want to now query for this range. That is number of ants that will be freed in this range, in the same fashion as we did before. So let us start checking for each of these ants one by one. So if this first ant fights with the second ant here, so it means that it wants to win over this ant, right? That is, it wants to divide this. So is it possible? Let's see. That is, we want this to happen, but this is not possible, we know. So it means that it will not be able to win with this, and thus will not gain a battle point. And since it lost a fight, even with just one ant in its range, so it means that it will never be able to escape the ant colony and will not be freed. So I can give it a tag like E, that is, it will be eaten. Now let us move to this ant. So now this ant will want to fight with this, this, and this. So if it fight with this, then it means that this 2 wants to divide this 3, that is this. And again, this is not possible. And since this is not possible, and since it lost a fight, it will again never be freed, and thus it will also be eaten. So E. Now let us talk about this ant here, which has a strength of 4. So now this ant wants to fight with this, this, and this. So now suppose this ant is actually fighting with this ant, so it wants to divide this, that is 3 by 4, which is not possible. So again, this ant will just be eaten. And now if you talk about this ant, then it will fight with this ant, this, and this. If it wants to win the match, that is wants to get freed, then it has to dominate each of these 3 matches, right? And to dominate, it means that this 2 has to divide this 3, this 2, and this 3 match is 4 only. When the value will not be freed, as well as the largest element of that range exists in this range, right? Because the minimum value present in the fight is able to the value of that range, right? It's common sense, right? Because if this x is 4, and what is the smallest? It is 1, right? So if I write here, we will not what we want. We want that value to divide that other's ant value, right? So if this wants so
Wait, what is
now if
this?
you want to answer the query, then I will say the total number of ants present in this range, which output is 1 for this. So in this way, we discussed each and every query is 1, that is 1. And now if you want to answer the query, then I will say the total number of ants present in this range, which is 2, minus the number of ants that will be freed, which is 1. So 2 minus 1, that is 1. And in the output also, it's clearly written 1. So that's why output is 1 for this. So in this way, we discussed each and every query in detail and saw how the outputs are coming each time for each and every query, right? So by now, you all must have understood how this formula is working. So this is just calculating the total number of elements present in this range minus the number of ants that will be freed. And an ant will only be freed if it is able to win the fight with each and every other ant present in that range. And in order to win with the other ant, we want that value to divide that other's ant value, right? So if this wants to win with this, then this 4 should be able to only, right? So now what we want? We want to find an element present in this range that will be capable of dividing each and every element present in this range. So an element will always be able to divide itself, right? So we will not talk about that. I want that element to also divide each and every other remaining element present in that range. So if you look very, very closely, then you will realize that suppose, so just tell me one thing, that what is the largest value present in this range? It is 4. And what is the smallest? It is 1, right? So if I write here in the separately, then my minimum value here is this 1 and my maximum value present is this 4. So I want to find the element that should be present in this range. That should be capable of dividing this 1 as well as this 4, right? So what does this mean directly? I want the element that should be present in this range. That should be capable of dividing this 1 as well as this 4 present is the smallest, it is 1, right? So if I write here in the spread, suppose, so just tell me one thing, that what is the largest value present in this range? It is 4. And what is the smallest? It is 1, right? So if I write here in the separately, then my minimum value here is this 1 and my maximum value present is this 4. So I want to find the element that should be present in this range. That should be capable of dividing this 1 as well as this 4, right? So what does this mean directly? I want to find an element that should be able to divide this 1 and I also want to find an element that should be able to divide this 4, right? So suppose the value of that element, let's say, is x. That is, I am saying that 1 modulo x is equal to 0 and my 4 modulo x should also be equal to 0. So what does this mean? This means that since we want to find the element x such that it will be able to divide the smallest element of that range as well as the largest element of that range, so this value of x can never be greater than this 1, because let's say if the value of this x is 2, let's suppose. So is this ever possible? Never. So this x can never say if the value of this x is 2, let's suppose. So is this ever possible? Never. So this x can never be greater than this 1. So this x will always be less than or equal to the smallest value of that range, right? It's common sense, right? Because if this x is somehow greater than the smallest value, then it means that for that range in which the smallest is, right? Because if this x is somehow greater than the smallest value, then it means that for that range in which the smallest is 1 here and the largest is 4, then that selected element will never be able to divide the smallest element. And if it is not able to divide the smallest element at least, then that ant will not be freed and thus it will be eaten. But we want to calculate those ants that will be freed, right? So that's why if you want to select this x, we'll make sure that this x should always be less than or equal to the minimum element present in that range. And I just now told you why this cannot be greater than the minimum element, because if it is greater than the minimum element, then that x will never be able to divide the smallest element and thus that ant will never be freed. So now one thing is clear here. Let me write this fact here in the note, that our x will always be less than or equal to the minimum element. So keep this in mind. We will use this fact later. And since now we are just talking about this whole range here, so now we want to select an element that is x which is less than or equal to the minimum element. So what is the minimum element here? It is 1, which is present here. So this x can either be equal to 1 or less than 1. But there is no element which is less than 1 present in this range. Is there any element less than 1 present here? Obviously not. Only this is present, right? So it means that only this ant has some possibility that it will be able to divide each and every other element, because the other remaining ants will never be able to divide this. Why? Because they are greater than this element, right? So if they want to divide this, then they clearly have to be less than or equal to this. But this, since these 4 are actually greater than, strictly greater than this element, so these 4 will never be able to win the fight with this ant, and thus they will never be freed, right? So only this ant now has the possibility to win over the fight with each and every other ant. That is the minimum element of that range, right? So this x has to be less than or equal to the minimum element. And since for a given range, by using common sense, we know that for a given range, only one integer can be the minimum value, right? We cannot say that this 1 is also minimum and this 2 is also minimum. For a given range, a unique value will be the minimum. And obviously this 1 can be present here also multiple times. We will discuss this very soon, right? So for a given range, only one value will be the minimum element. And since only one value will be the minimum element and our possibilities for x is less than or equal to minimum, and we know that this less value will not exist in this range, right? Because the minimum value present in the most minimum value present in the range here is 1, and there is no element present less than 1, right? So the only possibility that we are left for choosing this x is this equal to, that is the minimum value only. So our concern is not with this less than mini, but this equal to mini, right? Which is 1 here. So we will focus on this 1 only, that is this element, and will not any value present less than this. And let me explain you the same thing again with a different example, and it will become very clear to you what I am trying to say. So now suppose I am talking about this whole range, which consists of the strength like 4, 8, 12 and 16, right? So now what is the minimum in this range? The minimum is 4 and the maximum is 16. But we don't have to do anything with the 16, that is the maximum element we just saw. Our only concern is this minimum element, because whatever value of x we will choose, it will always be less than or equal to mini only, right? And since for a given range there can only be a one minimum value, which is 4 here, right? So our x should be less than or equal to 4, and since there is no value less than 4 present in this range, so we don't have to do anything with this less sign. Our only important thing here is this equal to, that is this element, right? So now what I'm saying is I want to find those elements that should be capable of dividing each and every element present in this range. So what can be the possible elements? The possible elements can be 1, 2 and this 4 because this 1 will be able to divide each and every element here, right? Similarly, this 2 will be able to divide each and every element. And in the same way, this 4 will also be able to divide each and every element. So these are our possibilities of choosing the x, right? So these are our possible x, which is obviously less than or equal to 4 here because all of these three, that is 1 to 4, are less than or equal to 4. These are able to divide each other to dividing that is present in this range, so we don't have to do anything with this less sign. Our only important thing here is this equal to, that is this element, right? So now what I'm saying is, I want to find those elements that should be capable of dividing each and every element present in this range. So what can be the possible elements? The possible elements can be 1, 2 and this 4 because this 1 will be able to divide each and every element here, right? Similarly, this 2 will be able to divide each and every element. And in the same way, this 4 will also this 1 capable to, that is this element, right? So now what I'm saying is, I want to find those elements that should be capable of dividing each and every element present in this range. So what can be the possible elements? The possible elements can be 1, 2 and this 4 because this 1 will be able to divide each and every element here, right? Similarly, this 2 will be able to divide possibilities of choosing the x, right? So these are our possible x, which is obviously less than or equal to 4 here because all these two values will be of no use this range index, right? So that's why. So let me write here. So these are nothing but the common divisors, right? So these are the common divisors for each and every element from L to R inclusive, right? So since we are talking about this complete range that is from 0 to 3, so these 1, 2 and 4 are the common divisors for each and every element in this range.
Okay.
And what is this? So this is nothing but greatest common divisor in this range. That is our GCD of this range, right? So these are our common divisors, and since this is the greatest of all of them, so this is our GCD of that range. And our concern was only this GCD, right? As I told you, as I explained you just in very, very detail. So let me tell you again what has happened actually. So we wanted to find some element in this range that should be able to divide each and every other element, and we saw that that value of element must be less than or equal to the minimum value of that range, because if we choose any other element other than the minimum element, it will not win the fight. That's so since here the minimum element was 4, I can say that this value of x has to be less than or equal to 4, and we saw that that to 4, and since and this less than factor, that is these two about this equal to nothing but the minimum element only, right? So the GCD is equal to the minimum element, and since the GCD here is equal to the minimum element, it means that there is some element present in this range which is the minimum of that range, and that element is also capable of dividing each and every other element present in that range. Let me speak once more. So what I'm saying is, we try to find the greatest common divisor of that range, right? And that element was equal to the minimum value of that range. It means that in this range there is some value which is present, that is the minimum value, and it is able to divide each and every element, which is evident from here, that is the GCD. So I can draw my second conclusion here very well, that if my GCD of a range from L to R is equal to the minimum value of that range, then that element that has this minimum value will definitely be freed and will not be eaten. So in this way, we have derived our mathematical formula that we will use in order to compute the answer for each and every query. That is, GCD of this range L to R inclusive should be equal to the very element, each and every other element present in that range. Let me speak once more. So what I'm saying is, we try to find the greatest common divisor of that range, right? And that element was equal to the minimum value of that range. It means that in this range there is some value which is present, that is the minimum value, and it is able to divide each and every element, which is evident from here, that is the GCD. So I can draw my second conclusion here very well, that if my GCD of a range from L to R is equal to the minimum value of that range, then that element that has this minimum value will definitely be freed and will not be eaten. So in this way, we have derived our mathematical formula that we will use in order to compute the answer for each and every query. That is, GCD of this range L to R inclusive should be equal to this minimum value of that range. And the last thing that I think I should tell you is, let's say instead of this 12 here, we had this 4 only, right? So since 4 is the minimum element and this 4 is able to divide 4 itself, 8 also, this 4 also, and this 16 also, so this ant will be freed, right? And similarly, this will also be freed because its value is also 4. So I can say that in this range, actually 2 ants will be freed now. That is the number of elements, that is the number of minimum elements that are present in this range. Since 4 is the minimum of this range and it is present in 2 different indexes, so I can say the number of ants that will be freed for this range, that the number of ants that will be freed here now will be 2 in this case. Because the minimum element is actually present at 2 different indexes. So that's why it will be able to divide each and every other element also. So I think I have explained you most of the things here by now. It is not that difficult to understand, but it is important actually, right? How we are using the terms of greatest common divisor and the minimum element and the count of minimum element in order to compute the answer for each and every query. So now I think we should move to the next stage of the solution. So now what we want to calculate the GCD of that range. Similarly, we also want to calculate the minimum value of that range, and we also want to calculate the number of such minimum elements in that range. And if we are able to calculate these 3 terms for a given range, that is the GCD, the minimum, and the count of minimum, then we should be able to answer each and every query, right? So this is the crux of the problem that I just explained you. You just have to find the GCD and also have to find the
Let's see. What is GCD? What's the difference between GCD and LCM? Now, I do know what GCD and LCM is. It's just that I just want to clarify certain things. Mhm. Multiplication of common factors. 36, 60, 2, 2, 3. GCD is 12. Greatest common divisor. And then for LCM, least common multiple. Highest common multiple. This will be 8. This will be 8, 16, and 48. Well, difference. Two. Okay, GCD means the greatest number that will divide both of these numbers. And LCM is the immediate next number is common multiple. So the common multiple of both these numbers. Okay, so we want to find the GCD of these numbers.
minimum element
Okay,
and the count. This is the minimum.
GCD of these numbers. Greatest common divisor of these numbers should be equal to 4. See, 4, 8, 16, 4, 1, 2 is a hmm. Greatest common divisor should be equal to the minimum number. Yeah.
count of minimum, then we should be able to answer each and every query, right? So this is the crux of the problem that I just explained you. You just have to find the GCD and also have to find the minimum element and the count of that minimum element in that range. So if the GCD is equal to the minimum element, then it means that there is some element present in that range which will be able to win with each and every other element that is dominate, and put it here, and we can calculate, and we simultaneously calculate all of these three things for each and every node, and hence merge the results each and every time. We should be able to answer our query, right? So let us now build our segment tree completely from the bottom to the top and see how it will be built, and then we will see how we will answer each and every query. So let us now start building our segment tree from the very bottom till the top. So here I have drawn the general structure, and as I have told you before that each
We need three parameters: minimum, count of minimum, and GCD.
node will consist of three informations, that is the minimum of that range, and combine the results for the first time for 2, right? It was 2. So I can say
Wait,
the GCD of, what is the GCD of this one in this range, right? So that's why I will write here 1. How many these ones are present? It was 1, if you remember, right? So we know that the strength of the ant in the 0th index was 1, if you remember, right? So this is the only element present in this range, isn't it? So this element will be the minimum in itself, right? So the minimum element present in this range will be this 1 only. And how many these ones are present? It is just 1. So I can say that the value of this minimum and count here will be just 1, right? So I will write here that this is 1 and this is 1. And what is the GCD in this range?
minimum and count is 1. GCD is 1,
So
obviously.
that is, what is the GCD of this? So it will be equal to 1 only, right? Because if we take any element greater than 1, then it will never be able to divide this 1. So the element that can divide this 1, and it has to be the greatest, so it will be equal to itself, right? So that's why I will write here 1. So in this way, we have filled the information for this node. So after we have filled the information for the left child, let us now move to the right child for this parent node. So let us do the same thing here once again. So now if you remember, then what was the value of the strength of the ant present in the first
3.
index? So it was this 3 only, right? It was this 3. So I can say here in the same way that the minimum will be nothing but 3 only, and the count will be 1, and the GCD will be 3 only.
Why is the count 1? Yeah, count of the minimum is
And I
3.
just explained you how these three values will be calculated. So once we have found the result, that is we have filled the nodes for the left and the right child, what we will do now? We will combine the results of these two into this. So let us do the same thing here. So what I am saying now is, what is the minimum for this range? That is, now we want to calculate the minimum for this range. So it will be nothing but the minimum value present in this range and the minimum value present in this range. So I can say
Remember the minimum
it like
is
minimum of the value found in this range and the minimum we found in this range. So the minimum of both of them will ultimately the
yes.
minimum this range, right? So that's why I can say now that the minimum value of this range will be the minimum of this and this, which is 1 only, right? So the minimum of 1 and 3 is 1. So I will write here 1. And
Count will be 1 only.
how many of these ones are present? So the number of ones that are present in this range will be equal to the number of ones present in this range plus the number of ones present in this range. And we saw that this one is only present in this range and its count was 1. So I can say here that the number of ones for this range also will be 1. And once we have done this, we now want to compute the GCD of this range. So what will be the GCD of this range? It will be nothing but the GCD of the left
1.
child and the right. So since the GCD of the left child is 1 and the GCD of this right child is 3 only here, so what is the GCD of this 1 and 3? So the GCD of this 1 and 3, that is the greatest common divisor, is nothing but 1 only, right? So I will write here 1. So in this way I have combined the results for the first time for this node here, right? And now let us fill the information for this base level leaf node. So this is our second index, right? And what is the value of the ant present in the second index? So it is equal to this 2, right? So it is equal to 2.
Complex and int GCD int A on int B. Return A equal to 0. Return 0 else GCD of A modulus A is this code for GCD content. Oh, A modulo B. Okay. Immorality. Should be A. If B equal to 0, you can A otherwise do this. Okay. Yeah, we'll fix that later.
So keep this in mind. So since this is equal to 2, I can say that the minimum in this range is 2 and its count is 1 and the GCDs will also be 2. And once we have found
So 2, comma 2, 0, 1, 2. Yes, 4. Yeah.
this, what we want to combine the result of these two nodes into this, right?
Hmm.
So
So minimum, wait. Minimum is 2. Here minimum will be 1. Count will be 1 only. And GCD will be 1 again.
now again, if we do the same thing, then what will be the minimum in this range? It will be the minimum of this range and the minimum of this range, right?
Hmm.
So since the minimum in this range is 1, and what is the count of this 1 in the left child? It is 1. So I will write here 1. So I will write here 1. And what is the count of this 1 in this range? So since we have got this 1 from this left child only and not on the right child, so what is the count of this 1 in the left child? It is 1. So I will write here 1. And ultimately, what will be the GCD of the combined range? So it will be nothing but the GCD of left and right. That is the GCD of 1 and 2, which is nothing but 1 here only, right? So I will write 1 again. And in this way, now we have combined the result of these two childs into this. And in this way, we have completely traveled the left part and have filled the information, right? And now it will travel to the right part and will combine the information of these two into x. The value of the line will be the minimum of this and this. That is the minimum of 4 and 2, which is 2 here. So I will write 2. And take the count of these two from here, which is 1 here. So I will write 1. And ultimately, what is the GCD? So it will be the GCD of the left and the right part. That is the GCD of 4 and 2, which is nothing but 2 only. So I will write 2. And in this way, we have done our most of the work. We just need to combine now the results of these two childs into this. Let us do that quickly. So now we want to find the minimum for this. And what is the count? So this count is 1 only, right? So nodes, but only those nodes that will actually, right, the actual segment tree actually consists of 4 n nodes, right? So in this case, 4 into 5, that is 20 nodes. So a total of 20 nodes should be present in the segment tree, but I have drawn actually not all the nodes, but only those nodes that will actually contribute to our answer, because the other nodes are sufficient to answer. I think now we can start answering our queries, right? Let us start from this query. So the first query is from 1 to 5 and the result expected is 4, right? But since we are talking about it in 0-based terms only, so this is actually my 0th index and this is actually my 4th index, isn't it? So now I want to query for this range, that is from 0 to 4. So let us now start our query function from the root node. So if you see the range of this root node, then what is this? This is 0 to 4. And what we want to query? We want to query also for 0 to 4. That is, this lies completely in this, isn't it? So it means that we don't have to go any further, because whatever the result we want is already stored here. So we'll just return that. So what we wanted, if you remember, so we just wanted the GCD of this range and the minimum value of this range. Here, what I want the GCD of that range and the minimum value of that range. And if they are equal, then we just have to calculate the number of such minimum values, right? So here, if you see, then what is the GCD? The GCD is 1. And what is the minimum? The minimum is also 1. So since they are equal, we just want to calculate the number of such minimums. And what is this equal to? It is equal to this 1 only. That is the count of this 1 is also 1. So that's why I can say that the number of ants freed will be 1 now. And what we wanted to do, we just wanted to subtract with the total number of elements present in this range. And how many elements are present total? These are 5. And we have to subtract this 1, which is 4 only. So that's why the output for the first query was 4, if you remember. Right. Now let us move to the second query, that is from 2 to 5. So now we want to answer from 2 to 5. That is in 0-based terms from 1 to 4. Now let us start from the root node again. So this 0, 4 lies partially in this 1, 4. So if my 0 is here and my 4 is here, then my 1 will be here, right? So this 0, 4 or this 1, 4
2, 5.
lies partially in my 4 is here, then my 1 will be here. Lies partially in this 1, 4.
1, 4.
So if my 0 is here and my 4 is here, then my 1 will be here, right? So this 0, 4 or this 1, 4 lies partially in each other. So it means that I have to explore both the directions. But first I'll go into the left part. So suppose now I'm standing at this node. What is this equal to? This is equal to 0, 2 range, which again lies partially. So I will again divert in both the directions. And now I'm here. And since this again lies partially, it means that I will go here and then here. But if I go in this direction, then this will lie completely outside of this range. That is the contribution of this. And this 1 to 1 lies completely in this 1 to 4. It means that the contribution for this node is okay. That is, we want this, right? So we have this currently. Keep this in mind. And once we have explored this also, it will backtrack and it will explore this part now. And it will see that this is 2 comma 2, which again lies completely inside this. So we again have this in our hand, right? So let us combine these two here and write the result here. So if I do this, then what will be my minimum? So my minimum
Okay, so we have to merge, call the merge function again,
will be the minimum of this part and the minimum of this part, which is
which is 2.
2, right? So I can say the minimum is 2. And what is the count of this minimum? So it is
Count of the minimum is 1.
equal to 1 only. So 1. And what is the GCD? That is, we want to calculate the GCD of this 3 and 2, which is nothing but 1 only, because neither this 2 can divide this 3 nor this 3 can divide this 2. So 1 is the greatest common divisor that can divide them both. So 1. So in this way we explored the left part, and now let us explore the right part. So now we are standing at this node, which is from 3 to 4, and this 3 to 4 lies completely in this query range, right? So it means that we don't have to go any further. We will just return the result of this node, which is these 3 values. So now what we want to do ultimately, we just have to combine these 2 into this node. And if we do this, let us do that here. So what will be the minimum? The minimum will be minimum of 2 and 2, which is 2. And what will be my count of this
Yes, will be 2.
minimum? So this is interesting here. Please see. So what is this minimum here? This is 2, right? And this 2 is actually present here also, and this 2 is actually present here also. So it means that the contribution for this 2 in this count will come from both, that is the left part and the right part, right? So since the number of 2's present in this left part is 1 and the number of 2's present in this part is also 1, so I can say that the total number of 2's present in this range will be equal to this 1 plus 1, that is 2. So 2 here. And the GCD value, so the GCD will be the GCD of this 1 and 2,
1.
which is 1 only. So this is my ultimate result for this query.
And now, since GCD GCD is less than the minimum value.
That is this query. And if you remember, then what we want to do next, we just wanted to check if the GCD of this range is equal to the minimum value of this range. So what is the GCD value of this range? The GCD is 1. And what is the minimum of this range? The minimum is 2. So clearly this 1 is not equal to 2. It means that if I show you in the array, it means that in this part of the array that we are pairing just now, we will never get any element that will be able to divide each and every other element. And it is true also, because if you see, then in this part we have no such element that will actually divide each and every other element, because this 3 will never be able to divide this 2. Similarly, this 2 will never be able to divide this 3. This 4 will never be able to divide this 3. That will be freed in this case will be 0, right? So the number of ants freed is 0. And if it is equal to 0 and the total number of elements present in this range is equal to 4, so the number of ants freed is 0. And if it is equal to 0, and if you see also in the output also, then it's 4 only. So I hope you can do this easily. So now I think I have explained you each and everything in very detail, and how greatest common divisor you say here. Then in the input we first have to take the number of this, what I told you, we just have to print the total number of elements present in this range, that is r minus l plus the query. So I will say t dot query from this l to r, and just give an ender like this, right? And
Just value is this r minus l plus 1. That's the value. Minus this. This is three ants. Three ants. Static class node. This node will contain 3 things. First is the minimum, the count, and then GCD. Node this A of node if static will equal to end, then this dot min will be equal to 1, count will be equal to 1, and GCD will be that number. GCD count, and this will be equal to array of stuff, and then return. Now for this, You need to write the merge function. Merge these two. Now, what does the merge function do? Public. Where should I write them? Inside this class. Inside this public node merge equal to no public host. What public oh. So yeah, before that we need to create a new node, right? Create tree of node. Now, what will this have? We also need to send a temp. Yeah, node temp equal to new node temp. This node result, then node left, node right. Return result. But before that, we need to count the minimum. Result dot min equal to node left math dot minimum of left dot min and right dot min. Result dot count equal to if left dot no, if left dot min equal to right dot min. If this is true, then just then increase the count by one, right? No, then add both of them. Add both the values. Left dot count plus right dot count. Otherwise, if left dot min is less than right dot min, then what should you do? Return the value of left dot count. Otherwise, return the value of right dot count. Yeah. Then result dot GCD will be equal to GCD of left dot GCD value and right dot GCD value. Yeah. And then at the end, return the result. This. Now let's write a code for query function public void int query int l left int right. We call the query util public int public node query util node result equal to this return result dot count. We have the starting node int node. We have int start int end int. This is the query, right? So left int right. We have 0 comma 0 comma n minus 1. What is left? We have left here, we have right here. If left, if start is greater than right or end is less than left, return 0. Else if left is this and end is basically these are within the range. And if this is within the range, return tree of node. Else find the mid start plus n divided by 2, then query util start will be this mid query util mid plus 1 till end int l equal to this int r equal to this, and then at the end return l comma r. Yeah, this is node. Return merge. Yeah, merge. You cannot store that value, right? It will literally opaque the tree. What did I return? Oh. Yeah, this variable as well. Okay, yeah, we should be good. Uh, should I just write a for loop? But it doesn't make sense. I mean, it should not change anything. Int I equal to 0 I less than 3. Is this the problem? Okay, let's leave it like this. What is wrong in my code? How is this wrong? That is never initial. How? Let's say dot close. Rearrange n integers into array. Oh my god. Orient. Nice. Array of I equal to 0 means this should be okay. At least I got some result though. Why? Oh, minimum will be that will be array of start. Count will be 1, GCD will be. Yeah. For empty ranges corrupts merge logic. 4432 returns count of minimum value. Um, it result of this. Then do this. Then do resolve. Otherwise, do this. Yeah. Check. We at the end we need to check. Mhm. If field ans dot gc equal to field ans dot minimum value dot count else r minus l plus. Yeah, arrays till all zeros. Mhm. The segment is built before what? No, I have taken the input and then built. The- Yeah, I have done this. Yeah, what is this? It's returning for empty ranges corrupts merge logic. If it's out of range, what should we do? When is zero, count as zero. Then why didn't it corrupt this? Mhm. Node neutral equal to new node neutral dot min integer save neutral dot count is 0, so dot CD is equal to 0, and then return neutral. This passes, no it doesn't. Obvious. Return what did you do? That is literally the same thing. But let's still say if it passes, that's literally same, yeah. It doesn't matter. It's not good. Let's say, oh, did I not do? Oh, okay. 2 into naught plus 1. Okay, 2 into naught plus 2. Okay, I see. Yeah, so why can I not return new node here? I should be able to. Why do I need to return this neutral thing?
After doing this, just give a return because it's a void function. So now let me declare the segment tree here. So I will name it as t only. So let me declare the structure here like this function, right?
What is this?
So what we have to do, we have to combine the results of the left and the right part, right?
Yes.
So I will say merge the results of the left and the right part like
Hmm.
this. So what is my left part? Left
Uh-huh.
part, that is the left child, which is equal to nothing but 2 into node plus 1. Sorry, tree of 2 into node plus 1, right? So tree of 2 into node plus 1, this is my left child, and this is my right child, that is tree of 2 into node plus 2. So the left and the right part will be merged like this. But before writing this merge function now, let us actually fill the base case properly here. So if you remember, then what we used to do in the base case, we used to assign 3 values, that is tree of itself, right? So that is case will be written, and once I have written the base case, I think I think we should now write the merge function here. So it will be of the type node only, right? And the parameter names that will give to it like L for the left, make a node for temporary
This will be node L and this will be node R.
basis, and will assign initial values like I will say, let's say 0, 0, 0 only, right? Because these 3 values will shouldn't be filled with their actual values. So now what I'm saying is we want to combine the results of the left and the right part here. First, let us combine the GCD for both of the left and the right child into this. I will say that this temp.gcd will be equal to nothing but the GCD value for the left and the right part, that is L.gcd, and sorry for this, and once we have calculated the GCD, it should be known. We just add if the minimum of the left part, that is this, is less than the minimum value for the right, then we have to take the minimum for the left part. So I will say that temp.minimum should be equal to this, equal to the minimum, that is my actually r.mini is minimum. So if my r.mini is less than my left.mini, because the minimum is present in the right part, it will now be equal to r.count of mini. The last possibility is that the minimum is equal on both.
Uh-huh. Hello.
the sides, and if the minimum is equal on the both the sides, what we have to do? So we can take the minimum from either of them, right? So let us take it from the left side. So I will say left temp dot count now, just like this. I think it is actually more readable and meaningful, right? So in this, and now I think we should move to the query part. So this query will return what? It will return a node only, right? So this end will also be a node now, and similarly this end will also be a node, and we again have to combine the result of the left and right. And if we don't want the contribution for this node, then what we have to return? We have to return some values that will not be considered. So since in the node structure, I have first used minimum and then the count and then the GCD. So you know that for a range, whenever we calculate the minimum value, if we want to ignore a particular part, then we return an int max value, right? So the same thing I'll write here also. So I will return int max for this minimum purpose. Part, then we return an int max. So you know that for a range, whenever we calculate the minimum value, if we want to ignore a particular part, then we will be 0 and the GCD will also be 0. And if any one of you, I'll write here also, so I will return int max for this minimum purpose, and the count will be 0 and the GCD will also be 0. And if any one of you is wondering that why I took the GCD here to be 0 by default, so let me tell you that the GCD of 0 and any positive integer x is x only. So that's why if I return here 0 and it has to combine with some other node which has GCD of x, so this will automatically be ignored and ultimately it will be equal to x only, right? So that's why I have written the GCD value here to be 0 and just combine the result here like this. So since this is returning a node value, so I will store here, let's say in the temp value, let's say, so I will store this, let's say in a value name as final, right? And I will just check now if the final's GCD value is its count of minimum like this. And now I think I've written the complete code here. So now if I run this, let's see. So as you can see that.
Let's check. I will be back.
So as you can see here that the verdict is accepted, right? And this is the code that we just wrote. That is the merge function logic, build function logic, and the query logic. And since we do not need the update function, we just erased that. And this is how the inputs were taken, and this is the mathematical logic here. So thank you so much for watching this video till this point. I really hope that you have understood something better, and I also hope that you are gaining confidence in this topic. And I'll be uploading more and more videos related to segment tree in the upcoming days. So if you have not subscribed to this channel yet, please subscribe this channel, like the video, because it takes a hell lot of efforts to create each and every single video, right? So please consider subscribing and liking the video and share with your friends who need to watch the series. And so yeah, thank you for watching this video. Thank you. Okay, so hi everyone. So welcome back to this new video in the segment tree series. So today in this video, we will be discussing about this interesting problem that goes by the name enemy is weak. And it was asked in Codeforces beta round 57 div 2. And this problem is rated 1900. Okay, and before starting reading this problem, let me tell you all that this problem will utilize the concept that we have discussed in the first lecture of the series. So this is the video that I'm talking about. So still, if you have not watched this video, please go back to this video, understand the concept, and then come back to this video, right? Then you will understand much more better, right? And also, if you have not subscribed to this channel, please subscribe this channel. As you can see that I am regularly uploading very good quality problems. As you can see, in this way only, I'll be uploading more and more videos in the upcoming days as much as possible from my side. So that's why if you have not subscribed to this channel, please subscribe the channel, right? So, and we are pretty close to 500 subs. So please subscribe. And so let us come back to the topic now. So the problem reads like this: the Romans have attacked again. This time they are much more than the Persians, but Shapur is ready to defeat them. He says a lion lion is never afraid of a 100 sheep. So you can ignore this line at all. Nevertheless, Shapur has to find a weakness in the Roman army to defeat them, so he gives the army a weakness number. So you can also ignore this line. This is not of much significance. So in the Shapur's opinion, the weakness of an army is equal to the number of triplets, that is I, j and k, such that I is less than j and j is less than k. And a of I is greater than a of j and it is greater than a of k, where a of x is the power of the man standing at the position x. And the Roman army has one special trait. The powers of all the people are distinct. So help Shapur find out how weak the Romans are. So in the input, we will just be given an
Okay,
integer
so
n
this
that can go
code
up till
got
106,
accepted.
and which will represent the number of men in the Roman army, that is the
This
size of the
got
array, and
accepted,
then will be given
which is
the array.
nice.
That is the powers of the men in the Roman
Okay.
army.
Now
So in the
I
output, we have to
also
determine the
want to
weakness of the
check
Roman army. That
the
is the
code
weakness of the given arrays, right? The problem is
for
quite straightforward if you
the
see.
previous
That is,
question.
we will just be given an array every time, and for every array, we just
Oh, this video was running. Oh my god. I also want to
The
check the
University of
code for
Melbourne.
this.
and this remained as it is.
I'll I'll do that later. But first, I need to take a break. I need to eat some food and I'll be back soon. Fade to black. Okay, I'm back. Hmm. Yeah, so I wanted to check the code for
Right child.
this question because I didn't understand why did we initialize this with a neutral variable here, and here we just returned a empty node. Why did we do that?
Because they are the left and the right child, right? So now I will is common.
The University of Melbourne pushes me.
To nothing but, as I told you, that it will be equal to lc dot left plus rc dot left minus this common, right? And in the same way, the right part will, and at last just return this temp. So in this way, I have written my merge function here, right? So this will return this node type, that is temp, to this, and it will be stored here. So I think I have. So now I think then all data type we have returned this is a node. So this will return me the merged result for the left part and the right part. So now since this query is a node type, so I will store it. Let's say give it a name of, and I just have to return what? I just have to return this nodes result. So this, and once I have written this, I think I have written the code, that is the query function properly.
Vary for this to this.
And this merge function here, this query function.
Yeah, in the query function. Yeah, why did you return empty node?
I told you that I will say that the left part, and if this is, then I will say since the structure for each node is a node here, so just I have modified this, and now so I'll say tree of node plus right. So this, so let me quickly write this merge function here as right temp. I gave you three, it will be is this minimum of here and equal to right part function here will be stored here. So I think I have, so now I think I am done with the build function. Let us now come to the query function here. When it goes out of the range, then what we have to return? So instead of returning a single zero, I have to return a triple zero here, like this. That is the value of all left, right, and result from this side will be zero. This query will also return a node, right? A node here in the data type, and this two will also be a node there. And what we have to return then? We have to return the merge.
Okay, so every value here is a 0. That's why we can return an empty node basically here. But here, every value cannot be like 0, right? Because of this, the min value needs to be integer dot max value. That's why we cannot return this a min empty node. Okay, okay. But let's solve this
and then will be
problem.
given. Okay, so hi
Discuss.
everyone. So welcome back to this new video in the segmentary series. So today in this video we will be discussing about this interesting problem that goes by the name enemy is weak, and it was asked in code forces beta on 57 div 2, and this problem is rated 1900. Okay.
Before that, I wanted to check this. Yeah.
Okay, and before starting reading this problem, let me tell you all that this problem will utilize the concept that we have discussed in the first lecture of the series. So this is the video that I'm talking about. So still, if you have not watched this video, please go back to this video,
Inversion count.
understand the concept, and then come back to this video, right? Then you will understand much more better, right? And also, if you have not subscribed to the channel, please subscribe to the channel. As you can see more videos in the upcoming days as much as possible. So please subscribe. And so let us come back. Who is ready to defeat them? He says like this.
Okay, let me read the problem first. Enemy is weak. Why is this open? Enemy is weak. Enemy is weak. The Romans have attacked again. This time they are much more than the Persians, but Shapur is ready to defeat them. He says a lion is never afraid of 100 sheep. Okay. Okay. Nevertheless, Shapur has to find weakness in the Roman army to defeat them. So he gives the army a weakness number. This is literally like not required in the question. This is just a random fact or theory, something like that. Not much related to the problem. That's what I think. The actual problem starts from here. Let's see. In Shapur's opinion, the weakness of an army is equal to the number of triplets I, J, K, such that I is less than J less than K, and AI, which is basically the value, AI greater than AJ greater than AK, where A of X is the power of a man standing at position X. The Roman army has one special trait. Powers of all the people in it are distinct. Okay. The input. Hmm, okay. The Roman army has one where the powers of all the people in it are distinct. Okay, that is good to know. Okay. Help Shakir find out how weak the Romans are. Okay. The first line of the input contains a single number n, the number of men in Roman army. Next line contains n different positive numbers. These are the powers of Roman army. Okay. So opinion, the weakness of the army is equal to this. Hmm. A single integer number. No, the first line. Okay, this is okay. A single integer number, the weakness of the Roman army. Please do not use modular LLT specific factor to read or to write 64-bit integers in something. Also, you may use. Okay, this is this. Okay. So you can have three. The output is, oh no, no, the array value is 3 to 1. So this means that the output is 1. For four numbers, 10, 8, 3, 8, 3, 1. So how is this 4? How is the output 4? In Chapo's opinion, the weakness of. Okay, so it can be 10, 3, 1 as well. And then, okay, so basically it's 10, 8, 3, 10, 3, 1, 8, 3, 1, and 10, 8, 1. Okay, so it is all the possibilities. So if we find now, next line contains. Okay, so here we are at this point. We need to find all the numbers that are less than this. So there are one, two, three numbers less than this. So this can form a total of 10, 8, 3, 10, 8, 10, 8, 3, 10, 8, 1, 10, 3, 1. So it can form a total of three combinations. Okay, but if we have two numbers less than this, it can only form one. But if it has three combinations, it can form three different combinations. Here, it's only 5, 4, 3. What if there was a 0 here? So there are 4, right? So 3, then 10, 8, 0, 10, 3, 0, 10, 1, 0. So this contributed a plus 3. If it's hmm, if it's 2, it contributed 1. If it's 3, it contributed 3. Wow. So there should be a pattern in that, right? There should be a pattern in that. Okay, we can figure it out. Basically, we need to find all the numbers that are smaller than this. That is fine. We can solve that using a segment tree. But how to get that pair? There are three numbers smaller than this. So in total, there are. Hmm, Okay, let's see.
The Romans have attacked again. This time they are much more than the Persians, but Shapur is ready to defeat them. He says, a lion is never afraid of 100 sheep. So you can ignore this line at all. Nevertheless, Shapur has to find a weakness in the Roman army to defeat them, so he gives the army a weakness number. So you can also ignore this line. This is not of much significance. So in the Shapur's opinion, the weakness of is the one. So tell me, how many triplets can be made out of this following array? So exactly one triplet can be made, right? Because only 3 elements are present. You cannot make more than one triplet. So this will be the only triplet. That is form. We wanted to see that if it satisfies these two conditions. Condition what we wanted that if it accepted that if this we don't want it, so in this then so let us now go to the blackboard and understand how the output is 4 for 10, 8 and 1, 10 and 3, 1, this 8 and 3, 1. So a total of 4 triplets. Understand how the output is 4 for this input. More than one triplet possible. So what are these triplets? As I told you, and I have marked the indexing also for all of these 4. So now if you see, then let us start checking each triplet one by one if they satisfy the given conditions or not. So what was our given condition if you remember? So our condition was that that our I should be less than j and our j should be less than k, and the value of the ith element should be greater than the jth element, and it should be greater than the kth element, right? So these are the two conditions that we want to satisfy for each of the triplets. So this is our first triplet, and clearly 0 is less than 1 and it is less than 2.
What versions in our segmentary code? This is the normal build. We pass while update. We start from 0 to original -1. Okay, yeah. Index. This is fine. So basically start from 0 to that index. Index is less than equal to the middle value. Then go to the left side. Otherwise, go to the right side. Okay. Yep.
So this condition is satisfied, but if you look in the second condition, so we want the element's value to decrease when we move, and then we get addition. So now we have also x direction. So that if we move right, so what we did out of the given array, we wrote all the possible triplets and checked one by one if they satisfy both of these properties, and if they do so, then we just increase the count 1 each time, and whatever the final count we got, this is our answer, and the output for this example is also 4. So I hope you have understood this example very well, and also what this question is asking us to print. And then this is our last example given in the question. So if you look in this example, then again our 4 triplets will be possible, just like we did for this array, right? So again here 4 triplets will be possible, but the only triplet that will satisfy the given conditions will be this triplet, that is 5, 4 and 3, because clearly the index is increasing while moving in this direction, but the element's value is decreasing. So that's why this is the only triplet that will satisfy this question. You can check by dry running, right? And that's why the output is 1 for this. So I hope you have got the concept of every example. How the outputs are coming for each of the examples, and what this question is asking us to print. So the question is not asking us very hard things to do. It just wants us to check for every triplet this condition. Blackboard. So I want to value in member.
No, I understand
Represent.
this, but how do you get the number of pairs? Like for this index, there are 3 elements that are smaller than this.
This range. Let's come to this question back.
But how do you know that there will be 3 combinations? There's a formula. This is a part of combinatorics, I believe. Let's see.
As you can see here, that this question is very much similar to the previous problem. That is I is the. So keep this word in your mind. So side, that is this range, which are greater than 2, right? So keep this word in your mind. So we found the greater elements on its left side, don't we? That is, for each index we found the number of greater elements on its left side. But suppose the question if had asked to find instead the number of smaller elements on its left, then what we have done in that case? So since it had asked greater here, so suppose we were standing at this index and the value was 2, so we wanted greater than 2, that is greater than or equal to 3, so we used to look in this range. But if the question has asked to count the number of elements which are smaller instead on its left, now what I'm saying, tell me the number of smaller on its left, then what could you have done? So we will again do the same thing only, but instead of starting from this 3 to 5, we will simply start from this 0 and we'll go till this 1, right? So since in this case we wanted to greater than 2, that is greater than or equal to 3, so we took this range. But now since we want to find the number of elements smaller and present on its left side, so I will simply start from the beginning and we'll go till 1 less what we want to compute. So this is common sense, right? We wanted greater, so we took this range, and now since we want smaller, we will simply take the range sum of this, right? And in so we start this range. But now since we want to find the number of elements smaller and present on its left side, so I will simply start from the beginning and we'll go till 1 less what we want to compute. So this is common sense, right? We wanted greater, so we took this range, and now since we want smaller, we will simply take the range sum of this, right? And in this way I will get these two. So this is easy, right? So let me erase this. So let me again tell you what I just said. I told you that in that question we used to find the number of elements greater on the left of it. So if we were standing at this index, we wanted to find the number of elements greater than 2, that is greater than or equal to 3, that have occurred in this range. So we used to take the range sum of this, right? But if we wanted to find the number of elements which are smaller than it and occurred on the left side, then we will simply take this range sum instead of this, right? So this thing is clear by now, I guess. That great, take the range sum of this. So I will simply start from the beginning and we'll go till 1 number. Since in this case we wanted to greater than 2, that is greater than or equal to 3, so we took this range 1, right? So since in this case we wanted to greater than 2, that is greater than or equal to 3, so we took this range. But now since we want to find the number of elements smaller and present on its left side, so I will simply start from the beginning and we'll go till 1 less what we want to compute. So this is common sense, right? We wanted greater, so we took this range, and now since we want smaller, we will simply take the range sum of this, right? And in this way I will get these two. So this is easy, right? So let me erase this. So let me again tell you what I just said. I told you that in that question we used to find the number of elements greater on the left of it. So if we were standing at this index, we wanted to find the number of elements greater than 2, that is greater than or equal to 3, that have occurred in this range. So we used to take the range sum of this, right? But if we wanted to find the number of elements which are smaller than it, and I will again say the same thing here, that is, I will again want to compute this greater and this smaller, but now for the right side. That is, I want you to answer for each index how many elements are greater on its right side and how many elements are smaller on its right side. So again,
Yeah, start from the right side and traverse to the left.
some of you might have predicted and guessed what we will do. So instead of starting from the very start and going in this direction, like start from this direction and we'll go in this direction like this. So as we move forward in this direction, if we want to determine the number of elements greater than itself that have occurred in this range, then we will simply take the range sum of that range, right? And it will give this result correctly. And similarly, if you want to compute the number of elements which are smaller than these two and occurred in the right side, then we will simply take the range sum in this range and it will give this output. So these two are the exactly same. Instead of getting this, for this condition, these four were our possible examples, right? So let me write one of them here. This 10, 8, 3 is one of the possibilities which will satisfy this. I will not touch this 8, right? And one thing, that if I keep the possibilities which will satisfy this condition, so just tell me one thing, that if I keep this 8 fixed, that is, I will not touch this 8, right? And if I change these two, that is, if I change this 10 to something like 11 and then also change this 3 to something like let's say 2, by doing this, that is keeping this as it is and changing these two, is this property still valid? So yes, this is still valid, because this is the greatest, this is the smallest, and this is decreasing in this direction. So these two conditions are still valid here. So now I have given you the permission to change these two values, that is the ith index and the kth index, while keeping this jth index intact, right? That is, we don't have to change this, we just have to change this. And we saw that earlier this is our one of the possible result which satisfied this condition, and now this is another possible result, and this, like, let's say 9 and this 2 to something like 7. So is my property still valid for this triplet? So the answer is yes, because the magnitude is clearly decreasing while going this way. So what I'm trying to say is, you just have to keep this jth index fixed, and you can select this ith and kth index value in such a way that this ith will always be greater than this jth index and this kth index will always be smaller than this jth index, right? So if you're able to make these triplets like this, right, so whatever value you will get, it will always satisfy this. So since initially this was satisfying this property and I wanted to satisfy it for another triplets, so I just keep this fixed and kept on changing these two values and made sure that the left value is greater than this middle value and the right value is smaller. So now assume that I'm talking about this array. So I have considered this myself, and we want to compute the number of triplets such that my I will be present in this range, my k will be present in this range, and I will mark this 3 here as my jth index, and I will not change this, right? If I do this, then I can say I want this to happen, right? That is, some element present in this range which will be smaller than this, right? So how many such triplets are possible? That is, I want you to fill these two spaces
4
in such a way that it
and
satisfies the given
3.
condition, that is this condition. So I want to fill this with some element greater than 8 of this range. So if you see, then we can fill this circle with either the second index element, or either with the first index element, or either with the 0th index element. That is, either with 9 or with 10 or with 11, because these three are actually. So let me, that is number of elements less than 8 in this range. So since this 7 is less than 8, this 3 is less than 8, this 2 is less than 8.
So 3 into 4, which is 12. And I believe plus 1. Oh no.
And this one is less than 8. So clearly all of these 4 elements are less than 8. So it means that we can fill these circles with any of these 4 values. And now let me write those values here also so that you can understand. Or with 10, 1. So if you select any value from this and any value from this, 9 from here and 7 from here, so we will increase our count by 1. Similarly, if we select this 9 and this 3, that is 9 and triplet, right? So again a valid triplet. A valid triplet. That's our answer. Take this 11. Similarly, if we take 11 from here and 3 from here, so 11 is
Yeah,
this.
so 3 into 4.
So clearly 11 is greater than 8, and it is a combination of this, this and this. The second triplet by the combination of and this. And say the total triplets, that is I, j and k, right, possible for a given jth index is equal to nothing but the number of elements present on its left, right, and they have to be greater than the jth index element, into the number of elements present on the right side which are less than this jth index element. So since here the number of elements greater than 8 on its left side was 3, and the number of elements smaller than 8 on its right side was 4. So I will say here 3 into 4, right? So 3 into 4, that is 12. So it means that by keeping this 8 fixed here, that is this third index, so this is my jth index, right? So by keeping this third index in every index of this original array, it will ultimately give our result that we wanted to compute for each of these indexes as the jth index, and we'll keep fixing them one by one, right? So one by one, each of these indexes present in the original array, that is these, right? So one by one, we will consider them as the jth index, and we'll keep fixing them one by one, right? And just add this result to our answer for each of these fixed index, because we saw that whenever we fixed some index and computed the number of elements greater than this fixed index on its left side and the number of elements smaller than this fixed index on its right side, and we just multiplied them in order to compute the total number of triplets possible for this j, right? So it was 12 here. So since it was 12 here for this jth index, that is the third index here, so in the same way we will fix each and every index one by one, and we'll compute the same thing, and we'll just add it to our final result. So since now I did it for this third index, what I'm not telling you is to do is we want to fix it for each and every index. But there is a very one good thing to notice: you can never fix this 0 or this 7.
It would not. Yeah, yeah, of course. I mean, this, like, any number greater than the 0th index number, this will return a 0, and then this will return some value. But since there is a 0 here, 0 into any of this value, any value, no, frequent, how do I put it into words? Number of elements on the right side into the number of elements in the left side will be 0, because the number of elements here in the left side is 0. So obviously this will not contribute. Yeah.
Why? Because there is no element present on its left side, and similarly there is no element present on the right side of the 7th index, right? So it is not useful to determine the number
Yeah, 0 multiplied something is equal to 0 only.
of greater elements on this left side, and similarly it is not useful to determine the number of smaller elements on this right, and the number of elements present on its right side which are smaller than the current element. And if we multiply these two, that is we take all the possible combinations, then that will give us the total number of triplets possible for that jth index. So if I write that down here, so for these 3 we got 12, right? So if I do the same thing one by one, that is keeping each of these indexes fixed. So let me do this thing quickly so that you can understand this thing in very much detail. So let us now start fixing them one by one. So now I am trying to fix this one index here, right? So what is the value of this first index? It is 10. So now I want to find the number of elements greater than 10 on its left side. So since this is the only element present on its left and is greater than 10, so I can write here that there is a total of one element present on its left which is greater, which is 11. Similarly, if I want to find the number of elements which are smaller than this 10 on its right side, so how many elements are smaller than 10? So if you look, then all of these elements are actually smaller than 10. That is a total of 6 elements, right? So I will write here 6. And if I write down all the elements also, then they are like 9, 8, 7. It's possible for this jth index, that is this first index, then it will be equal to this 1 into 6. So 1 into 6, which is 6. So I will write here 6. So a total of 6 triplets are possible. So it will be what? So it will be either 11, 10 or 9, or 11, 10 or 8, or 11, 10 or 7 index. That is the second index. So what is the value? The value is 9. So since there are two elements elements which are greater. So I will write here 2. And what are these two elements? These are then this 9. I want you to answer the number of elements on its, like if you want to either calculate the greater element or the smaller element on its left, or the smaller element or the greater element on its right. So we can decide this at any time. So this is not an issue. So what we left, will get this, right? And this only. So that means a total of 56 triplets are possible for the calculate, right? And what will be our logic? So now we just have to find these two things for each index, right? So we have already discussed how to find this term, that is the number of elements greater than the current element on its left side, in the first video of this series, right? So this is the exactly same thing, and as I told you that this is nothing but the reverse version of this. That is, instead of going in this direction and calculating this, if we go in this direction, then we'll get this, right? And it depends on us, like if you want to either calculate the greater element or the smaller element on its left, or the smaller element or the greater element on its right. So we can decide this at any time. So this is not an issue. So what we used to do, if you remember, in order to find this, we used to take the maximum element of it, which is 11 here, and used to draw another array such that we can access the 11th index easily, right? And whenever we used to do a transition from one index to another array such that we can access the 11th index easily, right? And whenever we used to do a transition from one index to another index, we used to update this thing continuously and just take the range sum in order to either find the greater or the smaller element present on its left side. So this is not an issue at all, right? I want to compute this term now. So consider this whole structure here. As I said, for the given array, since our 11th element is the maximum, so I drew this another array such that I can access this 11th element easily, right? And using this array, I will just find the number of elements greater than the current element on its left. Exactly same as in the first video. What we used to do, if you remember in this case, so initially the value of each and every element in this array used to be 0, right? We always start from the first index and go till the 6th index, because for this 0th index there is no element present on its left side which is greater, and similarly for this 7th index, that is this one, there is no element present on its right side which is smaller. So whenever we do a transition, we used to update the status of this in this array, right? So since I'm moving from 0 to 1, I will update this in this array. So this 11 will now become equal to 1. That is, if now I'm standing on the first index, then I have encountered 11 a total of 1 time before. So this array represents the status of
Yeah, t.update the index, which will be the value 11, comma 1.
the frequency of the elements that I have encountered before. Okay. And now, since we also want to calculate this term simultaneously, so how we will do this? As of now, I'm standing on the first index, right? And for this first index, I know the value of this term by taking the range sum of this, which is 1 here. So I know that a total of 1 element is present on its left side, which is greater than 10. So I already know this using this array. But now the question is, how we will determine this term using this array? That is, for each index, we want to determine the number of elements smaller than it on its right side. So if I'm standing on this particular index, then I only want the information regarding this range, right? Because if I'm standing on this index, then I'm assuming that I have started moving in this direction, and currently I'm standing on this index. So I should not have this information, right? I only want this information, and I'm standing on this index, so I should not have this information, right? I only want this information and want to determine out of this range the number of elements greater than or less than, right? So let me tell you again what I just said. So if I'm standing on this index and want to find the number of elements greater than or smaller than on its right side, then only this much information I need in this array. I don't need this information, right? So you can think it like, I have not yet encountered these elements. I have only encountered these much elements while moving in this direction. If I am standing at the 0th index, then what will be the status of this array? I would not have encountered any element before, right? If I have not encountered any element before, it means that the value of each and every element in this array should be 0. And also, if I am standing on the 0th index, then what does it mean for this array? It means that I have started my journey from here, right? And reached this 0th index. So by doing this, I have already encountered these elements one time. So that's why I can say that the value of each
Total number of elements encountered minus the total number of elements in the array, that is this up to 11, minus the total number of elements that are greater. Yeah. And since the numbers are distant, every single time the value will be 1. These values will be 1, because in the question they had mentioned that powers of all the people in it are distant. So the problem is done. That's it, right?
and every element present in the original array in this array will be equal to 1. We started moving in this direction from the right side, right? And if you are standing at the 0th index, then it meant for this array that we have not yet encountered any element. So it was 0 for all. But since we are standing at the 0th index, that is, we have started moving in this direction and reached this index. So it means that we have already encountered each and every element once. That's why I will write here the frequency for these terms like 1, 2, 3, 7. So 1, 2, 3, 7. And then 8, 9, 10, and 11. So 8, 9, 10, and 11 equal to 1. And others will be 0 only. So this will be the 8, 9 frequency for these terms like 1, 2, 3, 7. So 1, 2, 3, 7. And then 8, 9, 10, and 11. So 8, 9, 10, and 11 equal to 1. And others will be 0 only. So this will be the status of our second array initially. And since I did a transition from the zeroth index
Why did you put 10 and 11 as 1 as well?
to this first index now, it means that I only now need the information for this range, right?
Hmm.
Because if I'm standing on the
Okay.
first index, then in this way, I only have reached the first index from the second array's perspective.
Okay, so this minus this. And then minus 1 as well. Because you're at the ninth index here. And you need to subtract this value as well. Yeah.
Right? So the only elements that should be updated in this array should be these ones only, right?
Hmm.
So that's why what I will say is I will decrease the count of this 11 here by 1. So this 11 will now become equal to 0. I hope you have got this
Okay.
concept. So if I'm
Okay. 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 So just update that array with array's index with minus 1. Or just set the value equal to 0 then. Yeah. It's better to like literally in the update function set its value to 0. Okay, this makes sense. Oh my god, why is this? Yeah, 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 yeah. Yeah. Mm-hmm. This is a good problem. Like on the easier side, it is a good problem. Public class, yes, we just a minute. Okay. Mhm. Huh. Now, okay, what do we have here? Let's read the problem or just uh check the input. We have n first and then an array of size n. Int n equal to sc dot next int sc dot close scanner sc equal to new scanner system dot in int array to new int and then what do we do here? Yeah, initialize our no, first take the input I less than n I plus plus array of I equal to c dot next int. Then what do we do? Initialize our segment tree, static class, segment tree. Yeah, we have int tree and then n as well. Public, public segment tree array. This is 3 oops, equal to new int. Do we even need n equal to 3 dot length and we build using this array. We have the start node start and end and end. Public void build string int array int node int start int end. Okay, we'll write the logic for it later, but first we have this array. We need to perform some queries. First, we have segment tree. This will return all the numbers that are less than it. No. This, no. The right subtree, right tree, new segment tree of this array, yes. Should I sign my array? Yes, I should. Wait, let me first check the size. Oh, AI can go up to 10 power 9. Oof. So this will be long. No. Yeah, this will be long. Long. Next. Long. This is long. Yeah, the value here can be int.
size will be n equal to 10 power 9. 1, 2, 3 plus 1. In 10 n plus 1 because it needs to be inclusive. Or does it? Yeah, it does. Yeah. Yeah. Okay. Then what do we have here now? Right tree, right? This will set all the values equal to 1. Just build a right subtree, build a state. Yeah, we never used our build function. Yeah, that's why I was a bit confused. But yeah, we never used our build function. We just called it. We just called the update function. Okay. So we don't even need to build all of this. We don't need to build. We just need to update. So we don't need the we need the array, right? Do we need the array? No, we don't. Yeah, just update from this index to this index. Int node. Yeah, in update we need index and value. Now in the update util we'll have we don't have array here as well. We'll have our node. We have 0, we have ending index, we have idx and then value. Public void update util int node int start int end int left int right if start equally no. For update we need to get in the range, right? If this is out of bounds, if start yeah, no. If start equal to end, what do we do?
That's when you update. Update tree of node equal to that value. No. Equal to that value, yeah. In our case, it's fine. Else, int mid equal to start plus int divided by 2 int L. No. If idx is less than equal to mid, no, then we call the update start till mid, else call the update util from mid plus 1 till end, and at the end we update this 2 times node plus 1 plus 3 of 2 times node plus 2. Okay, now we have our query public void query. We have int left, int right. Now, if we want all the numbers greater, you go from the left will be from that number plus 1 and up to the last n. If you want all the numbers that are smaller, you go from 0 or basically 1 till that number minus 1. Yeah. So, okay, we have the range. Return, this will be int query util. We have our node start, end, then left and right. Public int query util, int node, int start, int end, int left, int right. Just a minute. I need to check something. Just a minute. So we'll have our node. We have end, end left. We have end, end left. Just, okay, this size should be fine. Oops. Okay. In the query util, what do we write the standard code? If start is greater than end or end is less than left, just return 0. Else if left is less than equal to start and and end is less than equal to right, then return tree of node. Else int mid equal to start plus end divide by 2 and intel equal to query util int r equal to this return l plus r 2 times node plus 1 2 times node plus 2. We have mid plus 1 up to mid and we should be good. We have the right tree right now. So for n equal to 0, I less than n, I plus plus. What do we want to do here? Right tree dot update. Why is this taking 3 parameters? Yeah, update. You have array of I and then update with the value 1. Why is this throwing an error? Wait, this is 10 power 9, right? Yeah, it should suffice under int. This can be int. This should be good here. Yeah, we are good. Then create another segment tree, which will be left segment tree. Segment tree. equal to new segment tree. Now, oh, left segment tree. Now, what does this do? Traverse through all the indices and find out how many numbers. So, left segment tree. This should be greater, right? This is small, but we need to find all the greater numbers that are greater. Dot query. We have the starting index. Array of I plus 1 up till n minus 1. Yeah. Now, but here n, I should name it size minus 1. And now, what is size? Int size equal to, yeah. Okay, from this to this will return all the values that are greater. Int left, or basically int greater numbers. Now we have all the greater numbers. We need all the smaller numbers. Int smaller numbers equal to right segmentary dot query array of I minus 1, and this will be from 0 to array of I minus 1. Hello. Yeah. Now, S out greater elements into smaller elements. And we have total plus equal to this into this. Then total equal to 0. At the end, S out the value of total. But before that, after we calculate total, what we do is in the right segment tree, we update array of I equal to 0. In the left segment tree, we update array of I with 1. Wait, what is this? Why can it not be this big? This tries to GB of memory. Oh my god. What's the latest version of this information? If start is greater than end or end is. Oh, start is greater than right. And then yes, yeah, yeah. But what table is yeah. So for suggestion, I can okay, I know how to solve it using like a Fenwick tree, but I want to learn how to solve it using a segment tree as well.
Standing on this index, then I only need the information for this range, right? You can also take it for this range, there is no problem. So now we are standing on the first index, and this is the status of our first array, that is, we have encountered current element from, because if you are standing, when I had traversed till the third index, I would have only encountered these much number of elements and not these. So the status of this should be absent from this array. So that's why I'll decrease the count of this 9 from 1 to 0. And now if I compute these two terms, so the number of elements greater than 8 on its left is actually 3, right? It is obvious from the range sum here also. So 3 from here. And we have to multiply this 3 with the number of elements smaller on the right of this 8 in this range. So it is 0 now. So this information is not needed now. We only need this information, because if you are standing at this index, then I'm assuming that we have traveled in this direction hypothetically. And if I have traveled in this direction and reached this index, then I would have only encountered these much number of elements and not these. So these status should be absent from the current array. So now what I want, the number of elements greater than 7, that is greater than or equal to 8. That is the range sum of this, which is 4 only. So 4 from here into the number of elements smaller on the right. So smaller than 7, that is smaller than or less than or equal to 6, right? So the range sum of this would give us this, which is 3. Which is true here also, right? So 3 from here. So 4 into 3, 12. Just as you got before. Update in index, which is 0. So clear my actually segment tree here. So I will use this first segment tree in order to calculate the number of elements greater than the current element present on the left side. So let me name this as the forward segment tree array here, like this. And similarly, I can construct another segment tree that will give me the number of total elements smaller than the current element on its right side, like this. Let me copy my standard segment tree template here. So this is my standard segment tree template here that supports many two operations. First is the point update, and the second is the range sum. And keep one thing in mind, that in this point update actually I am increasing the delta, that is I'm not setting it equal to delta. Actually, I'm increasing the delta. So if this delta is plus 1, it will actually increase the count. And if this delta is minus 1, it will actually decrease my count. And instead of passing this array here, I can simply pass the maxi that I have calculated. Because we don't need to pass the actual array here. Because if we pass this maxi here only, then we know that if the maximum element present in the given array was 11, then we want to access the 11th index, right? So
Hmm.
that's why in order to access this 11th index, I am increasing my maxi by plus 1 here. So that whenever I set the index of size of the segment tree, I can easily access this 11th index. So that's why I'm doing a maxi plus plus here and setting the size of the segment tree equal to this maxi. And once I do this, I'm just assigning the value of each and every element in this segment tree equal to 0. That is, after writing these two lines, what will happen? It will construct these two arrays, but with each and every element equal to 0, right? So initially, each and every element will be 0 for this and for this also, right? So the same thing is done here also, right? And then the usual build query update. It will construct element in this segment tree equal to this maxi. And once I do this, I'm just assigning the value of each and every element in this segment tree equal to 0. That is, after writing these two lines, what will happen? It will construct these two arrays, but with each and every element equal to 0, right? So initially, each and every element will be 0 for this and for this also, right? So the same thing is done here also, right?
Hmm.
And then the usual build query update functions. As I told you that before actually starting our range operation, we have to set the status for each and every element given in the original array equal to 1 in the second array, right? And not each and every index. We just have to update these given elements position. So since these terms like 4 and 5 was not present in this array initially, so we will not consider them equal to 1 here, right? So that's why we will set equal to 1 only those elements which are present here initially. That is, we have encountered them only and not the others. So we'll write the same thing here. That is, we'll travel each and every element again. I have to update the second array. That is, backward.update position we have to update. We have to update the nums of I equal to 1. That is, the value of delta is 1 here. So since it is plus 1, it will increase the count of all of these positions by 1. And now what we used to do, if you remember,
Yeah. In the update, we do plus value. So instead of setting it to 0, I do a -1 here.
so we used to travel from the starting till the end. That is, our j will go from the starting till the n minus 1. And for each of these j, we used to calculate the number of elements which are greater than the current element on its left. And this is calculated using the first array, that is forward.query. And since I want the greater, so I will say nums of j plus 1
Plus 1
till the
till
last element of this array. That
maxi.
is
Yeah.
this. And in the same fashion, I also carry minus 1 like this. And I just have to multiply these two terms
Oh, we start from 1. Yeah. We start from 1. Calculate the total count.
and add it to our final result. So let me copy this here. So this will be my greater left. Moving on to the next index, we have to update the status of the current indexes in both of the arrays. So I will say, and similarly, this backward.update
-1
this nums
equal
of
to.
j by minus 1.
Yeah.
So this plus 1 is the, so this 1 represents a plus 1 delta. That is we have encountered this element, and this minus 1
Yeah. So it's just that I should have set this value with the maximum value here. So just initialize a max. This is integer dot min value max equal to math dot max of array of I and this. Now, since this is done, int no n equal to max plus 1. Int size. Let's initialize our segment tray int size or intel. This is equal to n. We don't need this. We don't need that actually. So this dot n equal to n. Here we saying the size. Okay, initialize this with 1. Why did this fail?
Represents that we are erasing the information for this value, put or not. So as you can see, each and every test case is getting.
Then why did my code fail? Why is it still failing the test cases? Then what is the value of max for
Passed very well.
this file? Yeah, long. Okay, wait, this can be long. And this is also long, long. Let's see. To fix the segment tree code, don't convert it to Fenwick tree code.
Wait. Why did you do a call and compression? Don't do coordinate compression.
right? So I think I have written the correct code here completely, and also
Oh,
make sure that
you also do a coordinate compression.
this int is actually long, so this can give wrong results. And I also have made sure that since I have used long in every variable here, so that's why I also made this segment tree with this long only, right? So now I think I've written the complete code, and now if I try to submit this on the platform, let's see if this is correct or not.
Array of I can never be equal to 0. Oh, yeah. Okay, let's see for like how to do coordinate compression.
As you can see here that we have got memory limit exceeded on test 21. So why this has happened? So the video is not over yet. Please be with me for some few more time. So if you have read the question, then notice one thing, that the value of each element can go up till 1e9. So if it goes till 1e9, then what will happen? This maxi will be 1e9, right? And if this maxi will be 1e9, then this maxi is equal to n here. And the segment tree size will thereby equal to 4n, that is 4 into 1e9. And we are using two such segment trees.
Wait, what if I solve this problem using a Fenwick tree? Public class PSU Fenwick tree. Bracket class Fenwick tree. Long widths and then we need an we do okay. Let's see that yeah. So you take the coordinate compression even in Fenwick tree. What's the point? What's the point? Fenwick tree then. I mean the code is much way shorter. But that's it, right? Yeah. No, let's see how to do coordinate compression.
Here, that is 4 into 1e9 twice. So that's why this is giving a memory limit exceeded. So let me tell you about this concept of coordinate compression here that will be used in this problem in order to solve this memory limit exceeded problem. So what we do in this? So suppose initially we were given this array, and when we tried to submit the solution for this input, we got MLE, right? Just assume this was our original given array. So how can we optimize this now using this coordinate compression technique? So what does this technique says? It says that, let me write the indexes here. So this is 0, this is 1, this is 2, and this is 3, right? So this technique says that initially what we will do, we will copy this original array into some other array. Let's say copy v. So we will copy the same array, right? So once I have copied this array, what we have to do next? We have to sort this copy array. So if I sort this, I will get this, right? And once I get this, the next step of this technique is to remove the duplicate elements. So since this 1e9 is coming twice, so I will say that in the next step, I will just remove one of them. So I will remove this last one. So this is my current status. And now that in the next step, I will just remove one of them. So I will remove this last one twice. So I will say that In the next step, I will just remove one of them. So I will remove this last one. So this is my current status. And now this is my 0th index, this is my first index, and this is my second index. So it means that instead of using this 2e8 value, I will simply use this 0 value because this is unique for this 2e8. Similarly, instead of using this 5e8 value, I will use this 1 value. And similarly, instead of using this 1e9 value, I will simply use this 2 value. So this, you can think it like this 0 represents this 1 represents this now, and this 2 represents this now. So keep this in mind. So since the original array was something like this, so now if I map them using their new values, then it would be something like this 1e9 is now equal to this 2. So I will write 2. This 2e8 is now equal to this 0. So 0. Again, this 1e9 is equal to this 2 only, so 2, and this 5e8 is now equal to 1, so 1. Instead of doing operations on this original array, that is this one, I will simply use this array now. And there is a very good thing to notice if you see clearly. So this was the biggest, then this, and then this. So in this array also if you see, then this is the biggest, this is the medium one, and this is the smallest. So the relative order of the ascending and descending, if you see clearly, on this original array only, so 2, and this 5e8 is now equal to 1, so 1. Instead of doing operations on this original array, that is this one, I will simply use this array now. And there is a very good thing to notice if you see clearly. So this
and can be up to 26. So it won't exceed our memory limit.
was the biggest, then this, and then this. So in this array also if you see, then this is the biggest, this is the medium one, and this is the smallest. So the relative order of the ascending and descending order is same in this array as this array. And since we just wanted to compute the number of smaller and greater on the left and right, we can just use this array instead of this original array, and this will not give me the memory limit exceeded that we just got. So that's why we will use this coordinate compression technique in this question in order to reduce these large values into these smaller values while keeping the relative order of the ascending and descending order same, and thereby playing with this array only in order to compute the greater left and the smaller right, and we'll get the exact results therefore. So now we don't have to calculate this maxi. Instead, I will say that after taking the input, I will make another copy of this array as I told you. Let's name it as copy of v, and it will be equal to, or maybe copy of nums, so it will be equal to this nums only. And after doing this, we just have to sort this array, right? So I will sort this. So I will say sort. So after sorting it, what I told next, we have to remove the duplicates, right? So in order to remove the duplicates, I will say, so by writing this statement, it will actually remove the duplicate elements from this copy nums array, right? And after doing this, what we will do next? So I told you that for each of the original elements in the array, that is from 0 to n minus 1, we will assign new values. This nums of I will now be equal to what? So this lower bound function is used to find the new index in the uniquely sorted array. That is the copy nums array, right? And thereby assigning it to the original array like this. And once this is done, what I told you that my new maxi will be what? My new maxi will be the maximum element present in this nums now. So you can write it like, so this will be my new maximum element, right? So once we have written this and calculated our new maxi, I think the code is correct, but since now in the original question it was given that each and every input element was a positive integer, that is from 1 to 1e9, but since now the element value can be 0 also, so I will say here that instead of starting from 1, I will actually start from 0. And now if I run the code, let's see. So as you can see that each and every test case is correct now, and I think now that it should not give the memory limit exceeded problem, right? So now if I try to submit, let's see if this is correct or not.
What if the nums of I is equals to 0 there? Then 0 minus 1 will be minus 1. So we need to keep a check on that as well, right?
Just wrote. So as you can see that it is accepted now.
Okay.
This is the code that we just wrote. So the standard segmentary template, and initially we tried to do this with the coordinate compression, but then we saw that it was giving memory limit exceeded. And why I told you very well, because the segmentary size was getting excessive. So that's why we apply this coordinate compression technique here, and I also explained you this technique how this works.
Coordinate compression.
long sorted array dot clone array dot sort this. This is the value. This will be the index. Long x in circle. If dot contains key, if it doesn't contain key, this and then this. Size is equal to array. Hmm, those many elements. Yeah, dot get array of I, which is this. Yeah. So we don't need this, but create a hash map, long integer, compress coordinate compression equal to new hash map. We first need to clone a long sorted equal to array dot clone arrays dot sort. We have int id equal to 0 for I equal to 0, I less than n, I plus plus. If com dot if it doesn't contains this key, com dot put this key id plus plus, and this will be equal to id int c equal to com dot get array of I, and then update this value again for this, and c equal to com dot get array of I. We query for this, query for this, get the value, then update this. Huh. Okay, run all
What? Oh, oh, oh. This size, this will look solutions. No problem. Bye bye. into mode. Int n, int left, int right. Oof. This should be int, int. The value will also be int because it's only +1 or -1. Hmm. Yeah, I can return. Hmm. It's the Yeah. What is this? If it doesn't contain this, oh wait, if it doesn't contain this key, which is array of I, com dot put array of I. Do I? If it contains, oh, then put sorted. Yeah, yeah, yeah. Perfect. Oh, you know what?
right? And then the rest everything as I just explained you in the video. So thank you so much for watching this video till this point. And if you have not subscribed to this channel, please subscribe this channel because it is already creating a lot of amazing content here, right? And I'm so sure that these videos will definitely help you in your interviews because the questions that I'm discussing here are really of good quality and obviously high rated. So consider subscribing the channel and share it with your friends who need it to watch the videos. So yeah, thank you for watching these videos. Thank you. Hi everyone, so welcome back to yet new video on the segmentary series. So today in this video we'll be discussing about this interesting code forces problem from its reduce section that goes by the name first
One,
element
two,
at least
three.
x. So before discussing about this interesting code forces problem from its reduce section,
First element, at least X. Really on test two. Why did this code give a clearly when connected like unquote forces? Let's see. Do this. Yeah, right.
that goes by the name first element at least x.
Um, Leo,
So before continuing in this video, and I'm very sure you watch this video, operation of finding
Leo, Fatima. Segment 3, Part 1, Step 2. That means step practice. In this task, you need to add to the segment tree the operation of finding the minimum index j. What is this? Nice. This problem was rated. What was this problem rated? What?
Hi everyone, so welcome back to yet new video on the segmentary series. So today in this video we'll be discussing about this interesting code forces problem from its reduce section that goes by the name first element.
This problem was rated 1900. This was a E from Dev 2. A. You need to add to the segmentary the operation of finding the minimum index j such that a of j is greater than equal to x. Minimum index j such that that value a of j hmm, is greater than equal to x. The first line contains two integers n and m. This is 10 to the power 5. The size of the array and the number of operations. The next line contains n numbers ai. The initial state of the array is this. Okay, so we need coordinate compression again. The description of each operation is as follows. Change the item with index I to V. The following line contains the description of the operation. Each operation. Find the minimum index J. If there is no such element, print -1. Indices 1, 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7.
At least x. So before continuing in this video, and I also need 3. So in the input, we will just be given to minimum index. This is the problem. So in this problem, you need to add to the segment tree the operation of finding the minimum index j such that a of j is greater than or equal to x. So in the input, we will just be given two integers n and m. So this n will represent the size of the array, right? And this m will represent the number of operations or the number of queries. And then in the next line, it contains of n integers, that is the array itself, and each value can go up till 1e9, and the minimum value is 0. So every value is positive. In the next following lines, it contains the description of each query. So if the query is of first type, so it will contain two integers, that is I and v. So it means that we have to do the point. So if the query is of first type, so it will contain two integers, that is I and v. So it means that we have to do the point update at this index I with this value v.
Okay.
Right? So we have done this thing many times in the past, so this is not a harder thing, right? And this is the second query. So in the second query, we will just be given an integer x.
Okay, so this is second type of query. This is second type of query. This is first type of query. Okay, okay.
So for this, we have to find the minimum index j such that a of j is greater than or equal to x. And if there is no such element, print -1, and indices start from 0. So we have to check for the whole array here, right? And for each operation of the second type, we have to print the answer for the query.
We need to find the number that is greater than this current number, but return the index, return the smallest index or the first index that comes, which is greater, which contains the value which is greater than this x. So for each index, for range this to this, store the first number of the index which is greater. Hmm.
That is for this query. That is the minimum index j for which this condition is satisfied. This is the problem, and in the input here, as you can see, the size of the array is 5 and the value of number of queries is 7. So this is my array, that is 1, 3, 2, 4 and 6, and then we are given 7 queries. So this is our first query, this is my second query, this is my third, this is fourth, this is fifth, this is sixth, and this is 7. So every query will be either of the type 1, every query will be either of the type 1 or either it will be of the type 2, right? So if it is of the type 1, then we don't have to do anything, but we just have to do the point update, right? That is, so we'll just say that t.update I comma v, that is, we have to change the value at the ith index equal to v. So this is an easy thing, right? We don't have to worry about this here. This problem mainly focuses on this part, how we will implement this logic. And for each of this query, we also have to print the answer, that is the minimum index j. So if I explain you the example here, please see. So this is our array, right? So in the first query, it is 2, 2. That is, the value of x here is 2. For the whole array, we have to find the first index or the minimum index for which the value is at least 2. So if we start taking one by one from the very start of the array, so this is my first element and it is equal to 1, which is less than 2, right? So we will move forward. So now we are currently present at this, and the value of this element is 3, which is obviously greater than this x. So since in this array we wanted to find the element which is at least 2, that is greater than or equal to 2. So this is the first element in this whole array when we started traversing from the very start, which is greater than or equal to 2. So what is the index of this element? The index of this element is 1 here clearly. So that's why the output for the first query is 1. Similarly, in the second query, which is represented by this integer, the value of x is 5. So it means that we want to find the index of that element for which the value is at least 5, and it should be the minimum in the array.
Hmm.
So if you start traversing from here, then, so this value is equal to 1, it is less than 5, right? So it means that we will move forward. Now the value is 3, but it is less than 5. So we will again move forward. That we will again continue moving forward. And now we are at the last index, that is the fourth index. And its value now is equal to 6. And clearly our 6 is greater than or equal to 5, right? So the minimum index for which this query will give the output is the fourth index. So that's why the output for this query is 4. And now in the third query here, so this one.
So for that particular range, we need to store the maximum value, right? We need to store the maximum value for that particular range. But what if this is 4, this is 2, and we want to find the number 3? Yeah, then it should be max. What if for this range,
Present that the query is of the type 1, that is the point update. So in the second index, we have to replace whatever value present here before with
1, 2, 0, 1, 2, so this with 5.
5. So let me change this here. Okay, so the value of this array is now 5 here for this index, right? Let's move to the fourth query here. So in the fourth query, it is of the type 2. That is, we have to find the minimum index for which the value is at least 4. So if we start traversing from the start, then it is 1, which is less than 4. So we will move forward. And now it is equal to 3, which is still less than 4. So we will again move forward. And now the value is equal to 5, which is clearly greater than or equal to 4. So we'll stop at this point. And what is the index of this element? So the index is 2, right? So that's why the output here is 2. So in this way, we have performed this query now. Let us now move to this query. So now for this query, we have to find the index in this array. For now we are at the second, at least 8 and minus second query. So in this query, so let me do that quickly for you. Okay, so I have changed it now. So as you can see that this is the status of my current array after performing this query. And now let us perform the last query of this input. So for this query, we have to find the minimum index for which the element's value is at least 6. That is greater than, and now we again move forward. And now we will stop at this point. Why? Because this has a value of 7, which is clearly greater than 6. That is greater than or equal to 6. So in this way, we performed each question is not asking us to do very difficult things. It will use a very simple concept of segment tree here. And please keep in mind one thing, the solution that I will explain to you in the blackboard will be a general solution. That is, for this question if you have read, then it has asked us to find to you in the blackboard will be a general solution. That is, for this question if you have read, then it has asked us to find this condition, that is a of j greater than or equal to x for the whole array. That is, this j here can be any index from the starting to the end, right? But I will describe you a solution for which this j can vary. That is, you can even supply some range in the input from L to R such that we will only be allowed to pick this j from that range only and not the complete range. And that will be more general and moreover a good question over this, right? So in this question, the range is fixed here. That is, j can be any value in the index range, but if the input has given you such that you have to select a j in a range only, that is from L to R. So I will describe you that solution only, and by putting the value of L as 0 and R as n minus 1, you can just submit this solution and it will give the correct answer. I hope you got this point. And why I have decided to make a video on this question here, because this is a very standard question, and this concept will be used directly in many of the lead code problems and the contest problems. So that's why this concept is a very standard concept and it is applied in most of the problems. So let us now go to the blackboard and see how this question will be solved using segment tree. So I hope that you have tried to implement the brute force approach by yourself here. So I am not going to implement the brute force here because it is very easy to implement in this question and by video. So if you will understand why that will give clearly. So that's why I'll just discuss the optimal approach in this video. So if you remember, this was the given input in the problem and this was the expected output. So the array given was this. So let me write this array outside here clearly. So the array is one array, right? So how we will solve this question using segment tree? So we know that since we have to just write a query function which will return me the minimum index for which the value of the element is at least x, right? So we have to write the query function in the segment tree template. And we know that whenever we write a query function, we always start from the root node of the segment tree. And please keep one thing in mind that we know that our total number of nodes present in the segment tree is 4 times the number of total nodes in the array. So here since n is equal to 5, so the total number of nodes that should be present in the segment tree here should be 20. But I have only drawn a total of 9 nodes here. That is, and I think these 9 nodes should be sufficient in answering the answer for each and every query. And other nodes will only act as the redundant nodes and it will not contribute to our answers. So that's why I have not drawn that. So now what I was saying was, we know that for each and every query function, we always start from the root node of the segment tree. And this is the root node. And the nodes that I have marked green color with in the side, so those nodes represent our base level or the leaf level. And each of these leaf nodes represent just one single element of the given array, right? So this represents the 0th index element, this represents the first index element, this represents the second index element, this represents the third index element, this represents the fourth index element. So this is the basics, we know it already, I guess. And now since we want to calculate the minimum index for which the value will be at least x for a given query, so now what I'm telling you to do is, I guess you must have studied how to find the maximum in a range for using a segment tree, right? So we know that when we want to find the maximum in a range, so how we used to build the segment tree for this? So it is very simple. So we recursively travel to the left part of the tree and the right part and then combine the left and right results into the parent each and every time, right? So we know this. So let us do the same thing here also, and you will very soon realize that how finding the maximum for each and every range here in this nodes will help us in answering each and every query. So let us do that quickly here. So since this is 3 and this is 1, it means that the maximum for this range, that is this 0 to 1 range, should be equal to the maximum of the left child and the right child, which is 3 here. So this will be 3. Similarly, the maximum of this left child and this right child will be the maximum of this. That is maximum of 3 and 2, which is 3 obviously. So this will be 3. And once we have explored the left part completely, now we will go to the right part. So now we are present at these two nodes. It will now find the maximum of this part and this part. So it is 6, right? So it means that once we have got the result of this left and right child, we will combine this into the root node. That is the parent node of these two nodes. So what is the maximum of this 3 and 6? It is 6, right? So I'll write here just 6. So in this way, we have built our segment tree from the bottom to the top such that each node is storing the maximum of that range. That is the maximum element present in that range in this array. You can verify this also. So I think I filled this correctly here. And now, as I was telling you before, that since in this question we just have to write a query function that should be capable of answering each and every query, right? So we know that for every query function we always start from the root node of the tree. So now let us finally start doing the procedure here. So now we are standing at this root node, and this is the range here for this root node, which is from 0 to 4. That is the whole array. And for this whole array, the maximum element is 6. So for this range, the maximum element is 6, which is here. So now let us perform each and every query one by one. This is the first query, that is 2, 2. It means that the query is of type 2 and the given value of x here is 2 also. So x is here 2. So as I have told you before, that in this question we have to find this minimum index j for this whole range. That is, this j can be between this 0 and this n minus 1, right? So there is no specific range given in the question. We have to find it for the whole array. That is our j value, that is the minimum index that we have to answer for each and every query, can be any value in this range. That is, we always have to check from the very start of this array and check one by one, which is the first element, which is at least x, right? So there is no bound on the left and the right part. So we have to check for the whole array here. So if I write that here, so it means that my L value is 0 and my R value here is n minus 1. Coming back to the problem, so I was telling you that we were standing at this node and this was the range, and for this minus here, is at least x. That is, we always have to check from the very start of this array and check one by one, which is the first element, which is at least x, right? So there is no bound on the left and the right part. So we have to check for the whole array here. So if I write that here, so it means that my L value is 0 and my R value here is n minus 1. Coming back to the problem, so I was telling you that we were standing at this node and this was the range, and for this range the maximum value was 6. So the maximum value for this range was 6, which was coming from here, right? So this was our first query, that is 2, 2. That is, we have to find the minimum index for which the element's value is at least 2 here, that is x. Just assume for a moment that instead of this x equal to 2, I was given to solve this x for x equal to 14. So what would be the answer for this query in that? That is, I would have wanted to find that index for which the value was at least 14 in this. But clearly, in this whole array, the maximum value was 6 only, and there is no value of 14. So if there is no index possible to find for a particular query, so in that case, the question has asked us to print minus 1, right? So if my x was 14 here in this case, then I would have just printed minus 1 because the maximum value present in the whole array is just 6. So there is no index for which the element's value will be at least 14. So minus 1. So that's why whenever we will be present at any node, at this current node, we will always check that what is the maximum value present in its current range. So since for this node here, the maximum value is 6 here, and since we wanted to find such element whose value is at least 2, it means that this range definitely contains some index, that is some base level index, for which the value is at least 2. Because the maximum value is 6 here, right? Maximum value for this range is 6. So there is definitely some index present in this range for which the value is at least 2 here. So it can either be present on the left part or it can either be present on the right part. We are not sure. By currently standing here, we are just not sure that whether to go to the left part or to the right part. Thereby, it means that we have to explore both the parts. So first we will explore the left part and then we will explore the right part. But, since we know that this node is represented by a value of node and the left child is represented by a value of 2 into node plus 1 and the right child is represented by a value of 2 into node plus 2, right? By currently standing at this node only, we can know the value of this node and this node, right? Since we want to find an element for which the value is at least 2, so by standing here only, before actually going
Okay. We check. Okay, we check our children left or right. Find out which element has the minimum value, or basically, yeah, which node has the minimum value and is within the range of X. Yeah.
to the left part,
And we traverse there.
we will check that what is the maximum value present in this whole left part, that
Yeah.
is in this range, which is present at this node, which is 3 here. So the maximum value present is 3, which is definitely greater than this X. So it means that there is some index in this range for which the value is at least 2, because the 3 is the utmost value for this range. So it means that it is feasible.
But instead of 4 here, there could have been a 2 here and a 4 here. Then this value would have been 4. This would have been 6. But the 2 is present here.
To go to this part, that is to the left part. So that's why I will go to this left, and now I am standing at this node. So again we will do the same thing as I did in this node, that is I will check what is the maximum value present in the current node for this range. So since this represents from 0 to 2 and the maximum value present in 0 to 2 is this 3, right? And we wanted X at least 2, that is greater than or equal to 2. It means that in these both parts there is some index for which the value is at least 2, right? But we are not sure as of now whether it is present in the left part or whether it is present in the right part. So that's why we'll go first to the left part. As I said here before in this case, that whenever we'll be standing at some current node, we will directly before actually moving determine if it is feasible to go this part or not. Similarly, since we were currently standing here, we will just determine by standing here only that if it is feasible to go to the left part or not. That is, the maximum value present in this range, we will check, and it is 3 here, and we wanted to find the index for which the value is at least 2. So it means that there is some index in this range here for which the value is at least 2. So this range, which ultimately represents these two base level indexes, contains some element which is greater than or equal to 2. So that's why it means that since I was standing here, I would definitely go and explore the left part, because I know that its value is 3. So there is some element in the base level for which the value is at least 2. So it is feasible to go to the left part. So that's why I will move to the left part now. And now, since I was present at this node now, we will see the range of this node. So it is 0 to 1, and the maximum value for this range is 3. And we want X to be at least 2, that is greater than or equal to 2. So it means that there is some index in this range for which the value is at least 2. So it is feasible to actually explore this part, right? But we are not sure by standing here that whether to go to the left part or to the right. So by standing here, we will first check if it is feasible to go to the left part. So that's why by standing here, I will check the node value of the left. So it is 1 here. So since the node value here is equal to 1, that is the maximum value present in this range is 1 only. But we wanted our X to be at least 2, which means that clearly we don't want to go to this part anymore. Why? Because this part, which represents the range from 0 to 0, has a maximum value of 1. So we will not get any index with the element at least 2. So that's why I will not go to this part. And even if I go to this part, I will return some value that will be ignored here. So now, after exploring this part and not getting any result, the only option that we are left to explore is this right child, right? And since by standing here earlier, we saw that there is some element in this range which has a value of at most 3, and that element is obviously not present on this side. So it means that it will definitely be present on this side, right? So that's why we will now explore the right part of this. So now I am standing at this node, and since now I am standing at this node, and for this node clearly it has a value of 3, which is greater than or equal to 2, and also for this node, this is a base level node. How we will know this? Because for this node, our start is equal to end. So if this is 2, then so it means that we have finally found that one index, that is the minimum index for which the value is at least 2 in this whole range here, which is this index, that is 1. So we will just print or return this. So that's why the output here is also 1. So in this way we are done with the first query here. Let me erase this now. Okay, so now I want to perform operation for the second query. That is, I want to find the minimum index for which the value is at least 5. So if you look here blindly, then in this array the minimum element for which the value is 5 is this element only, that is the fourth index. So that's why the output is 4. But how will we determine using the segment tree? Let's see. So as I told you that for each and every query we will only start with the root node only, because this is how the query function works. So now we are standing at this root node, and for this root node it represents this range, and the maximum value present in this range is this 6, and the value here that we want, so let me write here also. So now we want at least 5. So our X is 5 here. So since this range has a maximum of 6, so it means that this definitely contains a base level index for which the element value is at least X, that is greater than or equal to 5. So it may be present on the left part or it may be present on the right part. So if we are able to find the answer on the left part, then we will not need to explore it on the right part, because the question wants us to answer the minimum index. So it might be present on both the sides. That is, there can be some value which is greater than or equal to 5 and might be present on both the sides of this tree, but since we want to answer the minimum one, so that's why we will only go with the minimum that we found, and that's why we will not explore this other part. Okay, so now let us start doing this. So since I was standing at this node and it had a value of 6, it was greater than or equal to 5, so it means that there is definitely some node present either in this part or maybe in this part or maybe in both the parts for which the value is at least x. That is 5. So since we are not sure here, so we will try to move in both the parts one by one. But before actually moving to the left part, I will first check here that if it is feasible to actually go to the left part. And how will we determine this feasibility? So now the maximum value present in this range here is 3, which is represented and written in this node. So since this range has a value of 3, but we want such element which has a value of 5 at least. So it means that there is no element present in the base level of this part for which the value is at least 5. So all these values will be less than 5 here. So it means that it is not actually feasible to go to the left part. The only other possibility that we are left now to explore is this right part. So that's why now I will explore the right part of the segment tree, and I am standing on this node which represents this range, and it has a value of 6 here. So since this range has a maximum value of 6, it means that in the left part or the right part. So I will want to explore both the parts. But before actually exploring the left part, I will check if it is feasible to go to the left part or not. This represented node, and this represented 2 into node plus 1, and this represented 2 into node plus 2, as I told you before. So I'll just check here by only that what is the value of the left side. So since the left side has a value of 4, it means that the range that it is a part of has a maximum value of 4. But since I wanted that element which has a minimum value of 5 at least, so it means that if we so this has a value of 6, and since this has a value of 6 here, and I have reached this node successfully, and for this node clearly the value 6, which is greater than or equal to 5 here, see, then the output is also 4. So in this way, we did the second query also. Let us now move to the third query of this problem. So the third query is a point update. That is, we have to update the second index equal to 5. Some element present at the base level for this tree for which the value is at most 6, that is greater than or equal to 4. But we are not sure whether it is present in the left or the right part, so we will explore both the parts one by one. For this way, which is 5, will also change. Whatever segment change, will just return or print this point update. That is, we have to update the second index equal to 5. So since this third query is about the point update here, so here we have to change this 2 equal to 5. That is, this second index equal to 5 here. So I have changed this equal to 5, and now I also have to change this and update it in the segment here, right? So since our second index is located here, so that means I will change this 2 here equal to this 5. And by doing this, we know that whatever nodes are present in this path from the bottom to the top, those much nodes will also change. That is, I have changed this node already, so this will also change now, and this will also change. And since in each of the node I am just storing the maximum of these two, that is maximum of 5, 6, which is 6, so it will store 6 now. So in this way, I have updated the segment tree from the bottom to the top, and by doing this, I also have completed the third query. So let us now move to the fourth query here. So the fourth query is 2, 4. That is, our x value is now for the root node. What will be at least 8. Common sense, right? So even if you go to the left, maximum is 6. In this whole array, I want to find the minimum index for which the value is at least 8. But since this whole range here has a maximum value of 6, so it means that we will not get any index for which the element value will be at least 8. Common sense, right? So even if you go to the left part or even part or to the right, which is the maximum of 5 and 6, right? Since that is from 0 to you till now, to take the input of the type. Actually code this up. So in the input, we have to take the inputs how a lot of efforts to create each and every single video from my side. So I think it would be very better for us if we actually move to the coding part and actually code this up, and then you will understand each and everything how it is performing under the hood. And finally, whatever I said to you till now will actually make sense. So let us now go to the code editor and actually code this up. So in the input, we have to take the inputs of n and m, and then n integers, and then the number of queries, right? So and then the n integers. So this is my input of the array here, and now I have to actually iterate through the n queries given. So for each and every query, I first have to take the input of the type. That is whether it is an update type or a query type. So if my type is equal to 2, then it means that this is a query type, right? And if this is not the case, it means that this is what? This is the update type. So for this array, let me declare the segment tree here. So I've also pasted my standard segment tree template here, and we have to write this query function, right? So before doing that, let us fill these parts.
Okay, let's parse this question. Hmm. Public class this is static class segment tree int tree int n. Yeah, we should be good. So what do we have here? We have int n and n first int n equal to standing is equals to new system dot any c dot close c dot next int n equal to c dot next int. Now a long array equal to new long of size this for int I equal to 0 I less than n plus plus array of I equal to c dot next long. Now while m is greater than 0, We check what type this is. If it's of type 1, this is the update query. This is basically update. Else, this is find max. Find max. Right. Hmm. Before that, let's initialize this. Ah, this will be equal to n public segment 3 in 10 3 equal to new in this dot n equals to n, and then also build our segment 2 node start and end. Just send this dot end node and start and end. Yeah. So if start equal to end, tree of I equal to array of start, I is basically node, and then return. If this is not true, find the made start plus n divided by 2, then call the 2 plus node plus 1, call the left part recursively, then call the right part recursively, then update the node plus 1 plus 2 into node plus 2. Ah, this is wrong. Yeah. For public query, now let's write for update first. Why not? Void update. What do we have? We have int index, we have int value. We need to set that value. Update util. We have int. We have node. We have start. We have end. We have ldx and then value. Public void update util int node int start int end ldx into value. If start equal to end, what do we do? Um, no. To update, right? If this is equal to this, then tree of node equal to that value. If this, okay. Otherwise, we have int mid equal to start plus n divided by 2. If LAX is less than equal to mid, we traverse to the right, sorry, to the left side. So till from start till mid, else we traverse to the right side, and then at the end just update the value 2 times more plus 2, and we should be good. Now for query, public void query int left int right. Okay, and by the way, this should be math dot max of this value, of these two values, right? And while building this also, this should be the max value of these two. Yes, this makes sense. Okay, now for query, return query util. We need to return the index, right? Yeah. Hmm. Query will not have left or right, but rather query will have the value. So we have node, we have start, we have end index, and then we have value, but we don't have the range. So public int query util int node int start int end and int value. If start equal to end, if we ever reach that point, we need to return start, return this value, right? Else if, yeah, we will also need the range from left to right, and we need to find this will be 0 and range will be till n minus 1. else if get the minimum value, right? So if tree of 2 into node plus 1 is less than tree of 2 into node plus 2 and this value, now I want to go, towards the left subtree. So this is true and the value, this value is greater than 3 node plus 1. Then query dot util what int mail equal to start plus end divided start till mid else query util mid plus 1 till end. Do we even need? No, this is not even necessary. This is not even necessary. Don't even need this. R return math dot min of L comma R. Mm, wait. I need to go to the washroom. I will be back soon. Take to black. Okay, I am back. Let's figure this out. Yeah, I get it. Just fix the errors. Yes. Oh, how do I forget to do this? Okay, so into take util. Yes, to F3 node F3 node. If this value is less than value, then simply return what? Return -1. Yeah, if this value is greater than the tree node's value, just return -1. If start equal to end, return start. Yeah, this is correct. Into mid, this is correct. Left equal to okay. So only if this is not equal to -1, go to the right sub tree. And the value can be long, obviously. Of course, it's going to be long. Yeah, yeah, yeah. If L is not equal to -1, then return L. Otherwise, return return R. This is basically R. Go to the, let me just even write this. And R, return R. And to and R. Okay. Yeah, this makes sense. Great. And I received no output. Oh, mhm. Wait. If this is 2, int, what is this? X, right? X equal to sc dot next int. Wait a minute. X can be a of j. So it needs to be long. Long x equal to next long. Okay. Just a minute. Let me check something. Anyways. Huh. This. Long x equals to this. And then just vary this. T dot vary x. Int z. Result. If it's type 1, what do we do? We take in the indices, right? At this index, change the value to this. Int index equal to sc dot next int, int value equal to long value equal to sc dot next long. Yep. Now t dot update, and this will be value. This will be long. This will be long. I was strong. How am I going out of bounds? 31. L 60. This thing is annoying, nothing long. Of course, of course.
here. So we know for each query type, that is type 2, we will be given an integer x, right? So we'll say this, and for this we want to print the answer. So I will say t.query, and for each query I will pass three parameters, that is this x, the leftmost value L, and the rightmost value R. But as I told you that in this problem of the code forces reduce section, our L is equal to 0 and my R is equal to 1, sorry, n minus 1, so it will be this, right? And in the update query, we will be given two integers actually, that is the index which I have to update and the value with which I have to update. This index equal to this value of node. So if the current value, what we want, I want this current value to be actually greater than or equal to the x. But if it is somehow less than x, then it means that I will not explore this anymore, because whatever the maximum value present in this range is not even x, so we will not get any answer. So I just return a minus 1 here. And I also told you that there is some restriction by this L and R. So if you are given a particular range from L to R, then I will also check that if my end value is actually greater than or equal to L or not. So if my end value is less than L, it means that we will again not get any answer from this node. And similarly from this right part also, I want that this right should be actually greater than or equal to the start. But if this right is actually less than start, so I again not get any answer. So that's a minus 1 for all these three. And now if this is not the case, then it means that this is a valid node. So some answer is possible. So either we have reached the answer node, that is the leaf node, or we have to explore the further nodes. So I will just check if this is a leaf node or not. That is, if my start is equal to this end or not. So if it is equal, then I will just return the index here. Let's say end. You can also write start here, right? Because start is equal to end here. And even if this is not the case, it means that we have to explore both the parts. So I just find a mid here. And what is this mid equal to? It is equal to nothing but start plus end by 2 here, right? So start plus end by 2. If you have noticed that whenever we will be calculating the mid value for the current node, so for here mid is actually 0 plus 4 by 2, which is 2 only. So this mid value will be actually the end of this left child. So that's why I will say here that if my tree of 2 into node plus 1, that is the value of the left child, is greater than or equal to x, if my 0 plus 4 by 2, which is 2 only. So this mid value will be actually the end of this left child. So that's why I will say here that if my tree of 2 into node plus 1, that is the value of the left child, is greater than or equal to x. So one condition, that is the first condition on L, the first condition on the node value, and then the second condition should be on the L value. That is, if my mid is actually greater than or equal to L or not. That is, if my L is less than or equal to mid or not. So if my L is less than or equal to mid here, so this is the mid here, right? So since this is my mid here, that is 0, 1, 2, this is my mid. And since what I'm saying is, in this 0, 1, 2, if my L value is actually starting from this less than or equal to mid here, that is before this range. So it means that there can be some indexes possible, right? So we can't ignore that. So that's why I'm checking if my L is less than or equal to mid. So it means that there can be some possible answer in this left part. So we explore this left part. And whatever value it will return, I will just store this in a variable, let's say left operand value. So how we will explore this left part? So for doing this, we'll only call the same function again. So instead of this node now, it is equal to 2 into node plus 1. Our start will be the same as the start, but our end will now be mid, and my x, my L, and my R will remain same. If this value is not equal to minus 1, so this statement means that by exploring the left part, I've got some value which is not equal to minus 1. That is, I've got this value here. That is a valid leaf node index. So I just have to print that only, right? So I will say, or rather return this. So return this. And if this is not true, that is, after exploring the left part, things never went true. So it means that our answer can now be present in the right part only, right? And not the left part, because when we explore the left part, we got nothing. Since we got nothing, it means that the only option that we are left to explore is the right part. So that's why we just explore the right part like this. So this is how I will write this query function here. And I think I've done a very silly mistake here. So this will not be a comma, but this. And also I think I should give here an ender here, because every time I have to print the output on a new line. Let's run the code and see if this is fine or not. As you can see, the outputs are correctly passing. So this is the code that we just wrote. So now let us try to submit this code and let's see if this is getting accepted into the platform or not. So as you can see that it is accepted successfully. And so this is the code that we just wrote and submitted and got it accepted on the platform. So I really hope that you have understood the concept very well, right? So this is a small concept that will be used directly in most of the contest problems, right? So that's why it is very important to watch this video and understand what I have told you. And yes, if you're still watching and have not subscribed the channel yet, please consider subscribing. Okay, so hi everyone. So today in this video, we will be discussing about this interesting problem from Yusako's gold module that goes by the name, why did the cow cross the road?
Okay, cool. Huh. Oh. Mm. Well,
3, right? So this problem will utilize the concept of segment tree, and if you know how to do point update and range sum query, then you're good to go with this problem, right? And before starting the problem, if you have not yet subscribed the channel to segment tree and other harder topics, so yeah, if you have not yet subscribed the channel, please subscribe it. Now let's get back to the problem. The problem reads like this, that the layout of Farmer John's farm is quite peculiar, with a large circular road running around the perimeter of the main field on which his cows graze during the day. Every morning, the cows cross this road on their way towards the field, and every evening, they all cross again as they leave the field and return to the barn. So, as we know, that cows are creatures of habit, and they each cross the road the same way every day. So, each cow crosses into the field at a different point from where she crosses out of the field, and all of these crossing points are distinct from each other. So, Farmer John owns total n cows. So, this farmer has a total of n different cows, conveniently numbered from 1 to capital N. So, there are precisely 2n crossing points, right? So, a total of n cows, and thereby a total of 2nb as a crossing pair. If cow A's path from entry to exit must cross cow B's path from entry to exit, right? Please help Farmer John count the total number of crossing pairs. So in the input, we will be given an integer n, that is the total number of cows, and then 2n lines describing the cow IDs for the sequence of entry and exit points around the field. And in the output, we just have to print the total number of crossing pairs. So this is our input. So for this given input, let me zoom this a bit. So our n value is 4, that is, there are total of 4 cows. And since there are total of 4 cows, then it means that for each cow, there will be 2 points. That is one entry point and other one is the exit point. So a total of 8 points given, right? So as you can see here, that this 3 can be the entry or the exit point for the third cow. Similarly, this 3 can also be the entry or the exit point for the third cow. So if this is the entry point, then it will be the exit point and vice versa. And the same thing is given for every cow from 1 to 4. And the expected output for this example is just 3. So this is the question. So let us now go to the blackboard and try to understand what does this question is trying to tell and how the output is coming 3 for this example. So let us now go to the blackboard. Okay, so this was the example given in the question, right? There are total of 4 cows in this example, and since there are 4 cows, we are also given 8 distinct points in total, and the expected output for this example is 3. So let us first try to understand that what does this array represent here. So this array represents the order of the cows on which they will enter the field one by one and leave the field. So there is some kind of field on which the cows wants to graze, right? That is graze the grass or something. So this 3 means that initially the field was empty, right? But then this third cow enters the field. Similarly, after this third cow, this second cow enters the field. And after this, the fourth cow enters the field. So at this point currently, if I say, then third cow is present, 2 cow is present, and fourth cow is present, right? And then after this, the fourth number, that is the fourth cow, is also written again in the array. So since we already encountered 4, and there is 4 once again here, so we can imagine it something like, whenever we will encounter a number for the first time, so we will interpret as that cow will be entering the field for the first time. And similarly, when we will again encounter that number which we have already encountered before, then we will interpret this second time number as the cow will be leaving the field at this time, right? So for this, we will interpret this element like the entry point for the fourth cow and the cow. And similarly, when we will again, and this point currently, if I after that, there is some kind, so this array represents the order of the cows on which 4 cows in this example. So this is the question. Let us now go to the blackboard. Okay, so this was the example given in the question, right? There are total of 4 cows in this example, and since there are 4 cows, we are also given 8 distinct points in total, and the expected output for this example is 3. So let us first try to understand that what does this array represent here. So this array represents the order of the cows on which they will enter the field one by one and leave the field. So there is some kind of field on which the cows wants to graze, right? That is graze the grass or something. So this 3 means that initially the field was empty, right? But then this third cow enters the field. Similarly, after this third cow, this second cow enters the field. And after this, the fourth cow enters the field. So at this point currently, if I say, then third cow is present, 2 cow is present, and fourth cow is present, right? And then after this, the fourth number, that is the fourth cow, is also written again in the array. So since we already encountered 4, and there is 4 once again here, so we can imagine it something like, whenever we will encounter a number for the first time, so we will interpret as that cow will be entering the field for the first time. And similarly, when we will again encounter that number which we have already encountered before, then we will interpret this second time number as the cow will be leaving the field at this time, right? So for this, we will interpret this element like the entry point for the fourth cow, and we will interpret this point as the exit point for the fourth cow, right? So that's why when I was standing at this point, we had third cow, second cow, and fourth cow in the field. But as this fourth was written again, so we interpret as that this fourth cow will now leave the field. So this fourth cow will now leave the field, and only third and 2 cow will remain. So now this fourth cow will leave the field. And now after this, we are present at this element. So at this element, since first is coming for that first time, then I will write here 1. That is, in this field currently, there are 3 cows. That is the third cow, second cow, and the first cow. And similarly, if we move forward now, that is at this element, then we encounter third cow. But since we have already encountered third cow before, it means that at this point, the third cow had entered the field, right? But now at this point, the third cow is trying to exit the field. This is at this element is so that will be entering the field for the first time. And similarly, when we will again encounter that number which we have already encountered before, then we will interpret this second time number as the cow will be leaving the field at this time, right? So for this, we will interpret this element like the entry point for the fourth cow, and we will interpret this point as the exit point for the fourth cow, right? So that's why when I was standing at this point, we had third cow, second cow, and fourth cow in the field. But as this fourth was written again, so we interpret as that this fourth cow will now leave the field. So this fourth cow will now leave the field, and only third and 2 cow will remain. So now this fourth cow will leave the field. And now after this, we are present at this element. So at this element, since first is coming for that first time, then I will write here 1. That is, in this field currently, there are 3 cows. That is the third cow, second cow, and the first cow. And similarly, if we move forward now, we'll be standing at this point. So the cow number that is present at this index is the second cow. But since we have already encountered 2, the next time we encountered it is the exit point for the second cow, right? So that's why this 2 will also now exit the field. And finally, when we move to this point, then it is equal to 1. And since we have already encountered 1 before, then it means that that before point was my entry point for the first cow, and the next point is my exit point now. So this one will also exit the field now. That is returned to the barn from where they had come. So this one is also gone now. So in this way, each of the cows, that is first cow, second cow, third cow, and fourth cow, entered this field one by one and then moved out one by one. So initially the field was empty, and after this array operation has been performed, the field is again empty. So I hope you have understood how this array is actually working in terms of field, right? So now let us get back to what the problem actually wants us to calculate. So the problem wants us to calculate this integer. But wait, what is this integer actually? So if you have read the problem correctly, then here the definition of that integer is written. So we have to output the total number of crossing pairs. So that's why this integer represents nothing but the total number of crossing points, or rather crossing pairs, right? So what does this total number of crossing pairs or this crossing pairs mean here? So the definition of a crossing pair is written something like, he calls a pair of cows A comma B as a crossing pair of cow. So two different cows are called as a crossing pair if cow A's path from its entry to its exit must cross cow B's path from its entry to its exit. So it might be a little confusing for you at the first glance. So let me explain you the same thing in the board only. So suppose I am talking about a cow. Let's say I'm talking about the X cow here and the Y cow, right? So suppose the entry point for the X cow and the Y cow are like it entered the field, that is the X cow entered the field at A time, and similarly the Y cow entered the field, let's say at C time. Right. Similarly, if I want to write the time at which this X cow left the field, then let's say it was B. And similarly, if I want to write the time at which this Yth cow left the field, then let's say it is equal to D. So I hope you understood this. So this X cow entered the field at Ath time and left the field at Bth time. Similarly, this Yth cow entered the field at Cth time and left the field at Dth time. So according to question, these two cows will be called as an intersecting pair if and only if the following condition holds. That is, A will be less than B, right? But before the X cow left the field, the Yth cow enters the field. That is, this C will be less than B, and then D will be here. So this is not very hard to understand actually. So what does this mean? It means that when X cow entered the field here at time A, and it is leaving the field at time B, but before actually leaving, the another cow with entry time C actually entered the field. So if this condition holds, it means that these two different cows are actually intersecting pair, and we have to actually calculate these much number of pairs only. So I hope you understood the definition of interfacing here. So in this case, we will say that these X and Y cows form a crossing pair. That is, these two cows are crossing each other's paths, right? So this X cow and Y cow are considered now as a crossing pair. So let us see now why the output is 3 here. That is how the number of crossing pairs for this example is 3. So as I said that for each of the cow, that is for the first cow, second cow, third cow, and fourth cow. So let us see for each of the cow how many crossing pairs will they be a part of. That is, let us first talk about this third cow here. So since this third cow is entering the field for the very first time, this 3 is in the field, and then this 2 will come in the field, and then this 4 will come in the field. But after this point, this 4 will left the field. So the first time we encountered a number, that is the cowth number, for the first time, it means that that cow had entered the field at that time. But if we again encounter that number that we have encountered before, it means that it is now exiting the field at equal to 4, right? So it entered the field here and then it is exiting the field here. So according to the definition of crossing pair, I told you, so as I said before, that if between this another cow enters the field, that is this condition, then I will consider these two cows as a crossing pair, right? Similarly here, since at t equal to 3, the fourth cow have entered the field, and at t equal to 4, this fourth cow is exiting the field. So we want to calculate how many such pairs are satisfying this condition here. So if you see carefully, then here, this fourth cow actually entered the field at t equal to 3, then the next moment only, that is at t equal to 4, that is the next second or the next minute you can imagine, the same cow exited the field also. That is, in between these, there is no cow present other than the fourth cow, because there is no cow entering the field after t equal to 3. So let me explain again what I'm trying to say here. So since at t equal to 3, the fourth cow entered the field, and at t equal to 4, the fourth cow exited the field. So in between these two time intervals, there is no cow which other than 4 which entered the field, right? So since there is no cow other than this 4 in this range, that is between 3 and 4, which entered the field after this 4, so that's why the number of pairs that this 4 will form with that other cow which is not present here obviously is 0. So if I write here, then this 3 will be equal to 0 first, as the field and now exited the field. So there is no existence of fourth cow in the field as of now. So this fourth cow has gone completely from the field. So when this next cow will come to the field at t equal to 5, so according to this cow, this fourth cow should not exist in the field at all, because it has already come and left before, right? So this cow will never be able to see the fourth cow. Imagine it something like this, right? So now this first cow has now entered the field, and since this first cow has entered the field for the first time, so there is no problem, right? So we will move forward. And now if we move forward and reach this element, that is at t equal to 6, then at t equal to 6, we encounter the third cow again. But since we have already encountered the third cow at the very start, that is at t equal to 1, so it means that the third cow has entered the field at t equal to 1, and now it is exiting the field at t equal to 6. So since this fourth cow is gone now, let me mark that also. So this fourth is gone completely. So now what I'm saying is we are standing at the sixth index, that is t equal to 6. So since we have already encountered 3 before, so that's why now we want to calculate how many C's are there that can be substituted here. A is equal to that field. So we just check this cow has this second cow now. So that is at t equal to this age. That cow has entered the, then we moved ahead, then again is present in the field. And now when we move to this, no more present in the field. Hope you are getting what I'm trying to say. That is, lie between two. This way, the second cow will also will completely become. We'll do this now. And how does the segment tree will help here in this case? Okay, so now let us see what will be our approach to this problem. So here I have considered a map here, that is int comma int. So the first integer will represent the time of entry equal to 2 equal to map, and my b here is 4. So that is the number. So at this go to the code editor and actually code this up. So in the input, if you remember, the input for this 2 and 0, there a map here. So I will be using cow id, right? And has left the field successfully, so we don't need its information anymore. And once this is done, we just have to print the result like this and return. So in this way, I think the whole code will be written, and let us run the code to see if this is working fine or not. So as you can see that we are getting correct answer for this test case. Okay, so hi everyone. So welcome back to this new video in this segmentary series. So today in this video, we will be discussing this harder problem from Code Forces Div 1 round 225, and this problem is rated 2000. So before starting this problem, if you have not yet subscribed my channel, please consider subscribing, because I'm already creating a lot of amazing content for you guys, and I have planned to upload more and more videos related to segmentary problems, including lazy propagation, segmentary beats, and other harder versions of the segmentary, right? So yes, if you have not yet subscribed, consider subscribing and share with your friends who need to watch this videos to gain confidence in this topic. So let us now come back to the problem. So the problem reads like this: Lahab likes trees very much. Recently he discovered an interesting tree named as propagating tree, right? So the name of the question is also propagating tree only. The tree consists of n nodes numbered from named as propagating tree, right? So yes, if you have not yet subscribed, consider subscribing and share with your friends who need to watch these videos to gain confidence in this topic. So let us now come back to the
Why we lifting plus KPM trees?
problem. So the problem reads like this: Lahab likes trees very much. Recently he discovered an interesting tree named as propagating tree, right? So the name of the question is also propagating tree only. The tree consists of n nodes numbered from 1 to n, and each node I having an initial value of a of I. So the root of the tree is node 1. So node 1 is the root. And this tree has a spatial property. That is, when a value val is added to a value of node I, the value minus val is added to the values of all the children of node I. Note that when you add value minus val to the child of node I, you also add minus of minus val, that is plus val, to all children of the child of node I, and so on. Look at an example explanation to understand better that how it is working. So this tree supports two types of queries. So the first query is of this type. So we will be given two values, that is x and val, and what we have to do, we have to go to the node x of the tree, and in that node we have to add this value val, and when we will add this value to that node, we also have to add minus val, that is this, to the child of this node x, and then we also have to add plus val to the child of this node x, and so on. That is, we have to continue adding this value val in alternate fashion, right? So this is the first query, and this is the second query. And in the second query, we will just be given an integer x, and we have to do nothing, but we just have to print the current value of the node x. So in order to help Lahab understand the tree
No, no, no.
better, you must answer m queries of the preceding type. You have to print the current value of the node x. So in order to help Lahab understand the tree better, you must answer m queries of the preceding type. That is, we have to answer the queries of this type only. So in the input, we will be given two integers, that is n and m, that can go up till 2 into 10 to the power 5. And the second line contains n integers, that is the initial value of the nodes of the tree. Obviously, the tree is rooted at 1, right? And each of the next n minus 1 lines contains an integer vi and ui, that is representing an edge between the nodes ui and vi. So these n minus 1 lines will help us to form the tree, that is the given tree. And then in each of the next m lines contains a query in the format described above. That is, we will either be given this or we will either be given this. And if we are given this query, then we have to print the answer, that is print the current value of the node x. And for each query of the type 2, we have to print the answer to the query on a separate line. This is the problem given, and this is the given example here. So this is our input and this is the required output, and here is the explanation for this input. So let me zoom this a bit. So in this input, we are given a total of 5 nodes and 5 queries. And for each of these 5 nodes, we are also given the initial values like this, that is 1, 2, 1, 1 and 2. And then we are given n minus 1 lines, that is 4 lines. So each of these lines represents an edge between the two nodes. That is, a bidirectional edge is present between 1 and 2. Similarly, a bidirectional edge is present between 1 and 3, and so on. Finally, we are given with this m lines of queries, that is total 5 queries, right? And each of these queries are either of the format 1 type or 2 type. So whenever a query will be of the 2 type, then we have to answer this query. So that's why, since there are a total of 3 queries of the 2 type, we are also given 3 integers in the output. So this is the question. Let us now go to the blackboard and see how the output is coming for this given input. So let us now go to the blackboard. So this is the given example in the question, and in this question we are given a total of 5 queries like this. So the first 2 queries are of the type 1 and the remaining 3 queries are of the type 2. And this is also our given initial tree in which the node 1 is the root node, which initially has a value of 1. Similarly, these green values represent the initial values of each of the nodes in the tree. So the first node is having a value of 1, the second node is having a value of 2, the third node is having a value of 1, the fourth node is having a value of 1, and last, the fifth node is having a value of 2. So this is the initial condition of the tree. Let us apply each of these queries one by one. So in the very first query, it is of the type 1. What we have to do in the first query? So since it is of the type 1, in this query, the value of x is 2 and the value of val is 3. Right. So what does it mean? It means that we have to go to the second node of the tree. So in this tree, where is the second node located? So the second node is located at this part, right? So this is my second node, and in this node, what we have to do? We have to add a value of plus 3. If I add a value of plus 3, then what will happen? See, I am adding a value of plus 3 to this node because it is instructed in the query to do. But if you have read the question, then by doing this, it is not enough. That is, we have to propagate this addition. So since we added a plus 3 to the second node, it also means that we have to again add a minus 3 to the child of the second node, just like this. And since these two nodes are the leaf nodes of the tree, that is, we cannot propagate these values any further, right? So it means that we will stop now at this point, and thus this query will end here. So in this way, our first query will be done. Now let us move to the second query. So in the second query, it is also of the type 1, and in this, the value of x is 1 and the value of val is 2. That is 1, 2. So since x is 1, it means that we have to go to the node 1 of the tree. So in this tree, where is node 1 located? It is located at the very top. That is the root node. This is the first node, and in this node, we have to add a value of plus 2. So if I add a value of plus 2, so it will be this, right? But what we have to do next, we also have to add a value of minus 2 to the child of this first node. So I will write here a minus 2 for both of these childs. And since this node has not any childs further, so we will stop at this point. But since for this node, it has two childs on its both sides, so it means that we further have to propagate this value. So that's why, since I added a value of minus 2 here, so it means that for these two nodes, I have to add a value of plus 2 instead. That is, here plus 2 and here also plus 2. And now since it has not any childs further, so we will stop now. And in this way, our second query will also be done. The first two queries of the type 1 is done. Let us now move to the third, fourth, and fifth queries. So in the third query, it is of the type 2, and the value of x is 1. That is, we have to actually print the value of the node x, that is node 1. So in this tree, this is our node 1, right? What is the value of this node 1 currently? So it is equal to 1 plus 2, that is 3. So I can say that the answer to this query should be 3. Alright. Now, this query is done. Let us now move to this query. So in this query, we have to find the value for the node 2. So since this is our node 2 here, so we have to print its value. So its value is what? It is equal to 2 plus 3 minus 2. So these 2 will cancel out each other and only 3 will remain. So I can say that answer to this query should be 3. So I will write here 3 again. And now, if I discuss the last query of this input, then it is 2, 4 minus 2 plus 2. That I've looked in the question, then the output is, so this will be my output, right? And if you have looked in the question, 3, the output is 3, 3, 0 only, right? So it means that our output is definitely correct. So in this way, the queries will be performed one by one, as I just told you. So I am sure that you must have understood the question and how the queries are being implemented in this tree one by one, and how the outputs are coming for each of the second queries. So before coming to the approach to solve this problem, there are a few things that you should must know beforehand, right? So let me discuss one of those things here. I will now discuss the concept of Euler tool. So let us now understand what is Euler tool and how it works, and why I'm discussing this concept here, because it will be used in this problem. So let us now go and understand the concept of Euler tool. So what is Euler tool? So Euler tool is nothing but a technique we generally use in tree-based problems, in which we represent the given tree into an array, right? So this is Euler tool. So we represent tree-based problems in which we represent the given tree into an array, right? So this is Euler tool. So we represent a given tree into an array. So what does it mean actually? Let me tell you. So this was our given tree, right? And these are the initial values present on the tree nodes, right? So now, as I just said you, that what is Euler tool? In Euler tool, we represent a given tree into a form of array. And why we do this? Because it is generally more easier for us to make operations on an array rather than doing it directly on the tree. For example, suppose you are being asked to find the GCD value of each and every node present in the subtree of 2. So you know that you cannot directly start from here. So it will be a little difficult for you to do this of each and every rather form of array, right? So now, as I just let me tell you, so this was our given tree, right? And these are the initial values present on the tree nodes, right? So now, actually, let me tell you, so this was our given tree, right? And these are the initial values present on the tree nodes, right? So now, as I just said you that what is Euler tool? In Euler tool, we represent a given tree into a form of array. And why we do this? Because it is generally more easier for us to make operations on an array rather than doing it directly on the tree. For example, suppose you are being asked to find the GCD value of each and every node present in the subtree of 2. So you know that you cannot directly start from here. So it will be a little difficult for you to do this operation directly for this subtree. Apart from GCD, you can be asked anything to do, like the sum of this part or the minimum or the maximum or any other operation. Right. So in that case, it is little difficult to do it directly on the given subtree, right? So that's why we try to represent the given tree into a form of array, because after doing these many lectures on the segment tree, we know that it is relatively easier for us to calculate the minimum or the maximum or the GCD or any value in an array in a certain range using a segment tree, right? So for us to calculate the minimum or the maximum or the GCD or any value in an array in a certain range using a segment tree, right? So that's why we try to represent the given tree into a form of array. And once this is possible, we can calculate any value related to a subtree, and I will show you how. Since I told you that this tree will be represented in the form of an array, so what will be the size of this array? I will discuss a particular type of Euler tool in which each node of the tree is visited exactly twice, right? And since I will be using one page indexing here, so that's why since the total number of nodes given in the question is n, so I will take the size of my array as 2n plus 1, right? So if I write the array here, so this will be my array here. So this is my Euler tool array, right? And since I'll be using one page indexing here only, so that's why this 0th index will be of no use for us. We will only start from the first index. So what we do in Euler tool actually is, so we will start from the root node here, and first we will travel to the left part, and then we will travel to the right part. And the first time we enter the node, we write its value in this array, right? Similarly, the last time we enter this node, that is the second time, that is the outgoing time, we again write its value in this array. So for this tree, if I start from this root node, then it has a value of 1 here, right? So that's why I will write here 1. And now I will move to the left part. And since I am entering the second node for the first time, it has a value of 2, so I will write here 2. Similarly, as I move to the left part again, I will reach the fourth node for the first time, which has a value of 1. So right here 1. And now what will happen? Since I cannot go here any further on both the sides, so I will return back. That is, I will backtrack. So it means that I am now leaving the. And now as I move to the left part again, I will reach the fourth node for the first time, which has a value of 1. So right here 1. And now what will happen? Since I cannot go here any further on both the sides, so I will return back. That is, I will backtrack. So it means that I am now leaving the fourth node. And since I am leaving the fourth node, and I will not return to this fourth node again in the future, so it means that I again have to write its value in this array. That's why I will write 1 again here. And now I will be standing at the second node. But since I have not yet explored this part, so it means that now I will be standing at this node. And since I have reached this node for the first time, which has a value of 2, so I will write here 2. So this will be 2. And now again, I will backtrack, right? That is, I will not return to this part again. So since I am returning back, which has a value of 2 here, so I will again write 2 here. So 2. I will not return for the first time, which has a value of 2, so I will write here 2. So which has a value of 2 here, so I will again write 2 here. So 2. And now I will be standing at this node. So since I am standing at this node, and I will never in future return to the second node, so it means that I am going out of this node. So since it has a value of 2, so I will directly write here 2. So it will be 2. And now I'll be standing here again, and since I have completely explored the left part, but I have not yet explored the right part, so I will now go to the right part. So now I will come to this node. So since I'm coming it for the very first time, so I will write this one here. So this will be 1. And now since I can't go any further, so I will backtrack. So since I'm backtracking and I will not reach this node again, so it means that I have to write its value again in this array. And now after backtracking, I'm finally standing at the root node. And since I have explored both the left and the right parts here, I will finally backtrack like this. That is, I'll finally leave this first node. So since at the very first time I entered this node here, and now I'm leaving this node, it means that I again have to write its value here. So I will again write 1 here. And I think I have to go one extra size, so let me erase this. So this will be the status of my array after completing the Euler tool. And obviously this array is of the size 2n plus 1 only. That is 2 into 5 plus 1, that is 11. That is from 0 to 10. Right, so 0 to 10. So this is my Euler tool array. So now, how this array will benefit us now? So now someone if asks you to find the sum for the subtree of this node 2, that is this tree, then how can you answer the same thing using this array now? So now how will you answer this question? That is the subtree sum for the second node. And you have to answer this question using this array now only. So since we know that we entered this second node here, right? We mark it. So we entered the second node here, and also we exited the second node where? So we exited the second node at this point. That is here. So it means that whatever node values are present in this range, it will only comprise of those node values that are present in this subtree. That is the subtree of 2. You can look also. So these two values represent the second value for this node, which is this 2. Similarly, these two values represent this value. And similarly, these two ones value represent this value. So each and every node present in the subtree of 2 is present in this range twice, right? So now if someone asks you to find the subtree sum of this subtree, that is the second node, so it should be equal to 2 plus 1 plus 2, that is 5. And if you also took the range sum of this range, so it will be equal to what? So it will be equal to 10. That is 2 plus 1 plus 1, that is 4, plus 2 6, plus 2 8, plus 2 10. And why this happened? Because each and every node was coming twice, so that's why the values also got added twice. So whatever the range sum we got here, that is 10, just divide it by 2. So what we will get? We'll get actually the subtree sum, which is of this subtree. So in this way, this Euler tool array can help us in many ways in order to do the subtree operations for a given tree. So now we know the use of this Euler tool array here. So we know this now. But how will you know that for the second node we entered at this index, and for the second node we left it at this index? How will you know this? In order to solve this problem, that is to find the entry and the exit points in this array for a particular node, we use another two arrays. So the first array that I will use will be used in order to determine the entry time for a particular node, right? And I will name it as in time, let's say. But instead of holding the initial values, what does this array will hold? It will actually comprise of the entry time for each and every node. So if I draw it here, so now since I have filled my Euler tool array here like this, and now I want to determine the entry time.
I think I'll need a break. I'll come back soon. Fake that. Yeah, bye.
time and the out time for a particular given node x, right? So how can we do this? So it is very simple actually. So what I will say is, when I had started from the root node, I will actually increase my timer by 1 every time we visit another node. So initially our timer value will be equal to 1, right? So when we are present at this node, that is the first node. So I will say here that for this first node here, since I'm present at the first node here, so I will say that the value that this array will contain now will be equal to 1. That is, the timer value will be equal to 1. And now I will move to the left part, and now I'll be standing at the second node. And since I'm standing at the second node, so I will say here that in the second index, the value of timer will get increased by 1. So since it was 1 before, so now it will be equal to 2. So it means that this value will be equal to 2 now. So you can imagine it something like, we are present at this node at t equal to 1, and then we are present at the second node at t equal to 2, and then we are present at this fourth node at t equal to 3, just like this. So that's why, since from this node I move to this part here, that is the fourth node, which is located at this index. So that's why I will write here 3 now. And now my timer value will increase to 4. So what does this array is holding? This array is holding the initial time, that is the in time for each and every node. But since now, for this node, I have to also backtrack, that is, in time is done here, but now I also have to fill the out time for this array, right? That is, at what time I actually reverted back from this particular node. Similarly, at what time I will revert back from this particular node, and at what time I will revert back from this particular node. So since we also want to fill the out time in the same way as the in time, and this out time will help us in order to determine this index, that is, the second time we left the particular node. So now we want to determine this index. So what is this index? This is my in time, and this is my out time, right? So that's why we will also consider another array just like this in time, as I told you before. So this is my in time array, and this is my out time array. When we wrote these 3 here, we were present at this node, right? So we started from the root node at t equal to 1, so we wrote here 1. Then we reached the second node at t equal to 2, so we wrote 2 here. And then we reached this fourth node at t equal to 3, so we wrote 3 here. But now since we are moving out of this fourth node and will not return back to it, and now we know that after writing this value here, the timer value is increased by 1. That is, the timer value is now equal to 4. So that's why the out time for this fourth node in this out time array here will be equal to 4. So it will be 4 here. And now I will be present at this node. So since I am entering this node for the first time, so I will write will be equal to 4. So reached by 1. That is, the timer value is now equal to 4 and will not return back to it. And now we know that after writing this value here will be equal to 4. So it will be 4 here. And now I will present at this node. So since I am entering this node for the first time, so I will write here in this in time array that its value will be equal to 5, because every time the timer will increase by 1. And now since I have to leave this fifth node here, so that's why in this out time array at this index, I will again write the value of increased timer. So it will be 6 now. And now after exploring both these left and right parts, I will be standing at this node again. And since I have to again go from this node to the upper side, and I will not return to this node again, that is, I'm going out of this node. So what will be the out time of the second node here? So it will be 7 now, because every time the timer value is getting increased. Right? You can
7.
imagine it like a ticking clock. And now once the left part is explored completely, I will move to this part. So now I'll be entering this node for the first time. That is the third node. So we have to fill this point here. So it will be equal to 8, right? And now since I have to leave this node, that is, I have to get out of this node here just like this. So I have to fill the out time in this array here at this index. So it will be equal to
9.
what? It will be equal to 9. And then finally after doing this, I'll be standing at
Basically, we have the range queries 8,9, 3,4, 2,7, 5,6. These are the range queries that we have.
this node again, and since I have explored both the parts, it means that I have to go out of this first node ultimately. So since I am going out of this node, it means that I have to fill this value here. So it will be equal to what? It will be equal to 10, because before my timer value was 9. So as you can see that only these much indexes are getting used and not these much, right? So it is not necessary to take the size of these two arrays, that is the size of in time and out time array, as the same size as of this Euler 2 array, right? So this is not necessary. You can just take it of the size as n plus 1. So since my n was 5 here, so 5 plus 1 6. So that's why I'm able to access the 0 to 5th index easily. So this will be sufficient. You don't need to take the whole size, right? So now let us come back to the problem what we are doing. So as I was telling you before, that since we wanted the subtree sum of the second node here, so we wanted to determine this left index and right index, right? That is the entry time for the second node and the out time for the second node. So if you look here in the in time array, then in this in time array, the value of the second node is equal to 2. So it means that in the second node, we entered it at t equal to 2. That is this index. So in this way, we will be able to determine this left index in this Euler 2 array. And similarly, since we want to also determine the out time for the second node, so we will look at the second node here, that is the second index, which has a value of 7. So since it has a value of 7, it means that we exited this second node at t equal to 7. So if you look in the 7 index in this array, which is located here, so in this way, I will be able to determine the right index of the second node in this Euler 2 array. So that's why these two arrays, that is the in time and out time array, are helping us with nothing, but just to determine the left and the right index in this Euler 2 array. And once we are able to determine this, that is the left index and the right index in this Euler 2 array, we just have to take that particular range and perform whatever given operation the question wants us to perform. So as I told you before only, that if I want the subtree sum here, so just take the subtree sum of this range and just divide it by 2, right? So since every node was coming twice in this range, so that's why I'm dividing it by 2. And whatever we will get will be the subtree sum for this particular subtree. Similarly, you can also be asked to perform any other operation in this subtree range, right? So this is the whole concept of Euler 2 as I just described you with the help of these 3 arrays. And I'm very sure that you must have understood it because I could not have explained it any better. This is the simplest explanation of Euler 2 that anyone can give you with these pretty visuals. And since this was the only given tree in the input also, so that's why these 3 will be used very soon. So I will not erase this. So let us now go back and see what the question was asking us. And if you have read the question correctly, then what is this first query is actually about? So it wants us to add a value to this node x, right? But actually we know that it is not about just this node x. Actually we have to do it for the whole subtree of this node x in alternate fashion, right? So since it wants us to add this value in alternate fashion for this whole subtree of this node x, so notice the word subtree. That's why I taught you this concept of Euler 2, right? Because now we know that whenever we are asked to perform a subtree operation particularly, then this Euler 2 concept is very useful because by using this Euler 2 we can simply convert this given tree into an array and just perform the range query as required. So now what I'm saying is, if the question had asked us to not do it in alternate fashion, that is just add this 2 value, that is +2, to each and every node of this subtree here, that is +2 here, +2 here, +2 here, +2 here, and +2 here. If the question had asked to do this, then what we could have done in that case, then it would be a very simple task actually. So since we knew in that case that the entry time for this one was 1 and the out time for this one was 10, so in that case we will have just took this range that is from 1 to 10 and simply increased each of these values by a +2. So I would have said that t.update from 1 to 10 I want to increase by a value of +2. So it would be a very simple task. But now the question don't want us to actually increase each and every value in a particular range by a common value, right? So for some indexes it wants us to increase by a plus value, and for some indexes it wants us to increase by a minus value. So this is why this problem is a little good problem other than a normal Euler 2 problem, right? If you have solved these 3 problems before, and I also made a video on a question named as Zania and bit operations. So in this question also we were asked a similar thing, not actually similar, but yeah. If you remember, then in this question for some of the levels of the segment tree we were asked to calculate the XOR value, and for other levels we were asked to calculate the bitwise XOR value, right? So what we used to do in that case, we actually used to take the help of the height of the nodes, and by using the height of those nodes we are able to determine whether to perform either the bitwise OR or the bitwise XOR for a given range or a given level, right? So that's why whenever we will be asked to do something alternately, because in that question also we were asked to do this, that is OR, then XOR, then OR, then XOR, and continuously like this, that is in alternate fashion. So whenever we are asked to do these things in an alternate fashion in a tree, then the height of these nodes play a very important role, keep this in mind, right? Or the level of these nodes, right? So that's why now what I will do here now is I will calculate the height for each of these nodes. So for that let us draw an array here. So now let us start filling the array values one by one, that is the height of each of these nodes. So since we know that we will start from the root node, so let's say that the height of this root node is actually 0, and then the height of the child of this root node is 1, and then the height of the child of this further nodes is 2. So 0, 1 and 2. So this is my level array, right? I hope you got this. So once we have calculated the level for each and every node, so this level array can help us now in order to determine whether to add a value of +2 to a particular level or a value of -2 to a particular level. So in order to explain you this concept using the level array even more better, let me draw 2 figures. So now since these were our given queries, right? So what now I'm saying is, let us actually perform these queries one by one, and I will perform it on both the sides, that is this side and this side. So in this side, as I have written that what our eyes will see, so what I will do in this side is the same thing as the question has asked us to do. So if the question will ask us to add a value of +2 to this node and -2 to this node and again a +2 to this nodes, then I will just do the same thing without any change. But our algorithm will not be able to do this directly, right? So whatever the algorithm will do with this tree, I will write here. So that's why I have drawn 2 figures here. So let us do it one by one. So since in the first query it wants us to add a value of +3 to the node 2, what I will do now, I will add a value of +3 to this node here, just as been instructed in the query to do. And since I have added a value of +3 to this node, it means that in the direct child of this 2 node, I have to add a value of -3. And I will stop at this point because there are no further childs of both of these nodes, right? So we ultimately want to do these things. That is, ultimately after performing these operations, I want to have a value of +5 on this node, I want to have a value of -2 on this node, and I want to have a value of -1 on this node, right? If I want to do the same thing with this side, then I won't do it directly. So what do I mean by this is, as we have already calculated the levels for each of these nodes, that is 0 and 2, so let me write that here only. So we know that this is our 0th level, this is my first level, and this is my second level, right? And obviously this first level is my odd level, and this 0 and 2 levels are my even level. And before actually seeing how the algorithm will work for this side, I want to tell you one more thing. So since this was our Euler 2 array, right? So this was our Euler 2 array, but now what I'm telling you to do instead is, for the even level nodes, that is, since here the 0th level and this second level are the even levels, so now in this Euler 2 array, nodes we encounter on the even level, so whatever values they will possess, I will directly write those values in that Euler 2 array, right? But for this odd level nodes, that is here the second node and the third node, instead of putting this 2 and 1 in the Euler 2 array, I will actually put -2 and -1. Right. So now what I'm saying you to do is, instead of putting this 2 and 2 here, that is the value for the second nodes which was present at an odd level as of now, I will put a -2 here actually. Similarly for this third node also, I will put -1 instead of +1. So since the third node is represented by these 2 indexes, so that's why I will store here -1 instead of +1. And you will very soon realize how this technique or little modification will help us now. So this is the Euler 2 array that we will construct initially based on the level of the nodes. So this is the current status of my Euler 2, right? So whatever Euler 2 we will construct, it will be this only, right? So whatever nodes are present at the odd level will actually hold the negative value of the original values. And since the odd level nodes have a negative value of their original value, so that's why here instead of this +2, it will be -2. And similarly, instead of this +1, I will write here -1. So now, since I want to perform an operation on this subtree of second node, so we know that for the second node, this is the required range. So whatever operation I will apply, I will only apply to this particular range. So this is our left index and this is our right index, right? So that's why I will say here that t.update from the left index to the right index. So whatever operation I will perform, it will only be performed in this range. So now, what technique I'm telling you to apply is, since in the question it wanted us to actually add plus 3 here and minus 3 on the childs, but now I'm telling you to do instead what is, since this is an odd level and it wants us to add a value of plus 3 here, but now instead of adding this plus 3, just add a minus 3, right? So if I add minus 3 here, that is on the odd level x, so I will get what? I will actually get this. So here, so in order to do this, I will actually pass minus 3 here, right? So when I will pass minus 3 here, it will actually add minus 3 in this whole range. It means that it will actually add this minus 3 in this node also and in this node also. I actually did an opposite thing. Since the question wanted us to add a value of plus 3 on this odd level node, but now what I did was, instead of adding this plus 3, I added a value of minus 3 on this odd level node. I did the same thing actually for this entire subtree and not just for this node. So I added minus 3 here also, minus 3 here also, and minus 3 here also. And now if you calculate actually, then actually after performing this query, I want just for this node. Instead of adding this plus 3, I added a value of minus 3 on this odd level node. I did the same thing actually for this entire subtree and not just for this node. So I added minus 3 here also, minus 3 here also, and minus 3 here also. And now if you calculate actually, then actually after performing this query, I wanted it to have a value of 5, I wanted this to have a value of minus 2, and I wanted this to have a value of minus 1. Alright, and now if you calculate it for this subtree here, that is after performing this operation that I just told you, then it will be equal to what? It will be equal to minus 5, it will be equal to minus 2, and it will be equal to minus 1. So if you have noticed, then here we wanted to have a value of minus 2, and we are getting here a value of minus 2. Similarly, here we wanted a value of minus 1, and here we are getting a value of minus 1. But here we wanted a value of plus 5. But here instead of this plus 5, we are getting minus 5. So out of this minus 5, I want to have a value of this 5, that is the actual value. So how can I get this 5 from this minus 5? Just take the negative of what is stored here. So minus of minus 5 is plus 5 only, which is our required answer for this node. Right. So that's why this trick is helping us in order to actually determine the value for each and every node after the operation. So that's why I told you that whenever the level of the given x node for a query is odd, then instead of adding this given val in the query directly in the whole range, I will actually add a negative value. Right. And since for the odd levels, I have initially stored the negative values instead of the original positive values, so they will cancel out each other somehow. Right. And even if they don't do so, I will actually take the negative of whatever the result will be stored at a particular node, and that will always give us the correct answer. And for the even level nodes here, whatever the answer will be stored here will actually match what we want. So we don't have to do anything for the even level nodes. It will always contain the right answer. But for the odd level nodes, I have to actually print or return the negative of what is stored. So that's why if it is an odd level, then in this range, in the Euler 2 array, I will increase each and every node by a negative value. And I just told you how can we use this simple thing in order to determine the value of each and every node in this subtree. That is the correct value. So for the even levels, it will print the same value, but for the odd levels, we have to take the negative of what is stored. Right. And if this is not the case, that is, the level of x is not odd, that is, it is even. So if this is even, then what I will say here that again I have to update this whole range only from left to right, but instead of adding minus 3 in this whole range, I will just add a plus 3 here. That is the opposite. Since this query has been performed, and now I want to perform this query. So as you can see that in this query, I want to add a value of plus 2 on the first node. That is plus 2 here. And if I add a value of plus 2, I want to add a value of minus 2 here and again plus 2 here. So this is the actual thing that we want to compute. Then if I write here, then I actually want to add a value of plus 2 on the first node and then minus 2 here and then again plus 2 here. Right. So what this is equal to? It should be equal to 3 minus 1, 3 minus 2 plus 2 0 and minus 1 plus 2 1. Right. So the actual values on these nodes that we should get after performing the second query are these. Right. And if I try to do the same thing here in this side, but using the logic that I just told you. So currently my x is 1 and my val is 2. So my x is 1 and my val is 2. And since my x is 1, so what is the level of 1? That is this level. So it is 0. And we know that 0 is an even level. And if it is even level, it means that we have to execute this statement. That is, I will first find the left and the right index for the first node using the Euler tool. If you look in the in time and out time array for the first node, then here it is equal to 1 and here it is equal to 10. That is, in this Euler tool array, in the first index, this will be my left index for the first node and this will be my right index for the first node. So whatever operation we want to perform now, I want to perform in this range. Right. We have got our left and right part. And as I told you already, that if it is even level, then instead of adding minus 3 as before, I will just add plus 3 as given in the question or the query to do. So I will just add plus 3 in this whole range. So what instead of adding minus 3 as before, I will just add plus 3 as given in the question or the query to do. So I will just add plus 3 in this whole range. So what will happen if I add this plus 3 here in this whole range? In each and every subtree of this first node, I will add plus 3. So let us see what will happen after doing this. And sorry, this is not 3 actually. It is now 2 for the second query. So it was 3 for the first query and it is 2 for the second query, as you can see. So it was 3 for the first query and now it is 2 instead of this 3. Now I want to add each and every value in this range by plus 2. So let's see what will happen if I do this. So if I add a plus 2 to each and every value in this subtree like this. So what value we will get? Let's see. I will add plus 2 here. Here also, here also, here also, and here also. And if I sum this, then this will be equal to 3, this will be equal to 1, this will be equal to minus 3, this will be equal to 0, and this will be equal to 1. After performing this operation using this logic that I told you, I will get this tree, right? Now if you compare both of these trees, then actually after performing the second query, I wanted my tree to look like this. That is, I wanted each and every node to possess these values, right? But after performing the logic that I told you here, I am actually getting this tree. If I compare the node values one by one, then let us start from the root node only. So since in this value for this tree, then it is giving us 0 and 1, which is correct. And if you look for the second and the third node, then we wanted 3 and minus 1, 3 and minus 1. But instead of this 3 and minus 1, in this tree we are getting minus 3 and 1, right? That is of both of these values. So if I take the negative, I will get after performing the query the even level nodes. Similarly for this else if condition, then only it will give this x node is even or odd. So if it is odd values, but these three queries. So if you look, then it is containing here. Then instead of this 3, so this will be my correct value here. So in this way, I'll perform this query. And now if it is whole level, so I will check if this 2 is present at an odd or even level. So since this 2 is here present at an odd level, so I will just take the negative of whatever value it is holding. So since it is holding this last value it is containing, I have explained it holds, right? And I told you in this question, instead of directly holding the original values, I will construct this Euler tool. That is, for the odd level, I will actually store the negative values of what it should hold, right? And once I have constructed this order tool initially, I also told you to calculate the level of each and every nodes, because this level of nodes will actually help us to determine what update function we should apply in the query. So if the level of the current x was an odd level, it means that I wanted to update the whole range by negative value. What is the query is asking us to pop? So if the query wants us to add a value of plus val, then instead of this plus val, I will add a value of minus val in this whole range. And whatever tree we will get, we saw that for the even level nodes, we will get the correct value, but for the odd level nodes, we will get the negative. So I'll just take the negative once again in order to get the correct value, right? Similarly, if this was not the case, that is the level of a given range by this to the platform. And if you're really enjoying the video, and I will store it in a vector, let's say as val. So let me declare this val here globally. And since the maximum value of n can go up till 2 into 10 to the power 5, so once the input for the n integers is done, what we will do next? I have to take the input for the tree, that is for the n minus 1 lines, right? So that's why for each line there will be two integers, that is u comma v. I have to draw a bidirectional edge between them, right? So for that, let me declare an adjacency list here. So it will be also the same size, that is 25 plus 1, and I think this should not be a constant expression, right? So let us take the so let us now direct the edges. So I will say here that g of u, I have to take the input for the m queries, right? That is from 0 to n minus 1. I will go, and for each of the query, I will first take the input of the type, right? So if it is of the type 1, so if it is of the type
Okay. Go to the higher page. First line, two integers and n. N is the number of array values. Each of the next n minus 1 lines contains this. Each of the next m lines. That okay. Let's parse this question. Class. Okay. You know what? You just need a standard template. Just need a standard template for segmentations. So can copy it like this, right? And then this. Mhm. This is the query. Okay, this is update. Okay. And we also need to build. We have the array. Array. This will be array starting. This is node. This is a start. This will be end. And yeah, that's it. This is end.
and this is okay. This is and 3 of node should be node this and this should be node. Why is this throwing metal? Oh, static. And then this. Perfect. This is our segmentary initialize. Yeah, right. Now let's create an adjacency list. Adjacency list. New list. But before that, this dot n. What do we have here? Int n10 equal to 0 next int n10 equal to 0 next int. Then fill in the array, int array, new int, int equal to 0 and this the minus plus array of I equal to 0 next int. Now we have to create the adjacency list for it, right? 0 adjacent and minus 1 plus plus. What do we take? We have v into v equal to c dot next int into u equal to c dot next int and adjacency list of v dot add u. Yep. Huh. Oh wait, first, yeah, I know why it's throwing an error. We need to initialize. This starts from 1, right? Yeah, it starts from 1. Need array list. And this is new int of size n. What is the error here? What? Nah, I just want to know this error. less than equal to. Uh, what's less than this? This is from 0 to n. Because this is for x. Oh. Yeah, I tried writing this. It's giving an error. No, this should start from 1 and run up to n minus 1. Start from 1. Zero, yeah, till n minus 1. And this, uh, yeah, okay. X error. I want to fix this error. How do you write this thing? Array this. Is it size n or size n minus 1? Shouldn't it be n minus 1? There are n elements though, right? Hmm, okay. So we have this. Let's see dot. Now for int I equal to 0, I less than n, I less than s. Or just write a while loop n minus it's greater than right. So what do we do here? You need to find what type it is. If type equal to 1, do this, else this. For type 1, the print the current mode value.
then it means that I want to actually update the tree, right? So this is an update operation. But if this is not the case, then it means that the query is of the type 2. So it means that I have to actually answer the query. So I have to find the answer for this query. And then at last I will just return. But we know that before actually starting our query operations, we first have to construct the Euler tool, right? And we have to do it in one page only. So that's why I will declare my Euler tool array here, right? And initially, since I don't want to use the 0th index, so that's why I will hold some random value here. Let's say -1. And now, in order to construct the Euler tool, what we have to do, we have to use the in time and out time arrays, right? So that's
Euler tool. Euler
why
tool.
I will use here and declare here the two arrays. That is the in time, which will be of the size as this, right? And in the same way, I also have to declare the out time array, which will also be of this size only. So once I have declared these two arrays here, I also have to declare the timer, I guess, right? Which will increase by 1 every time. So this will be equal to 1 initially. And now once I have written this, I think I should start my Euler tool operation. So I'll call the DFS for the Euler tool. That is the Euler DFS. And I will start from the root node, obviously. Right. What is the parent of the root node? So there is no parent for the root node. So that's why I will take -1 arbitrary value, right? So that's why I will take it as -1. Since I also have to store the level for each of these nodes, if you remember, right? So I also want to store the levels for each of these nodes. So that's why I will also use a level array here, which will be of this size only. So now,
Okay, so you need 3 things. You need array list. You need int Euler tool. This will be of size n plus 1. You need n time. This will be of size n plus 1. You need out time. This will be of size n plus 1 again. And you also need a level array n plus 1. Euler tool for the 0th index, set its value to -1 and call a Euler TFS. We'll send the Euler tool array. Parent will be -1 and we also name the level array initially, right?
I will pass the level for the initial root node. So what is the level? So it is 0 only, just as I told in the explanation. So let us now write our Euler DFS function here. So I will say here that the level for this node will be equal to this t, right? And the in time for this node will be equal to this timer plus plus, because every time.
Okay, so this, oh, we also need a timer. This these are global variables. Time. These are global variables. This is so stupid. Why is this? Why is this long?
some timer value is stored in the node, it will get increased by 1. Also, the Euler to array will hold this current node because it is getting visited for the first time. But as I told you that it increased by 1. Also, Euler TFS
int node, int parent, and int t. What is t?
function here for the initial root node. So what is the level? So it is 0 only.
Okay, this is the level. Fenwick.
Just as I told you in the explanation. So let us now write our Euler TFS function here. So I will say here that the level for this node will be equal to this t, right?
Excellent. Oh my god. It needs to be started.
and the in time for this node will be equal to this timer plus plus, because every time some timer value is stored in the node, it will get increased by 1. Also, the Euler 2 array will hold this current node because it is getting visited for the first time. But as I told you that it will depend on two conditions. That is the level of the node. We have to check, right? So if the level of the node here is actually odd, so if it is odd, then I told you that we will actually store the negative value of it, right? So if this is odd, then we will store the negative of whatever value is present in this node. That is this. And if this is not the case, then we will just store the positive value, just like this. And once this is done, I will start traversing the left and right parts. So
Euler tool is basically an array list. This timer if level of the node modulo 2 equal to odd, then array of node, else array of node.
I will traverse the adjacency list here one by one. I will check that if this child here, if it is not equal to the parent. So if this is not equal to the parent, because this is how we do a DFS in a tree, right? We don't use a visited array. So if this is not equal to parent, then I will again call the same ordered DFS here. And this time the parameters will be what? So the node will now be my child and the parent will be this node. And the
Or int neighbor in our adjacency list in our adjacency of this if ni is not equal to parent, what do we do? We call this function again where node is ni, parent is node, and d is the level, so increase that level.
depth will increase by 1. So this. And once I have written this, Now this part will do the backtracking. So we know that doing backtracking, I have to fill the out time array. So the out time for this node will be what? It will be timer plus plus something, right? And since I'm doing the backtrack,
Hmm.
it means that I am leaving this node, right? That is, I'm going out of this node. So
So fill this Euler tour as well.
in the Euler tool array, I also have to push this node again. This same thing here. So let me copy this. So this. And then finally I just have to return. So in this way our Euler tool will be constructed. And once this Euler DFS is calculated, so now I will declare a segment tree. Just have to return. So in this way our
At this index, we add timer plus plus, and then just copy this. Hmm. And parent. Ah, is undefined. Oh, this will be me. This will be node. This will be plus one. Now we have to build a yes. Wait,
our Euler tool will be constructed. And once this Euler DFS is calculated, so now I will declare a segment tree, right? And this segment tree will be constructed on this Euler tool array only, right? So this.
hmm.
And let me now copy my standard segment tree template here.
So just declare segmentary p equal to new segmentary, and we send the Euler tool array. We send the Euler tool array. Oops, this needs to be val. Correct this here. This needs to be val. Okay. Why is this giving me an error? It is down the Okay.
So this is my standard segmented template here, as you can see. This is a lazy propagation template, obviously, because I have to update the whole range, right? So the standard one will not work. I am using the lazy one, right? So keep this in mind. So now, as I have declared the segment tree here, let us now start our query operations one by one. So what I told you that for the type 1 query, we will be given two things, that is the x node and the val, right? So what we have to do here,
Hmm. For the type 1, we'll have X node and value. Okay.
have to first find the left index and the right index in the Euler 2 array for this x node. That is the left index and the right index. And this left index is calculated in the out time, in the in time array like this. And similarly, the right index is calculated in the out time array like this. And once I have found the left index and the right index in the Euler 2 array, what I told you to check? I told you to check if the level of this x node is actually odd or even. So if this is odd, then if you look here, I told you that if this is odd, then I have to update the range like this. That is the negative of val. So if this is odd, then I will say t.update from this left index to this right index by a negative value of this val. And I just told you in the explanation very well why we did this. And if this is not the case, it means that the level is even. And if the level is even, I have to update the whole range by this plus val only and not -1. So in this way, the first type of query will be performed. And in the second query type,
This is a difficult problem. This is a very difficult problem. In time of X and out time this node. Now if level of X, if this is odd, if it's odd, then we dot update. We have the index, we have the value, and we have mm, we have range from left to right, and then we have the value else we dot update left, we have right, we have value, that's it, right?
I have to answer. So how can you find the answer for the second type query? So in this, I will just be given an x, right? If I want to find the value for the x node here, let's say for this query, I wanted to find the value of second node here. That is this node here, which should be 3 here, which was -3 here, right? So obviously, since the
Just check the level.
operation was being performed on the Euler 2 array, which was passed in the segment tree initially. So know that for this second node, present in this range, right? And whatever the value this left index will hold here for the second node will be the same value as this right index will hold for the second node. That is here -2 for both. And since I just want this -2 here, so that's why, how can I obtain this value? I can just do a range query, that is the query sum for this range, that is from 7 to 7, or the query range from 2 to 2. So this will give us what? It will give us the summation of this range. And what is this range summation equal to? It is equal to nothing but the value of that particular index that should be present after performing the first type queries, right? So that's why I will say here that the result that we should get will be equal to what? It will be equal to t.query from the in time of x till the in time of x only. And you can also write it here from the out time of x
We are looking for
till the out time of x, because both are containing the same thing only, right? So you can either write this or this, there is no problem. So once I get this, I will get the value as required, right? But I told you in the explanation that whenever we will answer the second query, for the even level nodes, we will get the correct value. But for the odd level nodes, we will get the negative actually, right? So that's why here, we will check that if the level of this x is even or odd. So if this is odd, then we will do something, otherwise we will do something. So if this is even, then whatever result value we got is correct. So I will just print this. I will, right. So now if I run the rather just print it like this.
This is the update. This is the answer. So int result equal to t dot query in time of x till in time of x if wait int x equals int if level of this modulo 2 equal to 1, then this needs to be into result, else is putting the result. Okay, let's see for a bit. What do we have here? We have the left range, we have the right range, int left, int right, or left, something.
And in this way, I think the whole code will be written, right? So now if I run the code, let's see if it is giving correct outputs or not. So as you can see that we are getting the correct results here, right? So now if I try to submit the solution on the code forces platform, let's see if this is giving accepted or not.
Wait, it's this one. How do you write this left and right thing? Oh, yes. Hmm. But wait, we don't want point update. We need range updates. Want point updates, but range updates. Fix that. What why is this push here? What is the use of push? What?
We are getting the correct results, right? So as you can see that the solution is accepted. This simple value to concept here in order to construct the value to array. Old module that goes by the name why did the cow cross the road 3? Correct, 2 1 plus 1. So let me paste my standard segment tree template here. So this is my standard segment tree template here. But in this template, as you can see that in the input here I'm passing the size. But in this template I used to pass the actual vector. So this is now what? This is my size here. Let's say it as capital N. So this will be equal to now this. And this array will now be equal to what? So this I will have to resize this array. Right? And this will be enough. So I will say here that arr.resize this total size equal to 0. So what does this statement is doing here actually? So this statement is responsible here for creating this array here. With each and every element also declare a map. So xi is equal to empty.find both the map. So during exit I think the whole code will be written for this test case, right? So that's why I will write here. So we will. So I really. Hi everyone. So welcome. I will just store if my I is less than. This is my med, and since what I'm saying is in this 0 and 2. If so, we can't value it will return. I will just store this in a variable. Let's say left operand value. So how we will explore this left part? So for doing this, we will only call the same function again. So instead of this node now, it is equal to 2 into node plus 1. If this that is x and right to the right part like this. And also I think I should give here an ender here because every time I have to print output on a new line. And let's see if this is getting separated into the let us fill these parts quickly here. So we know for t dot square the code forces given 20. So right. So what I told you that whenever we be standing at the current left with this ender, these parts quickly here. So we know here that this first to create each and every single bit. Really hope that if you try to go to the left part here, we will not go that part. Why? And now I have to actually iterate through the m to 2, then segment here. So type that is type each query. I will pass 3 and my r is equal to x, which I have here completely. The only task we are left with is to write this query function. So we are provided with this x, l, and r. To the m equal to let me declare. So we know set t dot of the code will be given 20. So after right. So what I told you, I value to be actually present particular will again less than there we have will be that is node value. L is less than 0 and 2 possible. And same function and that right. So when true, it means I think I have to print try to submit this and got it accepted on the platform. So really hope that you have understood. I can see that it is accepted successfully. Code that we just wrote. So now I have to print the output on a new line. Let's run the code and see if this is fine or not. So you can see the outputs are correctly passing. So this is the code that we just wrote. So now let us try to the first is 2 only. So this is not the case. It means that we have to explore both the parts. So I just find out we have to explore that. Also told you. So if the current type 2 and if this is not the case, it means input of the actually makes sense. So if you still we will explore both. Won't explore the left or but now this whole range. But when you will solve some questions from other platforms, then they will not allow you to select this whole range directly. That is what I am trying to say is I told you that index says that they leave node. I told you before in the secure is this. Why? Because the move to the code iterate to the m query is given. So for each and every and if this is not the case, it means this and for this we want to print the answer. So I will say t dot the code forces reduce will be this, right? And in the update query, we will be given 2 integers actually. That is the index which I have to update and the value with which I have to update. This index equal to this value and it does just return. So after doing this, I think I have written the void function here completely. The only task we are left with is to write. Okay, so hi everyone. So welcome back. But if this is not the case, print it like this. Segment here. Let us now start our query operations one by one. Then we'll not array. I also have to push this node again. The same thing here. So related. So now I will declare a segment tree, right? It will be constructed on this euler 2 array only, right? So this. And let me now copy my standard segment tree template here. So this is my standard segment tree template here. Template here. you can see this is a lazy propagation template obviously because I have to update the whole range, right? So the standard one will not work. I am using the lazy one, right? So keep this in mind. So now
Mm. Let me call the scanner. What?
Now, as I have declared the segment. Okay, so hi everyone. So welcome back to the ninth video on the segmentary series. So today in this video we will be discussing this problem from yesterday's lead code bi-weekly contest, and it was the last problem and it goes by the name shortest path in a weighted tree.
3315.
The concept problem from yesterday's
3514. 2312 traded shortly.
lead code bi-weekly contest, and it was the last problem and it goes by the name shortest path in a weighted tree. The concept that was used in this problem is Euler 2 and lazy propagation. Although it can also be solved using Fenwick trees, but since it can also be solved with the segment tree, so that's why I'm including it in the series. And before starting the video, if you have not yet subscribed, and a total of 10 videos are present in the advanced like this, that we will be given an integer n, right, and an undirected weighted tree rooted at node 1 with total n nodes numbered from 1 to n, right. So we'll be given an integer n and a tree, and that tree will be a weighted tree, that is between every two nodes some edge weight will be present, right. And the
Huh.
Okay, I'm back.
root of this tree will be at node 1. This thing is represented by a 2D array edges of length n minus 1, where edges of I would be equal to ui, vi, w of I. It will consist of 3 integers. This thing will mean that an edge is present, and which type of edge? So a undirected edge, right? That is a bidirected edge will be present between the nodes ui and vi with the edge weight of w of I. So the same thing is written here. And after that, you are also given a 2D integer array queries of length q, where each query is either of the first type or of the second type. So if the query is of the second type, then we have to compute the shortest path distance from the root node 1 to the node x. And in the first type query, we will be given three integers, that is u, v, and w dash. So what we have to do in the first query is very simple, that we first have to go to the edge which is connecting these two nodes, that is u and v, and whatever edge weight is present on this edge, we have to replace that edge weight by this new edge weight, that is w dash. So the same thing is written here if you read, that is update the weight of the edge between nodes u and v to w of dash, where u, v is guaranteed to be an edge present in edges. And after all the queries have been performed, we have
Okay, the weight of the edge between nodes U and V to W. Compare the shortest path distance from root node 1 to the node X.
to return an integer array answer, where answer of I will be the shortest path distance from node 1, that is root node, to the node x for every second query.
What is
So this
this
is the question,
question?
right? And for this question, we are provided with three examples. Since all these three examples are actually kind of short, so I think I should explain you these three examples here also. And after this, we will take some bigger example and try to understand each and everything in very detail with that bigger example, right? So for now, let us understand these three examples one by one. So in this example, as you can see that the n value is 2, that is a total of 2 nodes will be present in the tree, and this is my edges array. So since only one element is present here, it means that an edge will be present between the first and the second node having an edge weight of 7. So the same thing has been drawn in the photo also. If you see, two nodes are present, that is 1 and 2, which has an edge weight of 7 between them. So by following these two instructions, our tree will be made, and then we have to start our queries. So the first query is of the second type, that is we have to compute the shortest path distance from the first node, that is the root node, to the second node. So since the first node is located here and our second node is located here, so we want to find the shortest distance between the first node and the second node. So what is the shortest distance here? So clearly visible, it is equal to 7 only, right? So that's why the output for the second type query here is 7 written. Let us now move forward with the second query. So the second query is clearly of the first type. So since it is of first type, so it means that we have to update the edge weight between the nodes 1 and 2 with this 4. So currently between these two nodes, that is between 1 and 2, the edge weight that is present here is 7, but we have to replace it by 4. So suppose the edge weight now that is present between this 1 and 2 is 4 now, that is we have replaced it, right? So instead of the 7, we have currently 4 here. And now if you move forward and move to the last query, which is of the second type, and again we have to compute the distance from the root node to the second node, then in that case, what would be the shortest distance? It will be this 4 only, right? So that's why the output here is, and again, right? So instead to replace it by 4, move forward with the second query. So clearly, and short instructions are from the first node, that is the root node, to the second node. So since the first node is located here and our second node is located here, so we want to find the shortest distance between the first node and the second node. So what is the shortest distance here? So clearly visible, it is equal to 7 only, right? So that's why the output for the second type query here is 7 written. Let us now move forward with the second query. So the second query is clearly of the first type. So since it is of first type, so it means that we have to update the edge weight between the nodes 1 and 2 with this 4. So currently between these two nodes, that is between 1 and 2, the edge weight that is present here is 7, but we have to replace it by 4. So suppose the edge weight now that is present between this 1 and 2 is 4 now, that is we have replaced it, right? So instead of the 7, we have currently 4 here. And now if you move forward and move to the last query, which is of the second type, and again we have to compute the distance from the root node till the
Was this question asked in any contest? Bi-weekly contest? 154. Good. 154. And the last contest was bi-weekly 171. 171. Okay. Just 17 bi-weekly contests earlier than this recent contest. Yay. Yeah, also my rating got updated from 1665 to 1713. Sixteen 65 minus 1683. It is 28. 1693. 28. And then 1713. 1665. 48. 48 minus 28 is actually 20. So a jump of 28 and then 20. Yeah. When do you get the what's this one? When do you get the night time on at what rate and or at what percentage? Yeah, my rating is literally about 1600. It's like 1700. Check according to the latest. Higher around 1850. Yeah, some users will do it. That's same. Wait, 16.
second node, then in that case, what would be the shortest distance? It will be this 4 only, right? So that's why the output here is 4. And we just have to return this array here. So I hope this first example is clear. Let us move to the second example. So in the second example, we are provided with 3 nodes. That is the first, the second, and the third node. And the first node is the root node, obviously. And then in the edges array, we are given 2 elements. That is, a total of 2 edges will be present. So the first edge is present between the first and second node, which has an edge weight of 2.
Hmm.
So as you can see here also that this edge weight is present between the first node and the second node, which has an edge weight of 2 between them. And according to this second element of this edges array, an edge weight should be present between the first and the third node, having a value of 4. So here an edge weight is present, that is this one, between the first and the third node, which is having a value of 4 as the edge weight. So we are done here. Our tree is ready. And now if you move forward and execute the queries one by one, then according to this first query here, it is of the second type. That is, we have to compute the shortest distance from the root node till the first node. So what will be the shortest distance from the first node to the first node? It will be 0 only. So that's why it is written 0. Now for the second query, we have to compute the shortest distance from the root node till the third node. That is from this node to this node. So what is the shortest distance? Will be this, it will consist of this edge only, right? So it will be equal to 4 only. So that's why it is 4. And now if you move forward and execute this third query here, so it is of the first type. That is, we have to update the edge now. So between what nodes we have to update the edge? We have to update the edge between the first and the third nodes. That is this edge only. And the new value should be equal to 7. So instead of this 4 now, it is 7 now. So 2 and 7, right? So once we are done with this query, let us move forward. So now we have to execute the second type query. That is the shortest distance between the root node and the second node. That is between this node and this node. So since only this edge weight is present, which is the third node, the shortest forward with the third example here. So in this third example, 4 nodes are given, and this is the description of the tree. And by following this description and node 4, that is this node and this node here. But 2 plus 1, and if you move forward in the queries array, so knowledge distance will be equal to 4, right? And also the total number of queries length can be up to 25 also, right? So these two constraints are important, and by keeping in mind these constraints, we have to derive a solution that can pass every test case. So this is the whole problem statement, right? So if some of you have already solved the CSCS problem set for the tree algorithms part, then you must be knowing that there is a similar problem present on it. So this is the problem that I'm talking about. So in this problem also, you have to do the exactly two things, not exactly but very similar. So as you can read that we will be given the description of the tree here, and each node has a value. So in this question, the edge weight has a value, right? But in this question instead, the nodes have a value, right? And the same thing is done here. If you see, that is for every query, we have to change the value of the node s to x, and then compute the sum of the values on the path from the root to the node s, right? So these two things are very much similar to this problem. The only difference is that in this lead code problem that was asked in yesterday's bi-weekly contest, instead of values being given for the nodes, the values are being given for the edge weights, right? That is along the path. But in this problem, the values were given for the nodes and not the edge weights, right? And if I make you see the solution here, then I have solved this problem before using the two concepts, that is Euler tool and segment tree, right? So as I told you in the starting of this video, that I will solve this problem also using the same concept only, that is Euler tool plus the segment
This is
tree, which will use lazy propagation. that is range update. So if you're not familiar with lazy propagation, please go back and study this concept first, and also the Euler 2 concept, because even if you have not studied it yet, you can simply watch back the previous video that I just uploaded, because in that video I have covered Euler 2 in very detail, like how it works under the hood and everything is performed, right? So you can watch that video for the Euler 2 purpose, and even if you don't want to study and just want to treat this segment tree as a black box, you can treat it. It is up to you. So if you have not yet solved this problem, please, I will suggest you to solve this problem first and then come back to this problem, and then everything will be so easy to you. So now let us start decoding this problem step by step. So the first thing that I want to tell you about this problem is, this problem always wants us to compute the shortest path from the root node to some other node, right? So notice this word, shortest path. Do you think that this word is actually meaningful in this question? I don't think so.
Yes, use Dijkstra's algorithm or don't. Complete the shortest path. Distance from root node 1 to x. This is a graph, right? This is a graph, so it can have multiple edges, multiple connected edges. So why not? So why not use a Dijkstra's algorithm?
Why? Because whatever structure will be given in this question will always be a tree, right? Clearly written here. It will be a tree, and we know that
It is a tree. It is a tree, so it will never have a cycle present in it, which means you can, there is only a single path to that node from a given index.
in a tree there are no cycles, and since there are no cycles, then it also means that if you take any two nodes in the tree, when I say any two nodes, I mean any two nodes. So if you take any two nodes in the tree, there will always be a unique path between them. The path between every two nodes will be unique, and thereby saying that compute the shortest path distance from some node to some node is not necessary. You can simply remove this usage of this word here. So instead you must read it like always compute the path distance from some node to some other node, right? Why? I just told you, because there is nothing like shortest path in the tree. There is just a path in the tree, right? Let us now try to go to the blackboard and understand the same thing in very detail, but with a bigger example, right? So consider this tree now that I have considered by myself, right? So this is a beautiful tree that I have drawn for you, and let us also consider these 5 queries here. So this is my first query, this is the second query, this is the third query, this is the fourth query, and this is the fifth query. And also since the second query is coming 3 times, so it means that the expected output should consist of 3 integers. So as I told you in the beginning of this video that I will be using Euler 2 concept in this video also. In the first place, we need to verify and find why we need Euler 2 actually in this problem. Because we know that Euler 2 is only helpful in those situations, right? So Euler 2 is only helpful in those situations when we want to compute something for the subtree, right? But in this question, how the subtree is getting affected, because suppose I'm updating this edge weight to some another edge weight, let's say x. So how by doing this the entire subtree of this is getting affected? Is it possible, or is it happening? Yes, it is happening. Why? So for that, let us compute an array that will hold the distance of each and every node from the root node initially. So let us now try to write the depth of each and every node present in this tree. So initially, as you can see that initially, what is the depth of this first node? That is the distance of the shortest path, or rather path only, as I told you, from 1 to 1. So it will be equal to 0 only, right? So the distance between a node to itself should be 0, right? So that's why I will write here 0. Now what is the distance of the path between node 1 and node 2? That is here, this root node and the second node which is present here. So it is equal to 3 only. So I will write here 3. Now what is the distance between root node and the third node? That is this node. So it will be equal to 3 plus 6, that is 9. So it will be 9. And now what is the distance between the first node and fourth node? That is this node. So it will be equal to this path, that is 1 plus 10, that is 11. So it will be equal to 11. Similarly, what is the distance between first node and the fifth node? That is this node. So it is just 1. So 1. And now what is the distance between first node and sixth node? That is this node, which will consist of this path. So 1 plus 10 plus 4, which is 15. So 15 here. And now what is the distance between the first node and the seventh node? So it will consist of these two paths. That is 1 plus 9, that is 10. So 10. And now what is the distance between first and eighth node? So it will consist of this path, which is equal to 10 plus 2 plus 1, that is 13. So 13. And finally, what is the distance between first and ninth node? So it will consist of this path, that is 3 plus 2, that is 5. So 5. So in this way, I have computed the depth array for the initial given tree here, right? So now, as I was trying to tell you that how Euler 2 is actually helpful in this question. So in order to understand this, why Euler 2 is actually helpful here, let us try to change some edge weight. So to understand this, let us change some edge weight. So if I change, let's say this 10 equal to, let's say 12, right? So what will happen if I change this 10 equal to 12? So let us do that. So now what I'm saying is this is no longer 10, but rather 12. So what has happened when I change this edge weight from 10 to 12 now? So clearly, if now I again try to write the depth array for this tree, then it will no longer be same. Because now if you try to compute, then clearly the path distance, or rather the shortest path distance from the root node to some of the nodes will change now, right? So if you look here, then the shortest path distance from this node to this node will remain same. Similarly, the shortest path distance from this node to this node will remain same because they are not changed. Similarly, the shortest path distance from this node to any of the nodes present in this subtree will also remain same. But if now you try to calculate the shortest path distance from this root node to any of the node present in this subtree, then it will no longer match here. So you can see also that, because now if I try to calculate this sixth node, 1, that is 13. Now this value should be equal to 13. What is the shortest path between this 1 and 6? Shortest path between this. So this is the thing, that this edge weight, that is this subtree here, the shortest path from the root node will also change, right? Because since this edge weight is leading to, now the depth array can be helpful in this case. So that's why you should think of using Euler tool here. So this was the first thing that I wanted to talk about. So let me revert the tree back to its original state. So this was our original tree and this was my original depth array, right? Since Euler tool can be helpful here, as we just saw, because the subtree is getting affected after changing some edge weight. So let us now try to do an Euler DFS for the subtree in order to calculate what. So we know that from the previous video that using an Euler tool we compute few of the things. So the first thing, important thing that we calculate is the in time array. The second important thing that we calculate is the out time array. And along with these two here, I will also compute two things. That is the parent of each node during traversal, right? So I will also compute the parent array and this depth array, right? Suppose now we have started our Euler DFS here, and now I want to fill these four arrays. That is the depth array, the in time array, the out time array, and the parent array. And if you remember also, then we also used to store the node values twice in an array like Euler tool array, as we did in the previous problem. But in this problem, we don't need to use this array or to store this array. And you will soon realize our Euler time array and the parent array. And if you remember also, then we also used to store the node values twice in an array like Euler tool array, as we did in the previous problem. But in this problem, we don't need to use this array or to store this array. And you will soon realize after we finish
Because we only need the depth array.
this DFS call that why we don't need that array anymore in this problem. Right, so till that point, let us fill these arrays first. Right, now we have started from the root node. We know that we first travel the left part and then the right part. Right, and also our timer value initially is equal to 1. Right, so at t equal to 1, we are present here. That is on the root node. So I can say that the in time for the first node will be equal to 1. Right, and now the timer will increase to 2 and I will move to the left part. That is on this node. So now at t equal to 2, I am standing on the fifth node. So that's why I will write in time for the fifth node here equal to 2. Now I will move again to the left part and I will be standing at this node, that is 7th node. So I can say that for the 7th node here, the in time value will be equal to 3. And now, since I am leaving this node permanently and I will not come back to this part, so I can say that in the out time array for the 7th node, this will be equal to 4. And now, as I have explored this left part completely, I will move to this right part. And now I will enter this 4th node for the left part. Out time for the 6 will be equal to 7. And why this is happening? So on the 8th node again, since this is the out time node and I want to leave this 4th node. Time for 5. So 13. And since I will leave this 3rd node at the same time, so 14. And then I will enter the 9th node. It will be 15. And then this will be 16. And as I explored both the parts, I will again be standing on the 2nd node. So in the out time array for the 2nd node, it will be 17. And finally, I will. So let me do that separately here. So since we started from
You know what? I want to check if Larry has solved this problem or not. Of course, he has. He has solved this problem.
Hey everybody, this is Larry. This is me going Q4 of the bi-weekly contest 134. Shortest path in a rated tree. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. So this one I will start by drawing. So give me a second to set up. Should have had this set up. Oh well, technology, you know. But yeah. But the first thing to notice for this problem is that it is. That might take over. It's kind of dirty. But the second thing after that is that it is a tree, right? And what does it mean for when we have a tree? Well, when we have a tree, a rooted them and that everything is the longest path from one node. That means that we can draw about that one node in the top, right? And then now there's only one path from any 2 points in the tree in either case. So that means that from one there are all these you know, like whatever, right? Okay, something like that, right? So the crux of the problem is that, okay, I mean, hopefully if you're watching this video, you already know how to do a general shortest path. So, you know, and in this particular problem, it's a tree. Like I said, there's only one unique path. So you could do it with a depth first search, breadth first search. It really doesn't matter. But from that, you construct, you know, I don't know, I'm just writing around the number, but on edges, right? So, okay. So the idea that I thought it originally was some sort of I should have remembered to look it up, but it's just like some sort of binary lifting, right? Binary lifting related something where maybe we update something, so then we update the binary lifting tree. But I couldn't really figure out easily how to do it, or I mean, not that I think it is possible, but it may be very implementationally difficult, right? Challenging, right? So that's why I was like, am I sure? So the way that I thought about it is that, okay, well, for every update, right? I mean, because if you don't know updates, I think this is a straightforward problem. But let's say we update this edge, right? Well, what does that mean? Well, that means that for me, that means that everything in this subtree of 4 will get some delta, right? for some delta, meaning that okay, if this one goes plus 3, then everything below it is plus 3. If this is minus 3, then same thing, right? Everything under it goes minus 3. So that's basically the idea that I have this one. And then I go, well, okay. And this is literally my step-by-step thought process. I go, okay, well, let's say we are trying to do that. Then how, how can we update so many nodes quickly? Because if we update one node at a time, that is going to be too slow, right? It's going to be O of n, and you have n squared. I don't even have to look at n in the sense that if n squared is fast enough, then the code sucks, right? Honestly, so I didn't really look at it too tightly, to be frank. But yeah, right. My hoodie's a little bit. So anyway, so then I thought, okay, well, how am I going to update these nodes in a funky way, right? Well, the thing that I thought is, okay, well, actually, we can with a segment tree. I don't know. I know. You already know that I hate segment trees by now, especially as a problem on lead code because it's just not really relevant. It is interesting for competitive, I suppose, but it's just not really relevant. And I don't know. It's just another thing, and I don't know. Is it helpful? In any case, but I go, okay, well, because the thing that I like about segment tree for this problem is that you get log n updates, which you kind of need, right? But then I go, okay, well, how do I update, 4, 6, I can't read my handwriting, but all these nodes at the same time with one query, if I had something like a segment tree? Well, then I go, okay, well, if I have a segment tree, then we can just relabel the nodes in a way such that, I think, is it a Cartesian order or Euclidean order? I forget, but I think maybe it's fine called an Euclidean order. But it reminds me of, I forget what it reminds me of. It's like, it's like a way from the depth of search thing, but I forget what it's called. Sorry, friends. But in any case, it's about visit order, the DFS visit order, right? This problem, yeah, and but in that case, one property, and I actually did not remember if this was the case. I just thought, okay, maybe I could do something with visit order. I think this is the case, but I had to, it took me I don't know, 20, 30 seconds to kind of verify in my head, which is that given a node, right? Let me change the color again. Given a node, you can just look at, and the reason why we drew these edges is that you can draw the first edge out and then the last edge.
The root node, and we first moved to the left part and the right part. So when we moved from this node to the left part and reached this, so we know that we are going from 1 to 5th. So since we are going from 1 to 5th, so we know that this 1 must be the parent and this 5th to which we are moving must be the child, right? So that's why I can say here that the parent of this child should be equal to what? I can write here that the parent of 5 is 1, right? So the parent of 5 will be 1. Similarly, the parent of this 7 will be this 5, parent of this 7 will be this 5, and then the parent of this 4 will be 5, parent of 4 will be 5, and then the parent of 6 will be 4. So the parent of 6 will be 4, and also the parent of this 8, that is the sibling of this 6, will also be 4. So the parent of 8 is 4, that is this. And once we are done here, we will now move to the right part. So in this right part, the parent of 2 will be 1. So the parent of 2 will be 1. And then the parent of both 3 and 9 will be 2. So the parent of both 3 and 9 will be 2. And since everything is filled now in this parent array except this first node, because the first node is a root node, so it doesn't have any parent. So we will arbitrarily fill this, let's say, with a value,
Minus
say
1.
So in this way, we will be computing all these 4 arrays here. That is the depth array, in time array, out time array, and parent array. And note that this in time array, this parent array, and this depth array will be calculated before the DFS call, right? So these 3 arrays will be calculated before the DFS call, and then I will do the DFS call here, and then here the out time array will be calculated. So after doing this Euler tour, we know that we declare a segment tree, and in that segment tree, we used to pass some array, right? And in the previous problem that we did in the series, we actually used to build an Euler tour array that consists of 2 into total number of nodes present in the tree, and such that every node appears twice in this array. So we named this array as Euler tour array only, right? And then we used to pass this array to the segment tree array, and whatever operations we did, we only did on this array, if you remember, right? But in this question, what I'm saying is, instead of constructing this Euler tour array during the Euler tour DFS, it will no longer be needed here. Although you can do with it, there is no problem. But I'll be telling you a more intuitive method. Now what I'm saying is, consider this delta array here, that is this array, which will be of the same size as that of the Euler tour array, right? So instead of passing this Euler tour array this time in this segment tree, I will just pass this delta array. So what does this delta array represents? So for a particular element, whatever the value will be written on that index, it will represent the change in the path sum from the root node to that particular node. So you will understand very soon how this delta array will work and help us. Now we have passed this delta array onto the segment tree, right? So let us start executing our queries one by one. So this is our first query. That is, the first query is of the type 2. That is, we want to find the shortest path from the root node to this 6th node. That is between this node and this node. So since in the depth array here, as you can see, we have already calculated the initial distance between 2 nodes, that is from the root node to each and every node in this tree, right? So someone if asks us to return the shortest path from root 1 to the 6th node, so I can simply return this value, which is 15. So in that case, I will just return this 15 here from this part, right? Okay, so once we are done with this query, let us now move to the next query. So in the second query, it is present below it the values that edge weight present between 4 and 5th node with this 13 value. That is this edge weight from 10 to 13. So what will happen? So it will now become equal to 13. Depth array in this array to determine that out of this 4 and 5, which one of them is parent and which one of them is child, right? By using the parent array, we will be able to determine easily that this 4 here is the child and this 5 here is the parent, right? So once we are able to determine this, what I will say that whatever the child out of these two is, so whatever the child is, this child subtree will get changed. Each and every node present in this child subtree, their value will get changed in this depth array, isn't it? So now we know that in order to do some updates for a subtree, we calculate the in time and the out time for this node, that is the subtree's head. So time for this 4 is not, what is the difference is dot update from this 5, the in time with 3. So this
Good.
was 15 plus done with this 2, right? maximum number of nodes that can be present here is only 5, so it will be maximum of this size only. And similarly, let us also declare the in time, out time, and other arrays. So they will be vector of int only, right? So in time, and then out time array, and then depth array, and then the parent array, like this. And let me also initialize the timer with 1. And as I told you that in order to retrieve the old value of the edge weight later on during the first query type, we will use a map data structure. So for that purpose, I will declare a map here. That is, for a particular u, v, I will be storing the edge weight. So once we are done with this, let us now try to write this function. Now, as I told you that first we will create the adjacency list. So for that, we have to iterate through the given edges, right? So this, and we know that this it is a vector. So my u will be what? My u will be it of this 0. My v will be what? My v will be it of this 1. And my edge weight will be what? That is the initial edge weight. It will be it of 2. So I want to direct the edge, that is adjacency list of u dot push back up here, that is v comma w, like this. Similarly, I also want to direct an edge from this v to this u, that is u comma w. And along with doing this, I also want to store the same thing in this map so that it can be used later. So I will say here that, and I will writing performance here as I told, that is first the v, or rather the child. So this is my child here, that is this value has been present in this depth.
I think what I need to do is eat some food. Most probably I will not be back. I will end the stream. I thought of coming back, but I have a meeting later. So yeah, I think I will end it now. I will most probably solve this problem or not solve this problem. I don't know. Ugh, this is a very, very difficult problem of my life. But I need to eat some food now. Okay. Okay, bye.